Is this working?
I think it, yeah.
Kind of.
All right.
Keep crunching.
Pin it that side.
Like maybe here?
Yeah.
All right.
To the other side, so it's not like rubbing. On the inside of your.
All right, but the other, you tend to look that way, and so it's good.
That is true. You always like.
Put it upside down.
Like upside down. Yeah, I agree. How is this? Is this too quiet? I think it's too quiet. Yeah?
No, it's
How about
fine.
this one?
It's
Is this
fine?
one working?
As long as you speak loudly.
All right.
Okay. Yeah, I tend to do that. So.
Good morning, everyone, and welcome to the 32nd SAO Astronomy Summer Program Symposium. We're going to get started on time in about 2 minutes. There are schedules at the back. Feel free to take one. There is coffee and breakfast. Please help us use it up. We've got a really great lineup of students who've worked so hard this summer, even if they have annoying ringtones. Just thank you for coming. I think you'll find the work that they've done impressive. Let's see, I'm just going to stall for another 50 seconds until we start on time.
Perhaps I can bring up my title slide.
Yeah. Why don't we bring up your slide? Sure. That's a good idea.
Nope, that's not it.
Uh-oh.
I knew something was going to go backwards.
You want the...
We had this working last time.
It was working. That's all right. That's all right. We figured this out.
Our IT specialist is on it. There we go.
All right.
Just click resume.
All right, so our first speaker today is Zachary Knutson. And actually, I forgot to bring my list of people, so let me get there. And so Zachary comes to us from the University of Florida and has been working this summer with Aneta Shemganovska. Hi, Aneta. Oh, hi, Aneta. You're in my near field. And he's going to tell us about sharpening the Chandra X-ray view of Sig-A. So take it away, Zach.
Hello, everyone. Good morning. Thank you for the warm introduction. So before we talk about sharpening images from space, let's talk about the actual telescope that we're using. So Chandra. I know a lot of you guys are probably already familiar with this diagram, but for those of you who are not, essentially Chandra needs to use these parabolic and hyperbolic mirrors to sort of coerce X-rays towards the detector. Because if we were to use a regular mirror like an optical telescope does, the X-rays would just be either absorbed or pass right through. Because of that, these mirrors need to be incredibly precisely machined, which they are in Chandra, providing us the highest resolution X-ray telescope, highest spatial resolution X-ray telescope, even though it was launched in 1999. And Chandra primarily looks at 0.5 kiloelectron volts to 7 kiloelectron volts. So Chandra's mirrors are very impressive, but they're not perfect. And what this results in is similar to how if you need glasses, but you don't have glasses, everything is sort of blurred. The telescope also is blurred by this point spread function, which is essentially what the telescope sees from a point source. And so for Chandra, we can model this in two different ways. We can either model it empirically using basically a bunch of stacked faint point sources, or we can parameterize it using a ray tracing simulation called MARCS. Before we talk about sharpening an image, let's talk about how an image goes from suppose a true sky flux image to a blurred image that we receive from our detector. So if this is our true flux image, essentially every pixel is getting blurred by this point spread function. And mathematically, this is called a convolution. So when we convolve our duck with the point spread function, we get this blurry duck. And because this is what the telescope sees. But our detector isn't perfect. And so there are individual pixel exposures that we need to take into account with the exposure map. And this results in our duck with lines in it. And then lastly, because really what we're doing is counting individual photons, we need to introduce significant amounts of Poisson noise. So just counting uncertainty. And so, great, OK. Now we have a really blurry, noisy duck. So what would be awesome is if we could just undo all of those steps to get back to our original duck. But because we added noise, this process isn't exactly trivial. This problem that I posed is called an inverse problem, and in this case, it's called deconvolution. And the most common way to perform deconvolution on noisy data is to do what is called Richardson-Lucy deconvolution. And Richardson-Lucy deconvolution is an iterative method that sort of tries to make a best guess at what the original image looked like, and then convolves that with the point spread function, and tries to optimize how good it fits the counts image that results. But what happens is that it tends to overfit the data. And so you get, if we apply it to this duck, we get this speckly mess. And so there's no clear convergence criterion. Either you run it, if you run it not long enough, you don't get the best fit possible. If you run it too long, you get this decomposition into point sources. So our group has developed a code called a Jolideco, the Joint Likelihood Deconvolution Code, and the biggest thing that we do is adding on to this Richardson-Lucy method is imposing priors. And what priors are is essentially just correlations between nearby pixels. On the right figure, you can see sort of some of the correlations that we add into our data to sort of massage the deconvolution towards more plausible reconstructions. And these correlations are based off of astronomical surveys. So we take a bunch of images and turn them into these patch priors, which are applied to our image. So starting from, how does Jolideco do? So starting from the original image, another common way to look at X-ray data is to just take that counts image and to smooth it a little bit, to sort of smooth over that Poisson noise. And that does OK. You can vaguely make out the shape of the duck. But once we run this through Jolideco, we get something like this, which, in my opinion at least, is a lot nicer. And you can clearly make out more features from the image, such as the eye now being clearly discernible, the shape of the mouth being better modeled, and also this gap between the two fingers is much closer to the original flux image. So great, we have our deconvolution code. But what are we actually applying it to? Well, we are applying it to an active galactic nucleus called Cygnus A. And on the right, we can see that it has been very well observed by Chandra. All of the blue you can see is soft X-ray photons. But this is the entire cluster. But what we're doing is we're zooming in on just this tiny little part in the middle, the nucleus. And if we zoom in and look at it using JWST, we can clearly see now some more features. We can see the central source. We can also see some dust lanes obscuring some of the infrared emission. And you can also see this secondary source, Cygnus A2, which made me really excited because it hasn't been observed in X-rays, or it hasn't been detected in X-rays before. And so without further ado, let's look at our observations. So this is one observation that we have from Chandra of the nucleus. And this is broadband from 0.5 to 7 kiloelectron volts. And this is, when we run it through Jolideco, I sat down I ran it through Jolideco, and here's what we get. With all 18 observations run through Jolideco, we get this, which, unfortunately, there was no Cygnus A2 just sticking out at me. It would have been right about here. But there is some very interesting morphology going on here. Particularly, we can see the point source at the center, but also this extended emission, which reaches out about a kiloparsec away from the nuclear source. But before we get ahead of ourselves and start trying to analyze this, this is a broadband image. This is all of what Chandra can see. But there's actually interesting features in the spectrum. So if we look at a spectrum of Cygnus A collected by NuStar, you can see that they were able to model it using 3 broad components, which are the cold intercluster medium in red, in brown is the hot intercluster medium, and in blue is reflection off of dust from the central AGN. And so what I then did was I made some narrow bands, which roughly tried to concentrate these 3 components. So a soft band from 0.5 to 2 kiloelectron volts, a hard band from 2 to 5 kiloelectron volts, and then a band containing iron K alpha from 5 to 7 kiloelectron volts. And so looking at these narrow band cuts and now running it through Jolideco again, we get this, which shows much more morphology now. We can clearly see in the soft X-rays that there is this clear bicone that extends about 2 kiloparsecs away from the central source. And also, we can still see that extended emission like we saw in the broadband image, but also in the hard X-rays, now it sort of looks like a ring with pockets in it, almost like a supernova remnant. And so, yeah, just taking a second to look at this. So we wanted to also look at how this compares to other observations of Cygnus A. Namely, that JWST image we were looking at before. So this is a 3-color image with JWST represented as Passion alpha represented as red, our soft X-rays in green, and our hard X-rays in blue. And the jet axis, as determined by radio data, is marked with this white dashed line. And what immediately jumps out at me in the short amount of time we had to analyze this data was that the Passion alpha and soft X-ray cones line up essentially perfectly. And also, there's these small pockets in the northeastern cone, right here and right here, where the Passion alpha doesn't exist. It's anti-correlation. So another interesting thing I wanted to share was that looking at just the X-rays, so soft X-rays in green, hard X-rays in blue, if we just kind of flip back and forth, adding in the hard X-rays and removing them, you can sort of start to convince yourself that it almost looks like the hard X-rays and the soft X-rays are also correlated. Like the ring, there's less emission in the ring. So perhaps there's some obscuration that's going on here from the hard X-rays, which contain mostly emission from, or mostly reflection from the central AGN. All right, so just wrapping up here, Jolideco we have successfully resolved additional spatial information from X-ray images of Cygnus A. And so Jolideco can be applied to the many other well-studied objects that exist in the Chandra X-ray catalog. But before we do all of that, we should first look at, I told you, or before what we were looking at was just the Mark's simulated point spread function, the simulated point spread function. But what I didn't say was that both of them are pretty similar. They only have minor differences, but we would like to better classify how the choice of a point spread function model affects the reconstructions. And lastly, because this was only 10 weeks, there are a lot of knobs to turn in Jolideco, and perhaps turning a couple more of those knobs, we could we could get even better reconstructions of our data. I'd like to quickly thank my advisors and all of you guys for waking up early and coming to my talk. Thank you so much. And also, if you have a question that I don't get to answer or would like to reach out, I really do believe in this method. Please reach out to me at my email below. Thank you so much.
Very nice. All right, questions? Question over there.
Yes.
Very nice work. Thanks for showing us.
Thank you.
So the ring you see in the iron line, do you have an idea of what's the physical size of the ring, and does it tell you something about sort of the size of the accretion system or something about that?
So, so just based off of the scale bar on this image, it's roughly a kiloparsec away from the central source. And because this is reflection off of, contains a lot of reflection, it's not entirely just reflection, contains a lot of reflection, what this tells us is essentially where some of the dust is. And so this could, with further analysis, tell us a little bit more about the dynamics going on at these like 500 parsec scales.
Julia, and then...
So I was going to ask the same question, but for these soft X-ray emission that you see, how far away, like up until when you see it compared to the location of the AGN? Like how far away does it extend?
Yeah, so we have clear detection out to about 2 kiloparsecs. It seems to sort of fade off after that. If other observations are to be followed, this is the wind, a wind from the AGN, and so perhaps this is telling us the extent of the wind, where the fast-moving wind is interacting with the slower-moving intercluster medium and is creating these X-rays.
So I have a question about your patch priors. Could you go back to the slide of the patch priors?
Sure.
Okay, so I'm contractually obligated to relate everything to the sun. So if you were going to use this method on the sun, which, instead of using a bunch of star observations of a bunch of different stars, could you imagine making up these patch priors, many observations of the same object, the same extended object, i.e. the sun? Like,
yeah, so
would this work the same way, or?
Yes, exactly. In principle, these patch priors can be trained off of, or created off of any astronomical data set you wish, as long as there's enough data, which is, on the order of maybe a couple hundred images or so.
Not a problem for the sun.
Yeah.
Presumably you get more flaring ones and less flaring ones.
Yeah,
and that gives it a
we've
basis.
got, we've got a solar cycle's worth of SDO data taking data every 12 seconds. So
yeah, you just need to give to create the patch priors, you just need examples of how pixels are correlated in the images you're looking at.
Did you have one, Chris?
I was just going to ask if you could elaborate more on the significance of the extent of the Paschen alpha detection, the alignment with the soft X-rays, but also on the, you really see that correlation on one side and not the other?
Oh, yes. So what I hadn't mentioned is that the wind is aligned towards us in the southwestern cone. So this wind is traveling roughly or somewhat towards us, while this wind is traveling somewhat away from us. This cone, that's why you see stronger emission in the soft X-rays in this cone. But yeah, so we didn't have very long. There's a lot of lines that we could also look at. That's definitely something I'd like to look into in the future, is are there more correlations with different emission lines? Or how is this correlation structure different? Sorry, hopefully that answers your question. I can also talk to you after the talk.
No, that's great. Can I ask one more question?
Yeah, go. One more, and then go.
Did you think about looking at the dust or the possibility of detecting the dust at this resolution or this sensitivity?
Yeah, so I guess the idea is we can't get perfect separation just because like the spectrum sort of overlaps, right? So there isn't a clear band that would only show us the AGN reflection. But we can sort of concentrate it, which is what we're looking at here. And so this should be probing more of the dust in this. And then this is more hot intercluster medium.
All right. Did you have one last one?
A minor one about if there was another source that you could look at, what source would it be?
I see.
If you know any.
Off the top of my head, I mean, well, there's a lot of different sources that we can look at.
Yeah.
Honestly, I think it's really cool that you mentioned the sun. That's something I hadn't considered before, but yeah, there's a lot of so much X-ray data available for it. And it works with any telescope. You don't even need observations necessarily from the same telescope. You can combine observations from different instruments together. So there's really a lot we can do, a lot of different things we can look at. But off the top of my head, I can't pick just one to look at next, I think. All right.
All right, I think we better move on. Thanks, Zach again. Our next speaker, let's get Sally set up.
So you organized. Yeah, please help. I got it.
So our second speaker today is Tally Vaneman from Yale University. And Tally's been working this summer with Kirsten Hall and on AGN and feedback and SMA and Chandra and all kinds of things.
This time. Are you just working for Zach?
There's going to be no tech problems today. We have it all sorted
Why is
out.
it going reverse now? It's going to work right now. Oh. There we go. All right.
And I'll just mention, do help yourself to more breakfast and more coffee during the presentations. So, Tally, take it away.
All right, thank you everyone so much for being here. Thank you for the lovely introduction. Like Jonathan said, I worked with Dr. Kirsten Hall and also Dr. Sarah Biddle and Nia Freeman to sort of search for feedback signatures through multi-wavelength analysis of 2 obscured AGN. So given that it is very early in the morning, I thought I'd start with a warm-up and just sort of go over again what an active galactic nucleus is. Thank you again to Zach for sort of leading me in here. An active galactic nucleus is a supermassive black hole at the center of a galaxy that is actively eating a lot of material, and this accretion is causing it to emit over all wavelengths. These objects have many different names depending on the angle that we're looking at them and the presence of radio jets, such as blazar, quasar, radio galaxy. And today I will specifically be looking at this kind, the Seyfert galaxy, sort of seen from a low angle. They can have radio jets, but more often they don't. And in particular, mine are obscured, which means that there is a fair amount of dust and gas surrounding the nucleus of these AGN, which makes it harder to see the AGN and the light emitting from the AGN itself, but it makes it a lot easier to see what we're getting at here, which is the gas and dust itself. Given that these objects are giving off so much radiation and other powerful forms of emission, it's pretty easy to assume that they have some sort of impact on the galaxies that they live within. We know from many previous studies that there is a correlation between the black hole mass and the velocity dispersion of the stars within the galaxies. We know that there is a correlation between the black hole mass and the bulge mass of the stars within the galaxy. And we know that there is a very tight correlation between the black hole mass and the bulge luminosity of the stars within the galaxy. So there's definitely something going on with the coevolution of these objects. And then furthermore, when we look at this number density function of luminosity of galaxies across cosmic time within the universe, we see both that there are fewer very luminous galaxies than we might otherwise expect, and fewer less luminous galaxies than we might otherwise expect based on a CDM cosmology. And this indicates that there is some sort of mechanism by which the luminosity of galaxies across cosmic time is being regulated, not too bright, not too dim. The current favored theory is that this is partially or mostly caused by the AGN within the galaxy. There's a couple different ways in which AGN can impact their galaxies, depending on the presence of radio jets, depending on the gas and the way the AGN is moving the gas around. And in particular, I'm going to be looking at only a couple of them. So we don't need to worry about the radio jets part. I'm working with safer galaxies, and my safer galaxies do not have radio jets. And then the difference between these things over here is whether any given outflow is created by a plasma or just shocks. I'm not particularly looking at that, so we don't have to worry about that either. And that leaves us with sort of these four concepts. The first of which is negative feedback, in which the AGN either ejects all of the gas out of the galaxy, all of this cold molecular gas that is necessary to create star formation, therefore halting star formation, or at least slowing it down a bit, and preventative feedback over here, which is another form of negative feedback, in which the cold molecular gas just sort of gets heated up either to the point where it's not cold or to the point where it's not even molecular anymore, in which case, again, no stars. Now, another interesting concept is sometimes the AGN can simply tussle the gas around, and this actually leads to some positive feedback in which more stars are created in the wake of this outflow, which is something that we could have looked at in these galaxies. However, 10 weeks is a very short time, so we chose to focus mostly on the negative feedback, leading to sort of these central ideas. Gas is being moved, gas is being heated maybe, and this has perhaps some effect on the creation of stars within the galaxies. So what would this look like? In this very interesting example from a paper by Fruglio et al. In 2020, we see a nearby obscured Seyfert galaxy similar to the ones that I'm going to be looking at, slightly closer. And in the blue here, we have X-rays, so very hot something that is coming from the AGN. In the green, we have the continuum, which is the cold dust. In the yellow, we have hydrogen-2, which is the warm molecular gas. And then in the purple, we have specifically the carbon monoxide 2-to-1 transition, which is one of our biggest tracers for cold molecular gas within galaxies. And the really interesting thing is, in this bottom corner here, we're looking at the hardness ratio of the X-rays, which isn't really important to understand what's going on here. What we notice is that where the X-rays are, the cold molecular gas isn't. And this isn't necessarily something that we expected to see, and is a very clear indication of feedback going on within this galaxy in a way that we didn't necessarily expect to see it manifested. So my project was to look at other similar galaxies and see if we can find this phenomenon as well in those galaxies to better understand what feedback might look like in these Seyferts. So today I will be looking at these two sources. They are both relatively nearby, heavily dust-obscured Seyfert galaxies, NGC 1125 and IC 1657. They were selected because they have publicly available Chandra data that in previous analyses has been found to have extended emission of some sort. And we are going to be combining this X-ray data with new submillimeter array observations to get a better understanding of what the gas looks like within these galaxies and how it might be interacting with the AGN. The first step in this process is to do a lot of data processing with the millimeter data. Like I said, it's from the submillimeter array shown here in Hawaii. And we looked for both the continuum, so the cold dust, and the carbon monoxide 2-to-1 transition as a tracer of the molecular gas. Here's an example of NGC 1125's continuum that we found. It is very centralized due to the setup of our observations. And we actually didn't see much dust within IC 1657, which is, again, probably more an artifact of the observations themselves. So for the rest of this talk, I'll be focusing on the molecular gas rather than the dust. What does the molecular gas look like, you might then be asking? So I'm going to present 3 moment maps for my 2 galaxies that help us get a better understanding of what the gas looks like. The first of which is integrated intensity. This is sort of where the gas is emitting pretty strongly. We see, first of all, that there is certainly extended emission. This is not even all of the gas, probably. This is just what we see based on our observations. And we see that it is very clumpy. All of the X's that you're going to see in the centers of these plots are the peak of the hard X-ray within these galaxies, which we take to be the center of the AGN. And we see that none of these clumps are co-located with the center of the AGN, which is pretty interesting. Additionally, we see this main axis here, which is co-located with the galaxy at large, but we also see this tiny little perpendicular axis thing going on, which is also pretty interesting. Then we look at the moment 1 map, which shows the velocity of the gas within these galaxies, and where we might otherwise expect a more or less ovular shape with white in the middle indicating the center of rotation and then turning to blue and red on the sides, we instead see within this oblong shape that the white center of rotation is instead shifted downward from the center of the AGN, with a lot more of the gas being blue shifted than red shifted at large. And then we look at the velocity dispersion of the gas within this galaxy, and we can see that it sort of is similar to the clumpy nature of the integrated intensity. All of these contours are taken from the integrated intensity plot to sort of compare where the gas is. And we see that there is these clumps here, and then also high dispersion within this perpendicular region and this other lump up here, which indicates disrupted kinematics of the gas within this galaxy. And if instead of looking at the spatial region, but rather the spectral dimension, we can see that rather than being a Gaussian like we might otherwise expect for simply rotating gas, we have this giant blue shifted peak over here, which we have taken to be some sort of outflow of gas from the center of this AGN, indeed indicating disrupted kinematics. Something interesting is going on with this gas. Similarly for NCG 1125, when we look at the integrated intensity, we see that it is a lot more centrally located at large, but this center is again offset from the center of the AGN itself. And we also see this additional region off to the right here, which is not as intense as the main area of the gas, but still definitely noticeable, and there is in fact gas there. And then when we look at the velocity, we see that the velocity center is again offset from the center of the AGN, and the wings are blue shifted and red shifted, with the wing that has a little bit more gas intensity being only kind of lightly red shifted. And then if we look at the velocity dispersion, we see that there is a lot of velocity dispersion going on in this additional section over here, indicating significantly disrupted gas kinematics within this galaxy. And then if we look at the line profile of this galaxy, we see that it does look a lot more like a Gaussian, but again, it is not as simple or smooth a Gaussian as we might otherwise get from a simply rotating gas. It's not fit perfectly. It's got all of these additional peaks and troughs indicating disrupted gas kinematics. Now, to get a full picture of these galaxies, we also want to look at the X-ray data taken from Chandra. Thank you for the introduction to Chandra, Zach. Specifically with PI Elvis, who works here. And we binned it into 4 bands, pretty similarly to what Zach did, with slightly different numbers: full, soft, hard, and iron K alpha to indicate sort of where the AGN itself is emitting from. And then we did some smoothing to make it look nice. Once we'd done all this, we overlaid all of our millimeter data on top of the X-ray data. And we can see that for IC1657, even though it was taken in a snapshot survey, there are definitely still interesting features going on in this galaxy, especially in the soft and iron K alpha bands. As you can see, there's this extended feature to the iron K alpha band that is more or less coaxial with this perpendicular feature in the molecular gas. And then in the soft band, although the soft band does not contribute as many counts to the full observation, just sort of given the full band observation, you can see this other extended feature that is neither coaxial with the plane of the galaxy nor this little perpendicular thing. So that's interesting. And then if we look at NCG 1125, there's definitely a lot of interesting things going on with the X-ray in this galaxy, specifically that there are 2 clumps of X-ray emission external to the central nuclear region of this galaxy. There have been a handful of speculations thrown around through other research as to what these clumps might be. They might be starbursting areas, they might be high-mass X-ray binaries, they might be an ionization cone of some sort. We're not really sure, but what we do see is that they are not co-spatial with the molecular gas, but neither do we see the definitive anti-correlation that we might otherwise expect to see based on the Ferruglio paper from several slides previous. So, you know, we're not entirely certain if this is feedback causing shifting of the molecular gas based on this specific combination of observations, but there's definitely something interesting going on here. And then just to get a slightly fuller picture of NCG 1125, we were lucky enough that this galaxy had some previously taken Hubble data, and so we decided to overlay everything, and we can see that everything is pretty much located in the center of the galaxy, with nothing else being quite perfectly aligned with the plane of the galaxy. The X-ray sort of extends below the plane of the galaxy, but it might still be within, hard to say. And then this other region over here seems to be located within the back portion of the galaxy, but that then doesn't explain why we don't see it in the front portion of the galaxy also. So in conclusion, did we find the smoking gun confirmation of AGN feedback that we might have hoped to see in these 2 galaxies? Not exactly, but we did find some really interesting disturbed CO gas kinematics near the AGN, as well as interesting placement of this emission and the relationship that it has with the X-ray emission, which is neither correlation nor quite anti-correlation. Mostly, we have a lot of future steps of other things that we would like to do with these galaxies in this particular research, including disk modeling of these galaxies to better understand the ways that they deviate from what we might expect, calculating star formation rate density to see what effects this disturbed kinematics of the gas has on the star formation rate within these galaxies, and placing our sources in context with other galaxies, both in literature and other sources that we have not even yet performed this analysis on, but we have all of the data necessary to get a broader range of results and understanding of these kinds of galaxies. I would like to acknowledge all of these lovely people and all of this lovely funding that made my summer possible. And I will now take questions.
Thank you, Callie. Question from the front here.
So, awesome talk, Callie. I was wondering if you could go back to like the moment plots a little bit. Yeah. So I was wondering, you had mentioned that like the X is like the peak of the hard X-ray. I'm just wondering like how exactly you went about plotting that on this if it isn't lining up with the center of the agent.
Yeah, so when we processed the X-ray data and loaded it up into Matplotlib, it was pretty easy to just ask Matplotlib, hey, where is the peak of the X-ray? Which pixel has the brightest value in specifically the hard X-ray plot that we had? And then we converted that pixel location into coordinates and then used the same world coordinate system as everything else that we plotted to overlay that on top of our plots. Thank you.
Questions? Adele.
Yeah, so I have a comment on this. What is the offset between these 2 points? Your location of the center, hard X space, and the center of the molecular gas?
So for this galaxy, it seems to be about 1 arc second, maybe a little bit less. So it could be within error.
Okay.
But it's also enough that it definitely seemed an interesting thing to mention.
Yeah, because there are known misalignments, astrometric solutions which are different for Chandra and different telescopes. So it's good to look at. Yeah,
Thank you.
Thank you. No, the talk is very nice. The results are very good.
Questions?
I was wondering if you could explain what a moment map is.
So a moment map is basically what happens when you take the spectral cube, which is the closest thing we have to raw data from this. So you've got a spatial dimension, an intensity dimension, and then a spectral dimension. And then we squish all of those dimensions down onto one plot to look at either only the integrated intensity, only the velocity, or only the velocity dispersion across the spatial dimensions.
So it's basically like raw average standard deviation. Is that?
It's like you integrate it once, then you integrate it another time with another thing, and then you integrate it another time with another thing.
Yes.
Thank you, Callie. So there's increased velocity dispersion close to the AGN that you could maybe relate to the presence of the central engine. Do you have a theory as to why that other clump over there has an increased velocity dispersion? Could there be another massive object there, or what do you think would be creating that increased velocity dispersion in the secondary clump?
I guess it could be possible if there's another object. I think one of our main theories right now has been that it is an outflow of gas, similar to what we see in IC 1657, just sort of the AGN doing a lot of jostling of gas around, and that might be what's causing the velocity dispersion.
One last question, if anyone has one? Yeah, there.
Hi, Tali. Amazing talk, and I just had a question about the velocity dispersion again. So I think you mentioned it's like in your conclusions a little bit, but what do you think the disruption of the kinematics mean for star formation rates in this galaxy, or like I guess most galaxies, because they both have this like kinematic disruption, right?
Yeah. So going back to the theories of feedback that we have, sort of there are two main effects that it could have on the star formation in these galaxies. And additionally, these are effects that we might not even see immediately. It could either cause the gas to not create stars, sort of disrupting it to the point that it is no longer able to have that good gravitational hold to compress into stars, whether that's because it just can't, whether because the gas is not cold or because it's not molecular anymore, or the jostling could increase the rate of star formation such that it accidentally like sweeps gas into the formation of stars. I believe both of those are probably things we've observed in galaxies in the past. So one of the most like near future steps that we have for these galaxies is to look at the star formation rate and try and get a better idea of what this jostling of gas is actually doing within this galaxy.
Awesome. Thank you so much.
Thank you.
It's like in the pocket. Sort of on the top of the phone.
Yeah, I got you.
Thank you, Andy.
Don't worry about it.
It's probably not going to work again. So the skill set of a scientist is being able to change the presentation.
Yes.
All right, so our third speaker today is Caroline Erickson from Butler University, who's been working with Pivot Triani, and she's going to be telling us about the mystery of helium-2, lambda 4685. So it's a whodunit, I guess.
Yeah, pretty much.
Yeah. So take it away, Caroline.
Thank you very much. Like Jonathan said, my name is Caroline Erickson, and I've had the pleasure of working with Pivot Triani this entire summer on the mystery of helium-2 4685 and X-ray galaxies. So what is helium-2 4685? Well, it's a nebular emission line that has an ionizing potential of 54.4 electron volts, meaning that for helium-2 to exist, a photon moving at ridiculously fast, with a ridiculously high energy of 54.4 has to ionize singly ionized helium. And what we want to know is what is the ionization mechanism producing these very energetic photons that then produce helium-2. Well, this is actually a more challenging question than we thought because we see it in a very, very broad range of galaxies. We see it in AGN, or active galactic nuclei, which at first can be very almost self-explanatory because AGN commonly produce highly energetic photons. However, we also see this helium-2 in star-forming galaxies that have no detected AGN features. So the question remains, what produces helium-2 in these star-forming galaxies? We start off by looking at their stellar populations, but right off the bat, they simply do not have enough, they don't create energetic photons that are capable of producing helium-2, except for one type of star, which is the Wolf-Rayet star, which is a supermassive star at the later stages of its life, and it has very active winds and a lot of mass loss that produces photons with sufficient energy. And we also see it in its spectrum. However, Wolf-Rayet populations are really rare in low metallicity galaxies, and so they simply cannot explain the helium-2 we observe in low metallicity galaxies. Furthermore, there are several instances when we observe helium-2, but no Wolf-Rayet features. So that leads us to the X-ray binary and the X-ray emission question, because they also have sufficient energy to ionize singly ionized helium. X-ray binaries are a compact object with a companion star, and we see that often in the sources that have helium-2, there is an elevated helium-2 ratio with the X-ray emission. We also see a very similar trend in the luminosity, the X-ray luminosity versus metallicity, and the helium-2 luminosity versus metallicity. However, these trends are not reproduced at higher redshift galaxy populations. So the question still remains, what produces helium-2? This is where my project takes off because thus far, we've primarily considered individual types of sources, either X-ray binaries or stellar populations. But what if we consider X-ray emission in general? So the goals of my project were to figure out trying to answer some questions about what is the primary ionizing mechanism producing helium-2. And in order to do this and see if it is X-ray emission, we need to investigate into the properties of these helium-2 emitting galaxies. And, well, how do you do this? The answer is emission line diagnostics and emission line ratios. First, I got to cover our galaxy sample. We want galaxies that both have X-ray data and optical line fluxes. So we use a different paper's catalog of galaxies that have XMEM Newton data and also exist in SDSS, Sloan Digital Sky Survey. And then we update that Sloan Digital Sky Survey data with a newer data release and select the certain lines of fluxes that we want. And with a couple of signal-to-noise ratio cuts, we would get out 73 helium-2 emitting galaxies that also have X-ray data. So back on the fun stuff, I mentioned that we have to have, or we want, optical emission line fluxes, and that's because these ratios in these lines provide insight into the galaxy's properties. They tell a story of the galaxy. One of the first stories that we use, one of the first diagnostics that we use, is called the BPT diagram, or the Baldwin-Phillips-Telrovich, which is a method of classification based on the ionizing mechanism dominant in each one of these galaxies. So here we have the total sample of all the X-ray galaxies from the original paper plotted, and our helium-2 sample are the three-pronged galaxies that we can see up here. One of the reasons that this diagram works is because on the y-axis we have the O3 over H beta line, which tells us a lot about the strength of the ionization within the galaxies. And then on the x-axis, we have the N2 over H alpha, which is a probe into the metallicity of the galaxies. With this classification system, we find 62 AGN, 3 composite galaxies, and 8 star-forming galaxies. One of the first properties that we want to look at is the ionization parameter. So we have the same metallicity probe on the x-axis, And on the y-axis, we have the O3/O1 ion ratio, which is a proxy for the ionization parameter. Now we can see here that our helium-2 emitting samples, specifically in the AGN, cluster at higher ratios of this ionization parameter, which indicates that the nebular gas surrounding these sources and surrounding these sources has a very strong ionizing field, which means that there's a lot more energetic photons in this area. This makes sense because helium-2 requires strong energetic photons to ionize the singly ionized helium. We then took a look at a couple of X-ray properties, including the X-ray luminosity versus the helium-2 luminosity. Here we see a beautiful linear trend. As the X-ray luminosity increases, so does the luminosity of the helium-2. We also notice that there's a separation between the star-forming galaxies and the AGN galaxies. Fitting a line to this data, we confirm this tight correlation between the two for the total sample of galaxies. So the black dashed dotted line is accounting both for the star-forming galaxies and the AGN. We can compare another paper published in 2025 by Korompatzakis, did a very, very similar relation and fit, and they also found a similar trend. There are slopes for the total sample aligned within about 2 sigma of each other. This isn't quite the same for the star-forming galaxies or the AGN individually, but that's because we have a smaller sample size. They have about 164 galaxies, while we have 73. Specifically, they have more star-forming galaxies, and so they have them at lower luminosities, while we have a smaller X-ray luminosity range versus we have a pretty wide helium-2 luminosity range, specifically for the star-forming galaxies. So yeah, this pretty much just strengthens our argument that X-ray emission is correlated to the luminosity, to the helium-2 production. Well, we can take this investigation one step further by looking at the ratio of the helium-2 luminosity over the X-ray luminosity. And this tells us how much helium-2 is being produced per X-ray. We find something very interesting in that the lower luminosity galaxies have a higher ratio and therefore are more efficient at producing this helium-2. Now get ready, because we can take this one step further. However, it takes a little bit of background context. So what we're going to do is add another X-ray property to this graph. So keep all of this graph, this layout in mind as I tell you about the hardness ratio. The hardness ratio is pretty much equivalent to the color in optical. And so it works as you have a ratio, and on the numerator you have the count of photons in a harder energy band minus the count of photons in the softer energy band. My data specifically looked at 5 different sections, and so we have 4 different hardness ratios that compare these sections that we look at. So as we then plot these ratios put out a color, and when the color is closer to blue or more blue, it means it's a softer source and has more soft photons, more photons in the soft band. And while the other side is if it's positive, like 1, it's going to have harder photons, more harder photons. So we take a look at this in steps. We have HR1 up there, and we can clearly see that there are that overall there's a general trend that these sources are harder. Specifically though, I want to point out that the star-forming galaxies have are highest have a higher hardness ratio, and therefore they have more photons in the 0.5 to 1 keV energy band. As we look at the HR2 and HR3 diagrams, we see a trend. We see a trend that as we increase the X-ray luminosity, the hardness ratio also increases. But that comes with a decreasing ratio. Main point that we see here is that the star-forming galaxies are the softest sources in both HR2 and HR3, meaning that they dominate in the soft X-ray band and are more efficient at producing helium-2. HR4, we don't really pay much attention to because XMM Newton data focused on the softer energy bands, and so we pretty much think that there's not many photons to be able to make a correlation here, as we can see. So yeah, returning back to those soft X-rays, we see comparing our sample to our total Pulitova sample, our total non-helium-2 emitting sample, we see that in HR1, again, our helium-2 sources are softer. So what this means is we need to be paying attention to the softer band of X-rays. But thus far, we've looked at this entire range of X-ray, but this is missing a very small but mighty section of the X-ray energy range, which is the super soft energy range. Sources that emit between 10 to 100 electron volts are considered, this energy range, are considered super soft X-ray sources. This is also the energy range that happens to completely overlap with the ionizing potential of helium-2. However, the contribution to the helium-2 production from super soft X-ray sources hasn't been extensively researched for several different reasons, including one, that it's pretty difficult to see super soft X-ray sources as they're often absorbed before they reach our X-ray instruments. So we have a lack of detections. Another interesting thing is that they are also not defined by a physical nature because we can't see them as well. So our future work that we want to focus on is being able to look at more galaxy properties, like maybe the equivalent width of a couple of lines, as well as we want to see how our results apply to higher redshifts and continue the work of what the contribution is, the contribution of super soft X-ray sources to helium-2 emission. We've started this work with theoretical models from Triani 2024, but now we want to add observational data. Furthermore, this is kind of difficult, as I mentioned, because the super soft X-ray sources are often absorbed, and the higher redshift sources are often shifted out of the wavelength frequency of our X-ray telescopes, so we don't have as much X-ray data on them. So in summary, we want to know what the ionization mechanism producing helium-2 has remained elusive. It's not stellar populations like Wolf-Rayette's, and it's not X-ray binaries alone. However, considering the total integrated X-ray emission from these sources, we can then learn, we want to learn what the properties of these X-ray galaxies are to connect the two. And our results show that there's a strong evidence that X-ray emission is the primary mechanism for producing helium-2 in these galaxies, and that star-forming galaxies are softer and more efficient at producing this helium-2, which is really interesting. So yeah, thank you guys for coming to my talk, and I'd like to acknowledge Dr. Pippa Triani and Pation, and of course the SAO AstroREU program and the Kinley Research Group. Questions?
Caroline, questions? Yeah, Tally.
In your early diagrams where you categorize everything on AGN star forming, you've got the triangles that are normal galaxies and the three prongs, and then you've got the X.
Yeah,
Who's
yeah.
that?
So that is really cool. Up here, this galaxy was originally classified as an AGN. However, when we were looking at these, so all the galaxies over here, they're super low metallicity, and those are really interesting to us. So we took a look closer at their spectrums, and one of the reasons, and while looking at these, and also we had a hypothesis, is we found that the spectrum of that specific galaxy is way more similar to a star-forming galaxy compared to an AGN, simply based on its a couple of factors, one of them being the equivalent width, the broadening of the lines, and that, and it had ridiculously high O3. That was the main thing. I'm talking like its flux was like 12,000. It was crazy. It was really interesting, but yeah. Ergs per second. Ergs. No, it was angstrom. Ergs per second. It was flux. It was flux. I have. Wait, hold on.
Okay, never mind. That was a meeting.
No. I can answer it. We just gotta. Ergs per second per angstrom. That's not it.
Because it's the integrated line flux, right?
Yes. Yeah.
Question over there.
Could you remind me, you said that when you look at higher redshifts, there's less helium-2? Or?
Not less helium-2. There is helium-2. And we don't know, we don't have, what we want to know is what's producing it. And we are still figuring out ways in which we can either infer X-ray properties about the higher redshift galaxies, or we can somehow get data from these higher redshift galaxies, which is obviously difficult. But no individual source has been able to account for higher redshift galaxies, helium-2, and lower redshift galaxies. So helium-2 exists everywhere in the range of redshift, metallicity, classification type, and no source individually has been able to explain it so far.
But I think you said that the ratio of helium-2 luminosity to X-ray luminosity was lower at the high redshift galaxies. Is that
Metallicity.
metallicity?
So it was what the paper said is that the ratios that we found, the trends between the helium-2 luminosity versus the metallicity and the X-ray luminosity versus the metallicity didn't show up in the higher redshift galaxies. Not showing that there's like less of one, it's that these trends that we said, oh, it could be high mass X-ray binaries for this, it can't be, it didn't show up for the high redshift galaxies. Yeah.
So thank you for a very well-motivated and engaging talk. Enjoyed it very much. I had a question that relates to this plot, actually.
Mm-hmm.
I was wondering, since you compared to Kurum-Patzakis, if you had thought about, since you have small number statistics when you're comparing to those trends, have you thought about constructing the other two BPT diagrams that are based on the sulfur and oxygen lines that are shown here?
Yes.
To make those trends?
Yes, we did make those, and I probably should have put them in there. They are connected to this classification. This is a 3-part plot, and we do see those other two. And the main takeaway from our other two sections of the BPT is that all of our AGN, other than one, are C-FER galaxies. So we were really focused, really high, they're higher energy compared to the other section, for those who don't know, the one that's below the line and the other two plots that you can't see here are liners, which are low ionization, narrow emission regions. So yeah, that's what we looked at. Yeah, does that answer your question?
So what I was wondering is you only have a few star formation dominated objects and even fewer composites.
Yes.
And so I was wondering if those IDs are confirmed in the other diagrams.
Yes, they are.
Okay.
Yeah.
Thank you.
Yeah.
Time for one or two more questions. Yeah.
So actually, similar about the 2025 paper, I was wondering, you mentioned that you explained very well what your data sources were and why your trends were different because of your data sources. So I was wondering if you could just say more, like, if you know what the difference between your, sources you were using versus them.
Yeah. So the Kurum-Patzakis paper started with a sample of galaxies that emit in helium-2, and then cross-matched that one with, first off, the Chandra catalog, and so then they found their sources. We started with X-ray selected sources, and then used SDSS to see if we could find the X-ray sources that those galaxies that have well-detected helium-2. So they started with just helium-2 and found X-rays, defined both. We started with X-rays, found helium-2, and got our sample size. And they did the Chandra. So yeah.
One last question.
Hi, thanks for the great talk. I don't do X-rays, so maybe this is a very basic question, but your conclusion seemed to be that you get more helium-2 from softer hardness ratios, i.e. lower energies. That seems to be counterintuitive to me because, as you mentioned, you need really high energies to ionize He2. So why is the softness ratio lower than when you're making more of these?
Yeah, so great question. I've been throughout the project also been wondering like a pretty similar question, asking myself a similar thing. But what we kind of concluded is that it's something we need to look more into, and maybe the peak, the majority of photons that are being produced are higher than the ionizing potential. So I feel like that is shown well by this. So like the source that we looked at through here primarily emit in this range, but we haven't looked much to it is the source that emit right over the ionizing potential. So maybe there's a correlation between they just have more soft ionizing photons instead of like the super hard ones. Maybe they kind of miss, the exact ionizing potential. So yeah.
I think it's true, right, that the ionizing probability is sort of goes like above the potential, it drops off with bigger E. But it's also true that for the same luminosity, you have, in soft versus hard, you have more photons.
Yeah.
Right, so maybe all that matters is you're above that potential by like a fraction of an EV. And then if you have more of those photons, you're golden, even if the total luminosity is less. All right, thank you very much. Let's thank We're only a couple minutes behind. We have one more talk before the coffee break. Right, so our next talk, you ready to go, right? Yeah. We'll get to that.
I think so.
Is that right? Our next talk is by Allison Snyder from Holyoke. And Allison's been working with program alum Kaylee Brower on finding out where is all the gold. If it's been disappearing from our stock market portfolio lately, find out where it's going to. All right, Allison.
All right, so yes, my project is Where's All the Gold, essentially, and I am this summer I was working with Dr. Kaylee Brower to create an analytical model of sort of how neutron star mergers are creating our process and how that's enriching sort of galaxies. So first of all, what is our process? So our process is the nuclear reactions that essentially create all the gold, the platinum, europium, uranium, all the like very heavy elements that we see up on this side. And obviously on Earth, that's pretty important to our daily lives. So we want to know how these are created. But this process requires very dense neutron environments, lots of energy. It's really rare. That kind of environment is really rare. But we have observed it in the neutron star merger GW170817. So we know that neutron star mergers are one of the few sources that can produce the R process. It is also theorized to occur in collapsars. Collapsars are essentially very, very massive stars that essentially die, form a black hole, and have the accretion disk. And in that accretion disk, we theorize that it can also occur. However, since we have only observed it in the star process in neutron star mergers, that will be the focus of what I'm working on. So let's go over to your sites again. So neutron star mergers, we have observations. Yay, that's always good in astronomy. These take a long time. You have your neutron stars. It takes a while for them to both die, and then they spiral around for a very long time before they actually merge. And these can also occur outside of star-forming regions. And so let's see, our other process, core collapse supernova, specifically collapsed stars. Our process is only theorized. We have tried to observe these, but so far we have not actually observed our process in these events. It's a faster time scale because the star just needs to live, die, our process produce, theoretically. And because this is a faster time scale, it also occurs in star-forming regions. So let's go over, there are a few problems with the neutron star merger model. So first, they take a long time to merge. This means we observe them happening in quiescent galaxies, galaxies where the star forming has essentially stopped, which means essentially if there's no more star formation in this galaxy, that our process that is produced is not actually ending up in stars, protostars, or a planet. However, we have observed the R process in old galaxies, essentially meaning well, we have observed it in the stars of old galaxies, essentially meaning, oh, there must have been a neutron star merger or something producing our process very early on. We aren't certain if a neutron star merger is fast enough for that. Second, neutron star binaries can get ejected out of the host galaxy. This diagram essentially is showing sort of where neutron star kilonova have been detected relative to their host. Because of the essentially supernova that produces each neutron star, those can be asymmetric, and essentially that explosion, sort of like a rocket, ejects the entire system outside of the host. Essentially, then when you have your supernova, your kilonova here, it's not actually within, essentially, going to end up in the star-forming regions of your galaxy. And finally, we have a lot of uncertainties in like how much yield, how many of these actual neutron star binary systems we have, and it's especially with only one very well observed observation, it's lacking a lot of detail. So my project goal is to determine whether neutron star mergers can account for the R process material we haven't observed across a number of different galaxy sort of simulations. So essentially if you want to track the history of like how neutron stars mergers might have enriched the history of galaxies, we have to look sort of at different histories of how galaxies have evolved over time. So first I was looking at, so I need that mass history essentially. So we do not only, unfortunately, so this is where we turn to simulations. So the first I used is the Caterpillar project, which has really high resolution of dark matter halos the galaxy over time. And then essentially from those mass histories, I was taking the median sort of a few different ones. And then from those mass histories, I went to essentially a universe machine, which gives me the star formation rates of a given galaxy at a given time. And essentially that allowed me to reconstruct how different galaxies would behave over time. So I went through a few different galaxies. So we're going to focus on these two first. So first I modeled a Milky Way one. Because the Milky Way is our galaxy, we want to do something that's familiar to us. So essentially these are sort of time and mass going up to 10 to the 12 solar masses. Then a sort of mid-sized dwarf of a sort of perhaps more, I don't know, a random typical dwarf galaxy. And for both of these, I sort of tried to capture a median one that was of the behavior of mass over time. And then I also wanted to look at a very tiny dwarf. However, as I mentioned before, or universe machine cannot actually predict the star formation rates of very small galaxies, such as this ultra-faint dwarf Reticulum-2. But Reticulum-2 is known to have 78% of its stars have R process enrichment. So it is a key point to study and say, can we actually account for the R process produced in this specific galaxy? So essentially, I turned to Simon et al. 2023, which has a reconstructed star formation history over time. And essentially, for that one, I have used this data instead of the universe machine. So let's go over a few model parameters. So first, our ratio of neutron star mergers is one binary neutron star system per 7 times 10 to the 4th solar masses. This is a rough estimate based off of kilonova and core collapse supernova ratios. Time scales, I have taken this from Michael Zevin's paper, 2022, of a delay time distribution as plotted here. We have a minimum delay time. Remember, delay time is from when the stars are born to the stars, neutron stars, and then they're spiraling into collapse. We're saying the minimum time is about 200 million years, and then follows the power law. We also have a yield per neutron star merger of about 0.03 solar masses, and then our galaxy retention rate is plotted here. So at a very small halo mass, essentially 10 to the 8th solar masses or lower, you're probably retaining like 1%-ish. And then we sort of go up until you get to about a Milky Way mass galaxy. We're saying you're probably retaining all the R process. Essentially, this is a function of how much of you have your system ejected from that supernova asymmetry, is the galaxy mass actually enough to retain it or not? So let's go over the Milky Way model first. And we have time on the bottom. Black, we have our star formation rates taken from universe machine for the given mass. And then we have our neutron star mergers. As you would expect, they are offset, but you still see that the neutron star mergers are occurring throughout the time when we have star formation in the Milky Way model. And then if we look over here, in green and blue, we have both the green is the R process that would be retained by the galaxy. Blue is the R process that would be actually produced. And we're seeing that almost all the R process is maintained within the galaxy. So essentially for the Milky Way model, yes, we can say both timescale-wise, R process is occurring during the entire period of star formation. Stars are going to get, young protostars are going to get enriched. And we are maintaining that R process within the galaxy. Now when we go to the mid-sized dwarf model, we're seeing there's a lot more noise on how many neutron star mergers occur at any given time. But we are still seeing neutron star mergers are happening throughout the star formation history. But when we look over here to how much is retained versus produced, we are losing significantly more of the R process. But there's still enough to maintain within the galaxy to say, yes, we're probably going to see R process enrichment of stars. However, when we look at Reticulum-2, I did about 10,000 sample runs of this one just because we only had a single star formation rate. And so when I did that, I got 6.6% produced a binary neutron star system, a neutron star merger. That's good. That's probable that we would get a binary neutron star. And then we also still got like 6.1% said that, oh, we got a neutron star merger before star formation ended. Yay, that means we probably could get R process enrichment. However, none of those were producing an R process before the 78%. Where you got your 85% of star formation, and then we still haven't gotten a neutron star merger. That's not aligning with what we actually observe in Reticulum-2. And this is also not accounting for how much this is a really small galaxy. We expect it a lot of the R process to be ejected from the neutron star merger exploding outside of the galaxy. So for Reticulum-2, it's very unlikely that a neutron star merger could account for for the R process enrichment. So do neutron star mergers account for R process enrichment? They are very good at doing it for larger galaxies. They account for both the Milky Way and for the mid-sized dwarf. Very good. But doing just those two is not enough. It could not expand reticulum 2 at all. It failed to get for this 78% of the stars. And we really need, your theory is only good if it matches observations. We also did not consider how much time that would take from, oh, you have your, say your neutron star merger is ejected a little bit outside the star formation region. Well, we didn't account for the time for that material to actually get back to a star formation region. So it could easily be that this time scale is even longer, which makes this theory even more unlikely. And then, so yeah, even more unlikely to be the sole source of our process. We also have more uncertainties in the sort of delay time that we aren't totally sure. We cannot actually observe something for a neutron star merger, true neutron star mergers for millions of years to actually see how long does it take you to observe. These are all, so we don't totally know, but it seems very unlikely that they are occurring at a faster rate, which leads us saying that we probably need to account for collapsars or other potential sources of our process, especially to enrich the very small galaxies with the heavy elements like gold and such. Special thanks to Jonathan. You did really great. Thank you so much. Also, Anya Nuget, Ashley Villar, and just the entire AstroREU. You really had a really great summer.
Thank you, Allison. It's been a pleasure having you here. I do think that the idea that, speaking as someone who's trained as a theorist, the idea that it has to match observations is very quaint. But yeah, let's take some questions at the back there first.
Yeah, just a couple of background. Under what physical conditions do we expect our process to occur as opposed to say the slow process? And then, do you actually see any neutron star mergers around the minimum time of 200 years? Because that seems really quick.
So for the minimum time, I'll address that first. Those are all theoretical models, essentially, sort of saying, okay, we have, it actually estimates have ranged from, oh, it could take like 10 million years to like 500 million years as a minimum time. And sort of, I just sort of chose a sort of minimum time somewhere in the rough estimate of like in the middle of that. It seems more likely that it's on the longer side now. As for the, I'll go back to the, so your question about the S process versus the R process. For the R process essentially means it's really rapid, that you're essentially you have a neutron environment that is so like dense that you're adding neutrons into your nuclei before beta decay can actually occur. So that requires the sort of, I don't remember the energy requirements, but it's a dense, essentially neutron density of upwards of 10 to the 20 neutrons per centimeter cubed, versus an S process, which has a little bit less requirements. You can get beta decay while between putting neutrons in there. But,
in the neutron star formation versus stellar formation rate plot for Reticulus 2, I think. Reticulum 2, thank you. I noticed that there were like these two spikes sort of making up the vast majority of star formation. Is that more so an artifact of the simulation and observations, or does that actually physically
That's
indicate?
more effect of this plot. Essentially, I took from this plot essentially the sort of average jump, because they have the minimum estimate, the lower estimate. So that's sort of an estimate of like this jump. I'm not totally sure if, because there's 2 time steps in there. And essentially, I think that's just an artifact of how the data appears. I think it's probably more likely to say it's a singular jump, but averaged over 2, that's what it does.
Yeah, when you talk about you said 100,000 like sample runs.
Yeah.
You said like 6% of them produce a single neutron star merger?
At least one neutron star
At least,
merger.
okay, at least one. So if, yeah, even if, are most of the stars R process enriched in reticulum 2?
72 to 78% are, yes.
Okay, so even if, say, there was 1 or 2 or 3 of these neutron star mergers, is there any idea how that would distribute across the entire dwarf galaxy? Like, how would it get distributed across all of the stars, across the entire galaxy?
One, it's a very small galaxy.
Mm.
So we can sort of, and also I'm not like going into the details of how the gases mix throughout the galaxy, but additionally, neutron star mergers produce a lot of jets. So essentially, if you have that partially, the material is ejected, you can sort of assume over time that the R process is going to get fairly distributed.
So very big boom.
Yes.
Yeah, I was wondering, what would be your next steps? Like if you had more time, what kind of improvements would you make, or assumptions would you test?
Yeah, so a lot of it was like sort of dependent on sort of, there's a lot of like various debates about like the sort of delay time such. And additionally, I think personally, if I had a lot more time, I would be accounting for the sort of the extra time of, oh, this, how much is like from where your neutron star merger is actually occurring to versus the galaxy center. Like that time sort of delay, I think it sounds like that's a significant portion of like, okay, you have your merger somewhere else. What's the delay time on that to it in addition? So I think that would be an important next step.
One last question, Dvorak?
Hi, amazing talk. And towards the beginning of the presentation, I think you had a slide about the evolution of like R process and S process.
Yes.
So towards the beginning, there's something called like stellar burning. What is stellar burning?
So I believe stellar burning would be essentially the, correct me if I'm wrong, I did not study this if I'm wrong. I believe that would be sort of what you get within sort of a stellar core, right?
So like the regular CNO process, for example, or the regular fusion that you get in this core of the star before it goes bang.
Oh.
Yeah.
Right? And then it goes bang and you get this much more intense, dense, hot situation for, you know, a very short amount of time.
And that's how we can get the R process.
And that's how we get all the way out of the elements. So, you know, your star like sits around for millions of years making helium and maybe a little carbon and up to iron. And then once you want to get beyond iron, it's that last few minutes when it goes bang and you have these ridiculous conditions, but all of this other stuff happens.
Awesome, thank you so much.
Right. Thank you.
All right, thanks. Our next speaker is coffee break. And we will resume in 15 minutes at 11:20 when Gabi will be talking.
Hear me out. New sci-fi concept.
Please take your seats. Feel free, however, to continue getting food and coffee during the session. So, our first speaker of this second session is Gabi Oliva, who comes to us from the University of Texas. And has been working with Thomas Connor and Luca on high redshift galaxy candidates. So, Gabi, all yours.
Thank you very much. Hi guys. So today we're going to be looking at investigating high redshift galaxy candidates with Chandra. When you think of a galaxy, usually you think of it being in light. So you can see some large scale structure, you can see some arms, see some little dust clouds going on. This is what you normally think of. But what you don't normally think to look in is the X-ray. You can uncover some hidden phenomena going on within a galaxy in the X-ray. So we have some X-ray binaries, we have traces of supernova and remnants, some starburst-driven winds and outflows. But most importantly, in the X-ray, you can see star formation and AGN activity that you wouldn't usually be able to see if you just look at it in optical infrared. I don't have my mic on.
I'm gonna start over now. It's too late.
Yeah. Is it on?
It's on the top of the thing.
Top of the thing?
Switch over.
Right there.
You got it?
Okay, yeah. Is that okay?
Yeah, that's my credit.
Okay, so sorry about that, guys. Okay, that's loud. Okay, right. So, star formation, AGN activity. Keep that in mind. X-rays. Super cool. So, how are we going to look at these X-rays of these galaxies? Well, of course, we want to use Chandra. It has the best spatial resolution of any. It has the best spatial resolution of any X-ray telescope, so it's the perfect telescope to use to look at these types of processes going on. But drawback of Chandra is this is what a significant X-ray source looks like. You can't really see it, but there's little gray dots here, and that's one photon. These may be 2 or 3 photons, and that is a source. So when you try to get a significant detection from the background, it's kind of rough. It's kind of hard to do, and so it makes detecting really faint things like high redshift galaxies really hard to detect. So you need really deep surveys, so long exposure surveys in order to get these types of images. So typically, what you do is when you want to categorize something in the X-ray is you take a deep field or a field of X-ray, and you look at what's bright in the field, and you're like, oh, I think, you don't say I think, but that's an AGN, and you characterize it like that. But when you do that, you only characterize the brightest objects that are able to be picked up by this telescope. Most X-ray sources are obscured in some way, or they're going to be more faint than they actually are, so you're not going to be able to pick up truly the real emission from these sources. You're only going to select the most bright sources, which is not good, especially when you want to look at really faint things really far away. So when you look at a galaxy like this, Whirlpool Galaxy again, here, because it's at a low redshift, it's in the nearby universe, you can pick out what X-ray components are coming from the X-ray binaries, what's coming from star formation, what's coming from such and such, or AGN activity. That's because it's close. But once you start going into the redshift, even like redshift 1, as the redshift increases, the size of this image decreases, and all of the X-ray components start kind of like you just see a sum of the X-rays. And so it's hard to parse out which is coming from which component. But in the nearby universe, the low redshift regime, we have pretty good models of galaxies and how much X-ray we expect them to be emitting. So we can kind of subtract out the AGN component of this X-ray luminosity, and we can better look at star formation, which is what we really want to be looking at in these galaxies. So this plot from Basu-Zeitch is really important. It's going to be coming back later in the talk. So it maps X-ray luminosity over star formation rate as a function of redshift. And we have a pretty good handle on what the current trend is for this lower redshift regime. But
We want to see more. That's only informed up to a redshift of 4. I want to know what's going on in the early universe. What's going on when these galaxies are babies. Because the X-rays at this time of the universe impact models of reionization or galaxy evolution and universe expansion and just so many things that we can learn from X-rays back during this time. But how are we going to do that? Because remember, Chandra, it's only a few photons, really faint. We can't look at the X-ray. What are we going to do? In comes James Webb. Work with me here. So, I know. So James Webb is already pushing the limits. Can I play this video? Yes. Okay, James Webb is already pushing the limits of what high redshift we can look into. We already confirmed a galaxy at redshift 14.5, and we do that with this Lyman break technique. So if you look over here, this is what a spectrum of, let's say, a galaxy looks like. And right here at this little break is called the Lyman alpha break, and it happens at the same point, 912 angstroms, no matter where you are. And this is any type, if your galaxy, if the light passes through any type of cloud or dust, it's automatically going to just kind of break off. You're not going to see anything. So if you're imaging it with wide filters, you're going to see in this filter nothing because it's gone. It's been absorbed. Same thing with this one. You'll have where it's breaking. In the filter where it breaks, you'll have like a half detection, kind of, and then it'll be bright and then bright. And so that's where you can figure out, okay, it's breaking here, so it's at around this redshift because that happens at the same point, no matter the wavelength. So currently, James Webb has these filters. Ooh. There we go. This is how far the Hubble filters went, and so this is how much longer James Webb is pushing this out to, which is really awesome. There we go. Okay, so this project, we're going to be working on, it's based off the CEERS project, which is the first, it's an ERS, it's a first cycle James Webb project. It is a near-cam imaging survey that covers 100 square arc minutes on this field called the EGS, which is just an area in the sky that's been imaged by a lot of things. And it images it in these 6 blue wide filters. This team, this work, is my collaborators added this James Webb wide filter to the CEERS imaging, and also this narrow filter. So it covered the exact same area in the sky and imaged it in these 2 additional filters. So if we take a look here, what we did is when we saw a increase in flux in this filter, that means that there's an emission line peaking in this filter. So when some spectrum is redshifted and then an emission line falls into here, we're going to see an increase in flux here, and from when we subtract this flux from the wide filter that it's in. Anyway, so if you take a look at this black spectrum, this is a model spectrum of a galaxy at redshift 6.2, and you can see that its H alpha line is peaking in this narrowband filter, and it's this Lyman break that is happening in this filter. That means because we can see the reduced flux in here and we can see the increased flux in here, we can categorize this as a redshift 6.2 galaxy. Same thing if we redshift this model spectrum a little bit more and we redshift it to redshift 8.4, the break happens in the 115 filter, and then the O3 is peaking in this narrowband filter, which means that we can categorize it as an O3 emitting galaxy. All right, so from applying this selection to the entire CEERS field, we found 51 H alpha emitting galaxies at redshift 6.2, and we found 9 O3 emitting galaxies at redshift 8.4. So we also found some other interlopers that also peaked in this filter, but I don't have time to talk about that today. So this project, this is what one of the pointings of the CEERS field looks like. So these are some of our galaxies. Let me introduce you. So this is what they look like. These are the redshift 6.2 galaxies in the CEERS field. Super cute. And these are 2 of the O3 emitting galaxies at redshift 8.4. So we're seeing stuff. It's very cool. And this is in the CEERS. This is in James Webb imaging. So now that we have our sources, we found them, they're in this field, we have 51 at 6.2 and 9 at 8.4. And they were imaged on this field. Oh, this is an X-ray project. Where are the X-rays coming from? Guys, what if I told you that this filter, this area of the sky was also imaged by a deep X-ray survey called AGES XD. It's a deep Chandra imaging of the same area on the sky from cycle 9, and is one of the deepest X-ray surveys that Chandra has, with an exposure time of 800 kiloseconds. Fantastic. So now we have locations of known high redshift galaxies, and we have an X-ray field to detect them on. So first we're going to go in and look at them as if they were X-ray point sources. We're going to see if we can see a significant X-ray detection here on this field. So this is the field, and this is zoomed in the location of all of the objects on the field. So the pink ones are the redshift 6, and the blue ones, or teal, are redshift 8. And so we used Chandra's Chow, which is like a data reduction program, and we used their function called source flux, which if you give it a position on an X-ray field, it'll see if at that position there's a significant detection of an X-ray flux. And we did that, and we found 7 H-alpha emitting galaxies and 1 O3 emitting galaxy had significant X-ray flux on this field, according to source flux. That's 8 galaxies, guys, that you can see in the X-ray. So do you guys want to see the pictures of what they look like, guys? Those are galaxies, guys. Can't you see? Like, wouldn't you know? So it looks to the eye, by your laughter, that you guys don't believe me, that these are galaxies. I swear they are, but they don't look very bright in the X-ray, which is expected because these are redshift 6, redshift 8. We don't expect to see photons coming in from here. But we wanted to make sure, so we did extra math, we did some Poisson statistics, and we wanted to see if, based on its background, if the photons that we see in this area are significant, they're above the background, they are a good detection. And, we found one of them, yes, technically. This one, to a significance of 2 sigma, that detection right in there is significantly bright compared to its background. But in a catalog of 60 sources with 2 sigma, you'd expect at least 3 of the objects to present themselves as a significant detection. So unfortunately, we're not considering this as pretty good. Kind of threw it out, but we weren't expecting that the bulk of our cool science would be from looking at these point sources. But we were expecting, what we can now do is to take all of these sources that we found and stack them together, stack their X-ray images to get some real good detections. So if you're not familiar with stacking, it increases the signal-to-noise ratio of faint sources. So you just add all of the pictures or the images of your sources on top of each other, and it makes the real detections come out more. And we're using the package CStack, which uses bootstrapping, which kind of resamples its data so that you get more of a more strong, more broad detection. So again, we're going to be stacking the 51 sources at redshift 6 together, and we're going to be stacking the 9 sources at redshift 8 together. So this is what it looks like. This is what CStack gives you. So CStack gives you an average count rate, which is how many photons are hitting your detector from the source. And we find that this one coming at 2.77 times 10 to the negative 6. Super cool, great. And this is, and this is in the energy band of 0.5 to 2 keV, which is more significant because these are so far away. The shorter bands are going to be more bright, you'd expect. And here, slightly lower count rate for the harder band. And then the stacking for the O3, there's only 9 of them. So when you stack less things, you're going to get a less significant detection from it, unfortunately. And we only had 9, not our fault. So also a pretty dim count, like a smaller count rate. And here we have a negative count rate, which is not good. So basically what this is saying is that the sources that we gave it, the points that we gave it, are more dim than the rest of the background. So they're just really not there. So that's okay. But what's important is that we can take these count rates and we can plug it into PIMS, which is a Chandra tool, and we can get a flux from these objects, an estimated flux of these stacked objects. And then we can take that flux and we can create a model, an expected model luminosity of the X-ray of these objects. And then we can use that and the luminosity of the H alpha in order to better constrain star formation rate, like that plot I was showing at the beginning of the talk. So we tried to do that. So here's this again for reference. So when you plot, because we couldn't plot the O3 stack because it wasn't that significant, it wasn't a good relationship. It wasn't a good relationship. I'm almost done. We didn't have anything for O3, but for H alpha, it was nice, robust stacking. There was 51 objects. So we got our point would be there on this graph. Okay, okay. She's doing her own thing. So, this indicates that these galaxies are generally, most likely, going to be host to strong AGN. They're in this AGN regime that Bossuzaj created. They are too X-ray luminous for their emissions to be explained only by star formation rate. So there must be some type of strong AGN component coming from these galaxies that we detected using CEERS. And this could indicate that AGN may have had a larger role in the early universe's ionization than we thought. So that's interesting. So summary, there were no significant X-ray detections yielded by the sample of high redshift galaxies by themselves, individually. Stacking was successful in increasing the signal of these distant X-ray sources, at least when we had a robust enough sample. AGN components of these high redshift galaxies may be more dominant than we thought. Interesting. And this color selection method of picking out emission lines can be used on other fields with deep multi-wavelength coverage, something that we can expand upon instead of maybe not just use James Webb, but use other telescopes. And more deep X-ray imaging is necessary in order to draw more conclusions about distant X-ray sources in the early universe. Thank you.
Thank you, Gabi. We have time for a couple quick questions.
Sorry.
Zach.
What kind of errors do you expect on that X-ray flux that you showed?
The flux or this point?
That, yes.
This
that
point, some pretty solid errors because it's based on a lot of plugging into models and assumptions. We're assuming a bunch of expansion constants, and we're expecting this C right here. That is just 4.5 times 10 to the negative 42. That is a number, and it's the same for all of this, which doesn't seem. I feel like there should be a more nuanced, because maybe it does explain the low redshift more, but these are peculiar. You know, they're new. They're crazy galaxies. They're not new. They're very old. So maybe they act different, and so maybe we need a better model to look at them. But some pretty solid error bars on those.
All right. One more question. Yes.
Oh, I don't have a great question.
It's only one. If no one else does either, so go.
Okay, well, I was just wondering the green boxes, the ones with the arrows.
Yeah.
What's the difference between that and the error bars?
The arrows, so the error bars are error bars, which means they could tell, top bottom. But that's the explanation. These are upper limits. So based on when it has the arrow pointing down, that means that is the brightest, or I guess the highest you'd expect is somewhere down from there. But those error bars means like it is somewhere within that range based on what they expect.
So it basically means that the error bar on that one could go all the way to the bottom of the
Yeah.
All right, thank you. Oh, well, very quickly.
Yeah, what would you want next? Like, what would you want to do? Like, if you could detect these sources, what would you do?
Good question. Okay, so I wish we had a better X-ray telescope with a wider collecting area so that we could have more photons, more stuff to work with. If not, if we can get more deeper images of these things so we can get something from these galaxies, that would be great. I also just want to look at more of the sky, get more of these, because 51 and 9, there's more out there. I want to get, I promise there are. And I just want to see more so that we can better constrain it and just look at more stuff.
So we only need a few billion for our next X-ray.
Yeah.
We'll be passing the hat. All right, thank you. Let's thank Gabi.
Stupid mic.
Yeah. Lesson learned the hard way. Always remember to remove your mic before you go to the restaurant.
Here? Is that good?
So we have 2 more talks before the lunch break. So our next speaker is Will Kinley from the University of North Carolina, Asheville, who has also been working with Luca and Thomas. Thank you for your efforts this summer, Luca and Thomas. Will is going to be telling us about blazar space densities at ridiculously high redshifts. So go for it, Will.
All right, thank you for that introduction, Jonathan. Like you just said, I'll be talking about computing the blazar space density evolution from these ridiculously high redshifts, 1.5 to 4.5. My wonderful advisors are Luca Akina and Thomas Connors in the crowd right there. And so we can, and I also want to talk about how we can use blazars sort of to study fainter jetted AGN populations. So I'd like to start by just refreshing everybody's memory. Here we go, here's the pointer on what a blazar is. So we have a supermassive black hole in the center. Oh, this is not the right one. This one, okay. There we go. In the center of a galaxy, and we have these relativistic jets coming out of here. And so a blazar is when we're sort of looking down the barrel of these jets. So right here, this is a 3/4 view, and this is a top-down view. So we're looking straight into this jet, and this leads to some unique emission mechanisms, or not emission mechanisms, but we have a unique spectral energy distribution here, and some nice boosting, which I'll talk about in a moment. So just again, this is a little diagram, oops, talking about the orientation, where we are the observer looking down in here, and so we can actually study these blazars. We can see fainter AGN populations because we're getting all this boosting, this relativistic boosting here, coming towards our line of sight. And so we can use a sort of geometric argument here. If we are looking at one blazar, which is really just an AGN with a jet, there's other jetted AGNs that are misaligned to our line of sight. So there's this big sphere of just misaligned AGNs. And so because of that, we can use blazars that we can actually see these things, and we can sort of extrapolate to general AGN populations. And so this is like the formal sort of equation here. We have the number of blazars, some term here, which I won't get into now, and we can actually think about the entire AGN population statistics there. All right, so that's just a recap there. And so I just want to talk about a little bit more of these characteristics of blazars. So first is just a half of a structural SED for one of these objects, and I want to focus on the radio emissions here, this radii. So we have a very, very strong flat radio peak. This doesn't look too flat, but I promise it is. And then on top of this, we also have a very strong X-ray and gamma peak. We don't worry about the gamma waveband right here, because that's just too hard to observe. But essentially, we have these two very, very strong peaks here that are very characteristic of looking at a blazar. And additionally, we have this little blue component right here, and that's just other AGN components. So then this red thing is what you see when you look at a blazar. Additionally, this is an optical spectra, and just really quickly, we can also just see, oops, this clicker, we can also just see this sort of the broad emission line here, which we can use if we're confirming these objects by eye and things like that. So moving on, so we have these blazars, we have this sort of idea of how we can apply them to general populations. But there's an issue in our data that arises when creating blazar samples. So when computing the space density evolution, so this is just how many, the number of blazars per volume across time. And so right here you can see sort of this sphere. So we're sort of looking at this shell. You can think about onions here. We're looking at different layers of an onion. So when previous works have actually done this work, or like computed the space density evolution, they find different results. So I first want to talk about Mao et al. 2017, and they generate a blazar sample in the radio with FIRST. So they are looking at that very distinct radio emission and saying this is a blazar. And so that's how they generate their sample here. And so they report a peak in the space density at a redshift of 2.2 around this area right here. So that is right there. And just again, this y-axis right here is the number of objects per volume, and we have all these different redshift bins. So they say that we count more blazars per volume at this redshift here, which was very consistent with other studies. However, we go over to Marcattulli et al. 2022, who has an X-ray sample of blazars detected in the X-ray, and they found a peak at z equals 4.3. So there's something going on here. Why are these two different samples finding different peaks? One is in the radio, one is generated through radio detections, one's through X-ray detections. And it's just them side by side. And so if we want to use these blazars as like tracers for general AGN population, we want to find out what's going on here, because these give us wildly different results. I mean, one is saying that there's more jetted AGN at this point in the universe, and one's saying that it's down here at earlier points in the universe. So we want to understand why this is here. So how do we actually address this? Well, we start with creating our own sample of blazars with the newest and best X-ray data. How do we do that? We use ERAS, which is part of the EROSITA, which is aboard EROSITA, or using the EROSITA telescope, and it's an all-sky survey with about 900,000 sources detected in the X-ray right now. So it's about the 0.2 to 2.3 kiloelectron volt band. And this is just a nice little picture of everything. That's the telescope there. So step one of creating this sample of blazars as detected in the X-ray is we start with ERAS, and I'll just go ahead and click through that. And so right up here, I want to point out that this is the coverage of ERAS. So I said it's an all-sky survey, but only half of the data is released publicly right now, so this is all we get. And I also want to draw everybody's attention to our sample size, which is going to dramatically decrease horribly as we go through this process. So just keep an eye on this number down here. Place your bets on what we have at the end. So step two, we have some X-ray data, and we want to get some spectroscopic data and radio data. So conveniently, SDSS, there's a quasar data release, which piles about 700,000 confirmed quasars with other surveys. And so within this, we have the first survey, which is a radio survey. So we want this radio data. I'll speak a little bit more on that later. And so right up here, you have this sort of black area, and that's where our SDSS and FIRST surveys are overlapping. There we go. And so we want more radio fluxes. We'll get to that part, why we want these. Actually, I can just say now. So we want these to do a further confirmation of that sort of radio spectrum. So we can use these as another identifier. We can use the radio emissions as another identifier of blazars later on. So we matched to VLAS, which FIRST and VLAS are both VLA surveys, and this is everything above 40 degrees of declination here. So moving on, this is just the full sky coverage. And we kind of have to eat our vegetables here first and talk about spurious matches, which is just how many non-real matches are we making. So when we cross-match ERAS and our SDSS catalogs, what's the chance that we just get some false positive? So to start, in ERAS, they give us some nice positional errors, and we create 3 bins just to reduce, hopefully to reduce the amount of spurious contamination. And then past this, we also make mock catalogs and match a mock catalog of SDSS data to the ERAS data. So just quickly, we have a real SDS source, and then we offset it by some random position. And we do this 200 times, so we have 200 randomly scattered views of the sky. And we count the number of false detections, false matches that we get. So we do this, and we average it out, and luckily we find that all of our sources are of 92% confidence. So if we have 100 sources, 92 of them are probably real, or likely real. And this is just a quick graph explaining, this is the log scale of the counts of real sources, is this black line, and this is the mock catalog, and again, this is log scale, so it kind of looks a little rough, but these sources are well above the number of spurious contamination, and then out here at higher angular separations, we have more contamination, but these can be checked by eye, because these are only a couple sources here.
How many sources are in all of our sources?
How many?
Like so you out of the here when you have like 92, all of the sources that you're talking about here are above 92% confidence.
Yes.
How many is that? Like all of them?
How many is all?
How many is all?
That's about like 1666, I think. 1666 sources.
Okay,
yeah. Okay. And so going back to this radio emission here, this SED, we want to confirm that we have flat radio spectrum because this is just another way that we can ID these blazars. And if you remember, we have 2 very nice radio fluxes, so we're just fitting a line, taking everybody back to algebra 2 here. And this brings us down to 1,377 sources. And our last cut that we want to make on our sample is a luminosity cut. So this discrepancy that I mentioned earlier, sort of like the different peaks, is primarily observed in the most luminous blazars. So this is that Marcattulli X-ray sample paper, and this discrepancy is just, it's at these higher bends. So we select a cut at every luminosity greater than 45.8 ergs per second in log scale. And how do we do that? Just standard luminosity distance equation, where we have redshifts from SDSS. We do applied K correction of 0.6. So cutting that, this is the 1,377 sources. These are all the ones below our luminosity cut, and these are all the ones above the luminosity cut right here. And our sample size is down to 48. So big drop right there, but that's still good. So only 48 sources, you might be saying, but comparing that to Marcattulli et al., sorry Marcattulli, but we have over double the number of sources compared to this highest X-ray, this highest bin, luminosity bin right here. So this is only about 20 sources across this line, and we have 48 now. So we've over doubled the statistics. And just as a recap, we have our 4 survey cross matches. We check for flat radio spectra, and then we make that luminosity cut. And again, we end up with a sample of 48 luminous blazars at 1.5 to 4.5 redshift. So, all right. So if you remember, we're trying to figure out the space density evolution of these guys. So let's talk about how we do that. And again, this is just the number of objects per co-moving volume. So co-moving volume is essentially just some shell, remember that onion, and it takes into account the expansion of the universe. So we use the Vmax method described in Schmidt 1968. This has been around for a while. And the special thing here is that our Z2, so our outer redshift, is the redshift at which one of the sources in that bin, it's the flux limit. If you shifted that source over to this redshift, it would be at the flux limit of the survey. So this is just further, this is removing some observational bias here. And so again, the evolution part is that we calculate the space density across time. And here we just have like the volume, and then so we take this volume and then we sum up the number of sources in the volume here. So the observed volume, which essentially is how much, what is the shell of the sky that we're looking at, and then we count up the sources in there, and we have our space density. So, and that's just our bins, and we do this for 7 bins specifically in our project. So actually, what do we get from this? Drum roll, please. We find a peak at a redshift of 3. So just to recap, we created a blazar sample in the X-ray, and we increased the statistics compared to Marcattulli et al. By a factor of greater than 2, and we find a peak here. So that's weird, because if you remember, that's not what happened in either 2 papers. So our first sort of result is that we do not confirm this peak that Marcattulli presents here. And additionally, we don't confirm this Mao et al. Peak either. And remember, this one is this one is a radio selected sample of blazars. So what does this actually mean? Let's see if yep. So we don't confirm either evolution, but our results could suggest a similar X-ray evolution to Marcattulli, but maybe just not as extreme. So we're below this line and we're above this one, and we're looking at the X-ray. So maybe we have some sort of X-ray evolution of the X-ray properties of blazars. That's just maybe it's similar to what's presented here, but not as extreme. So sort of shifted down a little bit. And if you remember, we're IDing blazars based off of X-ray and radio fluxes. So maybe that's sort of splitting the difference between these 2. And so what can we do now in the future? We can consider different luminosity bins. So if you remember, we did this for the highest luminosity bin here, but we cut out all of those other sources. So we could repeat the similar process, but for different binning. We could also increase our high redshift statistics. So everything out here, everything past like 4 starts to get a little bit limited, and so we can maybe combine samples or do further look at further surveys to increase those stats. And then finally, it would also just be interesting to look at these individual objects, because these are very, very exotic and unique objects in the sky, and especially when you get out to redshift 4 and 5, or 4 and 4.5, you're getting to very early points in the universe. So, all right, this is just a summary slide of everything I just said. And lastly, I'd like to acknowledge the wonderful table tennis player and my advisor, Luca Aquina, Thomas Connor, and all the wonderful friends I've made this summer who are in the crowd, Matt Ashby, and lastly, Jonathan McDowell.
Thank you, Will. Questions? And right back there.
I'm wondering, so comparing that to those 2 other studies that you were comparing to, could it be that for blazars X-ray activity peaks in higher redshifts, and then radio activity peaks at lower redshifts?
Yeah, I think that's part of the thought, is that there's the way we get these different emissions in X-ray and radio there's separate emission mechanisms. So I think the idea is that they sort of evolve differently over time. There's a lot more to say on that, but I think that's sort of what may be going on here that's giving us these different peaks. I'm not sure. I'll have to think about it. I can talk to you after this. I wouldn't think so, but
I noticed that the two studies you cite, they use different luminosity bins, and there seems to be a luminosity dependence on the blazar density over Z. Is it possible that there is a split between log of L equal to 45 and log of L equal to 46?
46. So are you saying between these two here?
So the highest luminosity
the more luminous ones evolve differently.
Yeah, I mean I think again, like I said earlier in the thing, we observe this discrepancy in the most luminous bins. So when you look down here, it's kind of flattens out. But when we start to look at really high luminosities, something is changing. So I think yeah.
Yes.
So very interesting. Thank you. A while ago, we were looking at the Chandra X-ray detected blazars and SDSS. So we had sample of 86, I think, but we didn't look at the space density evolution. So I think that's a sample to basically combine this. We were just looking at the properties of the sample, but of course Chandra is very expensive.
Yeah.
So you need to have a lot of corrections, but that's maybe another survey.
Yeah, I think that would be good.
Yeah.
To just increase the statistics of it, but it is hard because it's less of the whole sky. But
yeah, you have to put corrections on.
But it'd be nice to sort of add stuff to this curve out here. So, anything else?
Yeah. So I'm not an astronomer, but are the x-axis? Sorry, not the x-axis. The y-axis on all these plots the same? So the bottom two, which are from the papers that you cited, are from those have some crazy units. Is that the same as on the is that the same as a space density as you have it?
Yeah, it's these units. It's you can see this one's in megaparsecs. I don't know if you can see that, but this one's in gigaparsecs. So they're all saying the same thing, but it's just a different way of writing. They're all saying the space density in a way.
Per cubic gigaparsec, essentially.
Yeah, exactly.
Some of that in slightly different scales, but
but
since we're only looking for where the peak is, it doesn't matter what the y-axis is.
Yeah. Cool. Thank you.
All right, we better move on. So we have one more talk before lunch. I am informed informed that vast quantities of food are here, so we'll get our appetite ready by listening to our next speaker. Our next speaker is Sophia Kempe from the, how do you pronounce your last name? Kempe, it is Kempe. Sophia Kempe from the University of Connecticut. And Sophia's been working with Razi Amami, and they've been working together on modeling what happens to the chemical evolution of a galaxy when you put in an artificial starburst into your model. So, Sophia.
Hi. Hello. Thank you. Thank you for having me. All right. So, thank you for the warm welcome. As Jonathan said, we are going to be looking at the impacts of a Gaussian starburst on the evolution of galactic element abundance ratios. So, when we look into the universe, we see an incredible diversity in galaxies. An incredible diversity. We see galaxies, we see galaxies with different star formation activity, mass, metallicity, morphology, galaxy interactions across all redshifts. One of the questions that we are looking to answer is, what causes galaxies to become the way that they are? How do we, what is causing all of this diversity that we see? What drives the features that we see in galaxies? In particular, I want to investigate the question of what is driving the galactic enrichment. So what physical processes are we seeing that is causing the different elements that we see in different galaxies? However, this is a very complicated question to answer, because galaxies are very complex, dynamical systems, and many factors influence their evolution. When we look at the enrichment of a galaxy, it tells us the history of the processes that produce elements in that galaxy, star formation in that galaxy, and galaxy environment interactions. But how do we disentangle this story? Thanks to the advancements in the near-infrared, thanks to JWST, we have access to unprecedented spectral resolution, allowing us to investigate metallicities at incredibly high redshifts, more than ever before. I have the pleasure of working with data from the JWST Blue Jay survey. And as you can see, we have a bunch of people from the team here who are at the CFA. And so the Blue Jay survey has obtained deep spectroscopy of 150 representative massive galaxies at cosmic noon, which is around a redshift of 2. And today we're going to be looking at one of those galaxies, Cosmos 8013, which is a quiescent, meaning like low star formation rate, galaxy at Z equals, I think I mistyped the redshift. It's actually 1.69. And this galaxy in particular is representative of a post-starburst galaxy from their quiescent sample. So a post-starburst galaxy is a galaxy that has experienced rapid quenching after an episode of high star formation. And these galaxies make up 30% of their quiescent sample of galaxies. So what are we going to do here? We are using a galactic chemical evolution model to simulate element abundances over cosmic time. So how are we doing that? Our model is implementing a single zone approximation. Basically what that means is you're imagining a galaxy is just a box. And inside of that box, you have gas and stars. And the assumptions of this are that the gas is uniformly distributed and all new elements are mixed instantaneously throughout the region, which removes all spatial dependence, which makes our calculations easier because we don't have to worry about localized pockets of different metallicities.
or like mixing in the galaxy. At any time in the galaxy, the rate of gas that is in the galaxy is going to be dependent on a couple of things. It's going to be dependent on the rate of mass flowing into the galaxy, of gas flowing into the galaxy, the rate of gas flowing out of the galaxy, as well as the rate of gas that's being converted into stars, given by the star formation rate, and the rate of gas that's being returned, enriching the galaxy. So let's go back to our flow chart that we saw earlier, and let's turn it around a little bit. So I'm going to be breaking down each of these aspects and going into a little bit more detail here. So first, we're going to take a look at the processes that produce elements in galaxies. So you probably know this, but different elements are produced by different processes. This is a very famous figure, which shows the periodic table based on the processes that produce each element. And we see that there's a large variety in the processes that produce each, different elements in different regions of the periodic table. And several of the other interns have also mentioned this before. And so, all right, so in our simulation, we are only considering 3 of these. So we're considering, these are the most common nucleosynthetic processes that we see. One of these, the first one is the core collapse supernova, which is dying, massive, short-lived stars, which mostly produce alpha capture elements, like oxygen, neon, magnesium, etc. And we also have type 1a supernova, which produce most of the iron peak elements that we see in the universe. And then AGB stars have S process, which is slow neutron capture, which is like the counter to rapid neutron capture that Allison talked about earlier. And so for type 1a supernova and AGB stars, they are ruled by a longer time scale because of their progenitors are lower mass stars. And in particular, I want to point out that for type 1a supernova, because it's a binary, it's not going to be ruled by a single time scale, and also we see a large array of lifetimes of these stars. So instead of picking a single lifetime, we do a distribution of explosion times. But for core collapse supernova, because these stars are so short-lived, we essentially are assuming that they are going to explode instantaneously, because compared to the timescales that we are considering for galactic chemical evolution, they're extremely short. Right, so now that we have that, let's move on to the star formation of the galaxy. So as I said, we are considering a galaxy from JWST's Blue Jay survey. And the high-resolution spectra from JWST allow us to estimate the star formation histories of galaxies from spectral energy distribution fittings. So in this plot, you can see we have the star formation rate on the y-axis and the time since the Big Bang. This is the star formation history that has been extracted from the SED fitting for this galaxy by Park et al. But as you can see, it's very discontinuous. But we do see this. We see a constant star formation history in its history, and then we see the burst right before the observed time, which is here. So recently there has been rapid quenching immediately after a starburst. But because it's discontinuous, we want to implement a smooth function into our simulation. So we model this parametrically as a Gaussian with a constant background term. As you can see here, I have plotted the Gaussian fit to the bin midpoints in red, and in blue is still the original estimated star formation history of the galaxy. Moving on, we also want to consider the galaxy environment interactions. So basically, as I was saying earlier, the amount of gas in the galaxy is dependent on inflows, outflows, star formation rate, and recycling. But two of the parameters that we want to consider are dependent on the interplay between these different rates. So we have the star formation efficiency timescale, which is defined by the amount of gas in the galaxy divided by the star formation rate. And then we also have the mass outflow loading factor, which is the rate of gas leaving the galaxy divided by the star formation rate. I also talk about the metallicities that we have. So we're assuming a very low metallicity for inflows, and then all of the gas that's leaving the galaxy is the same as the interstellar medium of the galaxy. Okay, but for the simplest case, we want to adopt constant values of the mass loading factor and the star formation efficiency timescale. And as you can see based on these equations, if we're assuming a constant term here for both of these, and we know we are inputting the star formation rate that is constant and then has like a peak in it, that means that both of these are going to be dependent on the star formation rate function. And the implication of this is that the starburst is going to be driven by an inflow of new material. So now that we have all of these combined pictures, now we can finally start to talk about enrichment. And we can simulate the enrichment of the galaxy. And in particular, I want to talk about iron and oxygen because these are very commonly used in observation, and they are tracer. Iron is a tracer for supernova 1A activity, and oxygen can be a tracer for core collapse supernova activity. So let's jump into it. So here you can see, here's our star formation history. I've continued the evolution because, as we'll see, so in our simulation, compared to hydrogen, so for each element compared to hydrogen, and we see 4 distinct phases in our abundance evolutions. We see, firstly, we see an evolution to equilibrium under constant star formation rate. So during the first phase of the starburst, we see both elements evolve to some equilibrium value because of like the equations I was showing you earlier. If we have a constant value for eta and tau, that results in there must be like an equilibrium between the mass that's flowing in and out of the galaxy and the abundance of an element. And second phase, we see when the burst begins, new gas is flowing into the galaxy, diluting metal abundances. And so we see a dip in both of them. In the third phase, we see the new metal production due to the nucleosynthesis that's occurring in galaxies is surpassing the dilution rate, and so abundances rise. And then when the burst ends, we see that the elements return back to equilibrium because of outflows. Something that we would like to consider is sometimes we want to consider the difference between iron and oxygen because it informs us we can compare the core collapse supernova to supernova 1A. So what we see is that in this plot here, we have on the y-axis we've subtracted the oxygen line from the iron line, which is basically reveals the differences between these two. And so when we compare them, we see that in the initial evolution equilibrium, iron is boosted compared to oxygen because of supernova 1A, and also because of the longer timescale for evolving to equilibrium. So it takes longer to get to that equilibrium point, and so that's why we see an increase compared to oxygen. And during the burst, core collapse supernova rates are temporarily boosted. And so basically what that means is that the oxygen is not going to be depleted as quickly because it's immediately being replenished by the very, very fast timescales of core collapse supernova immediately exploding and replenishing the oxygen that's being diluted. And so we see the abundance of iron to oxygen drop. And then finally, we also see that after the burst, iron decays back to equilibrium at a longer time scale than oxygen, and so the ratio of iron to oxygen will be increasing. And we see the same thing in metallicity space. So here on the y-axis, we basically have the same thing that we have here, but then the x-axis is the ratio of oxygen to hydrogen. So we can compare iron's evolution to oxygen's evolution. And so here we see a lot of the same phases. So we see here we have the initial evolution to equilibrium when we see that iron to oxygen rises. And then when the burst starts here, we see that iron decreases compared to oxygen. And then when the burst ends at this point, iron begins to increase with respect to oxygen. But this is only for one galaxy. What about other galaxies with potentially different amplitudes or different burst widths or burst peak times? What do we see if we have galaxies with those features? We see a lot of complexity. In the next part of the talk, I'm going to be talking basically individually about each one of these and breaking down kind of like what we're seeing. So first, let's look at burst amplitude. So we see that in our animation here, when there is no burst at all, we have we have no loop whatsoever. And so basically what that's telling us is that the loop is produced completely by the burst, which is cool. And so we know that the burst definitely has an effect on abundance ratios that we're going to be seeing at a given time. And we also see the fact that the shape of it is changing. We're seeing basically that iron is more sensitive to changes in amplitude compared to oxygen. So we are seeing that after the burst, we see this rise more so than at lower amplitudes. So if you have like a galaxy with a much higher peak in star formation, you're going to see a much different abundance at a different time compared to another galaxy. And here I have also plotted, so this is the observed abundance, this is the abundance at the observed time of the galaxy. So like this is the galaxy this is the time of the galaxy that we would be observing. And so you can see at different points, we would be observing different abundances for different amplitudes at the same time. When we consider burst width, we find that overall, a wider burst has a sort of a smaller change in the amplitude of the difference from equilibrium. And we can see that here, if we increase the width of the burst, we see that it's much less of a change because it's more gradual. We also see that, again, iron is more sensitive to this effect, and that iron has a longer decay back to equilibrium than oxygen, which you can see here. So as the sigma increases, we see that iron has a much more gradual decay back to equilibrium compared to oxygen, because of the longer timescales associated with it, and also the function that we've used for the decay time distribution of supernova 1A explosions. And then for the burst peak time, we really don't see a large effect on the shape of the trajectory and metallicity, but we do see a change in the time. So the more recent the burst, the greater the effect on the observed abundance ratio. So as you can see in this plot, and a little bit in this one, like you can see the color scale changing, you can see that at the observed time, here is where this is the abundance that we would be observing, but for even half a gig a year sooner, or yeah, a burst half a gig a year sooner, you would be seeing an abundance that's much, much closer to the equilibrium, and then it only continues from there. So what that tells us is that the more recent the burst is, the greater the effect on the observed abundance ratio of a galaxy. So in future works, we would want to consider alternate burst mechanisms, because it's possible that maybe inflow of gas as a star formation, or as a mechanism for the starburst doesn't make sense for the galaxies that we're looking at. So we would want to consider potentially other burst mechanisms. We also want to potentially include a term for quenching at the late times in the galaxy. What we did was we basically assumed that it was constant, had a burst, and then returned to constant, which is why we saw that it returned to equilibrium. So it would be interesting to explore what would happen if we consider quenching at later times. And we also want to extend our analysis to all 14 quiescent galaxies and over 100 star-forming galaxies in the JWST Blue Jay survey, which would allow us to compare different populations of galaxies and see what patterns we see in their abundances. Additionally, we want to do a more direct comparison between our model predictions and observed abundances, which would allow us to better constrain our assumptions about galaxy parameters and yields. Potentially, we could do this by doing MCMC fits. Yeah, so this would be a very important next step in our work. While we have considered a redshift of about 2 cosmic noon, this framework can be extended to many, many different galaxies across many different redshifts that we can observe with many different telescopes. In summary, galaxy enrichment is complicated. There's a lot of different factors that are contributing to it. We have made very big assumptions, but we have to in astronomy. But there's still more that we can consider, more parameters we can consider changing. But if we consider just star formation history, we see that for amplitude, iron is more sensitive to changes, and also the same for the burst width. And we see that I can just show these. So we see that for an earlier burst, we have less impact on observed abundances. And then jumping back to this point, I skipped over it, but different element abundances depend on the star formation history, the various nucleosynthetic processes that produce each element, the galaxy enrichment interactions, as well as the time scales that control their nucleosynthetic processes. And then finally, in the post-starburst galaxies that we were looking at, we should still see boosted abundances after the burst ends because of this final period after the burst. So that's something that we could definitely look for in these galaxies. I want to thank everyone here for listening and coming to these talks. We really appreciate it. And I also wanted to say thank you so much to Rosie, my lovely advisor, Jonathan McDowell, Matt Ashby, Daniel Eisenstein, Charlie Conroy, James Johnson, who met with me and answered all my questions and gave me advice on my project, and also to my fellow REU students who made this summer unforgettable and taught me so much. And so thank you. This is my summary slide again.
let's take a couple of very quick questions before lunch. Yes.
So when you're computing the O over H, is that the total metallicity or just from oxygen abundance?
For the O over H?
Yeah, for the x-axis in this figure.
It is the, are you referring to like oxygen, like are you saying?
So I'm just concerned because that when the metallicity takes, like when the iron over oxygen is increasing, it looks like the oxygen over abundance is not decreasing. So I'm just like, maybe that's because the, hold on. Yeah, I was just confused whether the x-axis here is the total metallicity or just like the oxygen abundance over.
Yeah, so the x-axis here is the oxygen abundance, but oxygen is a tracer for, like, can be a tracer for the overall metallicity of a galaxy. So it wouldn't be incorrect to imagine it similarly as the metallicity of the galaxy. Yeah.
I think one other question is, what is the metallicity of these observed galaxies, and which model would explain the observed metallicity the best?
Yeah. So we had the star formation histories were already done by one of our collaborators, but we didn't have the observed abundances taken, or we didn't have abundances done already, and so just for the scale of the 10-week program, it would be way too much time to or much longer to try to get the observed abundances and also do this analysis. So that's part of our future work that we're going to consider. Yes.
Okay, we better thank Sophia again. We now have slightly under 1 hour for lunch. We resume again at 1:20. There's plenty of food. There's still some coffee left over. There's some drinks. So please help yourself. Welcome to the last two talks of the AstroREU symposium. Following that, we will have the CREATE program talks. So our first talk in the afternoon session for the AstroREU. Welcome to the last two talks.
Inception.
Okay, so I can confirm that we are now being streamed. Okay, guys. So I'm very pleased to introduce Andy Dvorak from the University of Maryland, Baltimore County, who's been working with Caroline Huang this year on M101, lovely galaxy, and the AGB stars in it. So Andrew, take it away.
All right. So first of all, I hope you all are enjoying your lunch. Hopefully it tastes good. Again, my name is Andy. This summer I worked with Caroline to investigate a newer method of obtaining distances to faraway galaxies using J-region asymptotic giant branch stars. Specifically, my project is focused on the uncertainties associated with a color magnitude diagram generated from observations of M101. So the larger motivation behind this project involves measuring distances to objects in the universe, which is quite difficult. To your everyday person, measuring cosmic distances might not seem all that complicated until you realize you don't have a ruler that can stretch out hundreds of millions of light years. From our observations of distant galaxies, we can only measure angular sizes across the sky and the amount of flux that we get in our detectors. So when I look at a galaxy, I can't tell if it's super close and really tiny or if it's far away and extremely large. To counter this, we can leverage astrophysical phenomena to create distance indicators. One type of distance indicator, which you have likely heard of at some point or another, are standard candles. To be a standard candle, an object must have a luminosity that is expected to be the same everywhere throughout the universe. And since we know that luminosity decreases as 1 over the distance squared, then these indicators allow us to compare the absolute magnitude, or the absolute magnitude of these indicators with their apparent magnitudes as we see them, to then derive a distance from us. Some standard candles include Cepheid variable stars, who have a period luminosity relation that was discovered by Henrietta Swan-Leavitt, Meyer variable stars, Type 1a supernovae, tip of the red giant branch stars, and then J-region asymptotic giant branch stars. My project is mainly focusing on the JAGB stars, but sort of the larger scope is that as we expand our distance measurements out to cosmologically significant scales, they become rungs of a cosmic distance ladder, which serves as a basis for determining the Hubble constant, which parameterizes the expansion rate of our universe. So J-region asymptotic giant branch stars, or JAGB stars, are a subset of carbon-rich AGB stars. AGB stars are intermediate mass stars that can become carbon-rich after going through a thermally pulsing phase. During this phase, convection processes within the star result in a third dredge-up event, which for stars around 2 to 4 solar masses can cause the abundance of carbon on the stellar surface to exceed that of oxygen, therefore becoming carbon-rich. Since these stars are old enough, they've evolved through this phase, they are mainly distinguished by a red coloring. The JAGB method makes use of a color magnitude diagram. These diagrams are analogous to a Hertzsprung-Russell diagram, or HR diagram, which measures a star's temperature on the x-axis, as well as its luminosity on the y-axis. Instead of these, a color magnitude diagram uses color on the x-axis and magnitude on the y-axis. Since the magnitude of a star is related to the log of the flux, a color, which is then the difference of two magnitudes, is then related to the ratio of fluxes, which then cancels out the dependence on distance. A color magnitude diagram is also therefore more in line with what we can actually see with our eyes rather than these theoretical predictions based on temperature. But still, same rules apply where you go further left, you're bluer, you have hotter stars. Further right, you're redder, you're cooler stars, and the further up you go, the brighter you get. In addition to being distinguished by their red coloring, predictions from stellar theory have that J-region AGB stars will appear both redward of the red giant branch and brighter than the tip of the red giant branch on a color magnitude diagram. The diagram shown here is a color magnitude diagram from the Large Magellanic Cloud with each region labeled on it, and the J region here is this overdensity we see right there highlighted in green. The LMC is actually kind of important for the JAGB method, since recent studies have been conducted on detached eclipsing binary stars within the LMC, and then through analyzing their properties, a geometric distance to the LMC has been measured. And then with that, color magnitude diagram can be analyzed to then obtain an absolute magnitude for these JAGB stars. And then with an absolute magnitude being half of the equation, so to speak, for standard candles, there's now much more of a merit to measuring apparent JAGB magnitudes in other galaxies. Yes, Jose?
What are those two axes, J and JK?
Oh yeah, these are ground-based filters, I believe from 2MASS, so they correspond to just different like filters on that.
Okay.
Yeah. So the JAGB method, put very simply, first involves creating a color magnitude diagram of the data we have, then determining the J region from that color magnitude diagram, and then extracting a single apparent magnitude from that J region. Well, there we go. So the focus of my project is the M101 galaxy, or the Pinwheel Galaxy, which was discovered by Pierre Méchain in 1781. This galaxy is host to the nearest Type 1a supernova, SN 2011 FE, which makes it a perfect target for distance calibrations. M101 has been studied as a host for different distance indicators using the methods mentioned previously. And with the JAGB method being a fairly new method compared to the others, it serves an additional way of checking these different methods. But other methods aside, an apparent JAGB magnitude in M101 has already been calculated in this Lee et al. 2025 as part of the Chicago Carnegie Hubble program. The goal of my project, therefore, is to conduct a similar study of M101 using JAGB stars to better understand the uncertainties relating to the method itself. And the focus of my observation is going to be roughly down here. So the data used for this project consists of Hubble observations from the Wide Field Camera 3 using its f110 and f160 filters. There are 13 epochs of observation in total that give 13 f160 observations and 11 f110. All 13 epochs are compiled from both new and also archived Hubble observations. And the field of M101 that was observed was centered on SN 2011 FE. And each observation contains, on average, around 62,000 stars, totaling to 103,000 stars across the full overlapping region. Then prior to this project, photometry and calibration had already been conducted on the data, so that the data we're working with just consists of an identification number for each of the stars, as well as instrumental magnitudes associated with each star in each epoch. Part of this project also involved searching for archival F8114 Hubble data sets on the MASS database. There's only one that was able to be found that had an overlap with our field here. But that data still needs to undergo the full reduction process, which was not within the scope of this 10 weeks. But we can still use it as a blue channel to conduct a very rough RGB color image of our M101 field. Isn't that beautiful? But since the JAGB method involves the creation of a color magnitude diagram to isolate the J region stars by separating those redder and bluer stars, we have to consider the effect of the Hubble filters that we are using. In fact, this is the first work to utilize both F110 and F160 filters for the purposes of the JAGB method. However, as you can see here, the transmission functions of these F110 and F160 filters are fairly close together. Something like the ground-based filters from 2MASS, as seen here, the J and H, for example, might be able to obtain a better color separation. Because when we are converting these fluxes into magnitudes, these two band passes will give similar results, and therefore less of a distinction between colors that you might expect with band passes that are further separated. But now we have that data, we can form a color magnitude diagram. So since the JAGB method only requires the detection of a single apparent magnitude from a sample of JAGB stars, only a single epoch of observation is technically needed. Other distance indicators like Cepheids or Miras, which are based on a period luminosity relation, will require enough of a baseline to best examine their light curves and therefore use them as distance indicators. However, JAGB stars themselves are actually variable stars, so we consider a time-averaged color magnitude diagram that is composed of the average magnitudes of each star across all the observations in which they appear. Then, since we are using F110 and F160, again, we don't see as much of that overdensity that we saw on that LMC plot. But if we plot the full distribution of magnitudes over here, we see that there are two kind of overdensities that we observe. This larger one down here is mainly comprised of all the dimmer stars that exist down here. But we're particularly interested in this sort of higher up one that is picking up a lot of these brighter stars. So now the question is, where is the J region? So from that plot, we now have sort of a rough estimate of the magnitude bounds of the JAGB stars. So now we need to test various estimates of the bounds of this J region to see what we get. And to reiterate, we'd expect that the JAGB stars will be redder than the red giant branch and brighter than the tip of the red giant branch. However, finding where the tip of the red giant branch is requires an edge detection method, which was not within the scope of this project either. So instead, we wanted to test how sensitive our analysis was to our estimated bounds through defining 5 estimated boxes to encompass the J region. So we started with the largest possible guess, which has lower bounds of the median color and median magnitude of the full star sample. The upper bound of this box was taken to be 21 mag, and on the magnitude axis, and 1.63 on the color axis, which is 0.75 mag larger than the median color. And by setting these bounds, we're ensuring that we're capturing enough of these brighter stars while also sampling enough into the full distribution to get enough of the redder stars. Next, we refine these boxes to be more in line with that smaller overdensity that we saw. The box that we consider to be the best estimate has magnitude bounds matching those of the overdensity, as shown by the gray bar still. And then the color bounds for this box were chosen to be 1.5 mag and 1.1 and 1.5. This, again, just ensured that we were sampling enough into the red stars without dipping too far into the extreme red, which would fall outside of the J region. Then boxes 3 through 5 were then slight variations of this best estimate box, with each box expanding out 0.05 mag on every side from the one before. So between that best estimate box and box 5 down here, there's a 0.15 expansion on the bounds on every side. So with these boxes defined, we can then look into extracting an apparent magnitude from each of them. When it comes to extracting a single apparent magnitude from the JAGB stars, you're essentially smoothing over the variations between them to converge to a representative magnitude of all of them. This can be done by calculating the mean, the median, or the mode of the distribution, or of the stars within that J region. For this work, we mainly focused on the modal magnitude of the histogram that was made, of that magnitude histogram. This is just more in line with what has been done in the literature. But in any case, it should be noted that the histograms were made using a bin size of 0.01 mag, meaning that there is a noticeable amount of fluctuations within the histogram itself. This is actually an example from, I believe, box 4. That's not really important. So to counter this, we adopted a Gaussian windowed, locally weighted regression smoother, or a GLOS smoother, to then reduce this noise. Very simply, the GLOS smoothing works by iterating through the center of every bin in the histogram and looking at the surrounding bins within a window defined by a chosen smoothing parameter. Then all the points within this window are assigned weights to them based on their proximity to the central bin, as they would fall in a Gaussian distribution. So bins closer to the central bin are weighted more than those further away. And after the values of each surrounding bin have been weighted, they're fit with a local second-degree polynomial, and the value of that central bin on that polynomial then becomes its smoothed value. And this then iterates through all of the bins, and you're left with a smoothed histogram. We tested a range of smoothing parameters from 0.1 to 0.4 in steps of 0.05. And for this work, we chose to use this sort of median value of 0.25, which follows other studies that have been done in the literature. But also, from our test on that best estimate box, we found that the peak of each smooth histogram varied by around 0.2 magnitude, depending on the smoothing parameter that we picked. So taking the modal magnitude of the J region to be the peak of this smooth histogram for each estimated region, we get the following modal magnitudes for each box. And if we use our best estimate box to be our preliminary apparent magnitude, we report a value of 23.32 mag with a 0.2 mag uncertainty associated with the choice of region, which mainly from these four boxes, these four variations. And then we have that uncertainty associated with the choice of smoothing parameter at 0.2 mag as well. But for the JAGB method to be properly used as part of this larger goal of achieving a distance to M101, as well as maybe be used in a cosmic distance ladder, the uncertainties within the measurement need to be understood significantly more. You're trying to convince people you know the expansion rate of the universe. You need to be sure of your answer. So our next steps are mainly looking into sort of that method and the choices we made along the way. So the first one would be to try not using that smoothing technique at all and just see what happens if we just detect the mode of that J region and how that value comes out, as well as look into detecting the mean or the median instead of the mode. We also, in the data, there's also photometric uncertainties that were not considered here. So those would definitely be, those are associated with the magnitudes of each star that make up the color magnitude diagram. So factoring in those uncertainties would likely have an effect. And then we also have that F8114 data. We can then create another color magnitude diagram to then just use as a reference. So to summarize, this project analyzed F110 and F160 data for the M101 field surrounding the supernova SN 2011 FE. From a color magnitude diagram made using this data, we report a best estimate of the J region of these bounds. Then from this region, we used a glow smoothing on the J region to extract a preliminary modal magnitude with uncertainties associated with the choice of J region as well as the smoothing parameter. With the ultimate goal of using this JAGB method as a means of measuring a distance to M101, we must investigate the uncertainties significantly more. Then we'll be able to factor in an absolute magnitude as well as all the uncertainties with that to then obtain a distance modulus and therefore a estimated distance to M101. I'd like to thank everyone that has helped me with this project along the way. First and foremost, Caroline, then Jonathan and Matt for advice on papers, Randall Smith, as well as his research group for all of their scientific advice, everyone back home who told me that I would regret not coming here this summer, and all the CASRA students, as well as specifically the AstroREU. You guys mean the world to me, and this summer's been amazing, and it's because of you guys. Thank you.
We have a question from Gabi.
Yes, Gabi.
Amazing job.
Thank you, Gabi.
So where would this fall on the cosmic distance ladder? Can this probe like farther than Cepheid variables, or is it just like an extra check?
I'm glad you asked that. So I have this slide here.
Who fixes it?
Yes. So this is the cosmic distance ladder. This is from Reese 2022. So the JAGB stars primarily fall within this like intermediate rung here, sort of existing as kind of a substitute for these Cepheid variables to then calibrate distances to the supernovae to then move on to this sort of last rung here. But And JAGB stars would fall within this middle rung here. That's your question. Thank you.
Now, you explained very well that you need to do a lot more fancy math, a lot more statistics
Yes.
to quantify your uncertainty. However, just based off of your plus or minus 0.2 magnitudes, what Hubble constant do you get, and what are your uncertainties, quote unquote?
I do not know.
Oh, okay. All right.
That requires, because that again requires that like you use that distance function you get to then calibrate other stars, and then there's a whole another step to the process to then work that out. So
Gotcha.
I have no idea.
Not there yet. No worries.
Okay, one more question, yeah?
Yeah, thank you for the talk. I have a very silly question. What makes JAGB stars standard candles? Why are they constant magnitude?
Yeah, so from my understanding of them, what makes them useful is that when we look at them, hold on, where is it? It's here somewhere. Yeah, so when we look at them using like the J-band like magnitudes, we see that this region here is pretty like consistent. It's very like boxed, if that makes sense. If you were to plot it with other bands, you would get more of a sort of a curve to it. But using the J-band, which is more near infrared, you'd get this fairly consistent apparent magnitude,
So,
I believe.
is it observational effect we see, or is it something we expect from the period of the stars?
So you said the period of these?
The theory.
Oh, the theory.
Is it do we like them because of theory or because of observation?
That's a good question. I don't know how to answer that specifically, I guess.
I would say we don't have a good theory of J region.
Yeah, I'm honestly not too sure how to answer that, unfortunately.
Thank you.
All right. Yes. Let's thank Andy again. And for our final AstroREU talk, get up and get ready.
You got the timer here.
So now I've got to do the intro first, Carmen. Yeah, so I'm very happy to introduce Carmen Galmes Altafulla, who is from Santa Cruz. So jumping all the way from the East Coast to the West Coast for our last two talks. And Carmen's been working with Rosanna DiStefano, who unfortunately can't be here today because she's not well, but hopefully she's zooming in. And Carmen's been working on microlensing and looking for binaries in microlensing. So Carmen, all yours.
Hello, my name is Carmen Galmes Altafulla. I have the pleasure of being advised by Rosanna DiStefano.
Mike.
Being advised by Rosanna DiStefano in collaboration with the Rubin microlensing group, who's a great little group that looks for binaries in microlensing. So what is gravitational microlensing? I want to start by defining this. So imagine you have an object, and that object has a magnifying lens going over it. You're going to see it bend more light towards you and then bend less light as it moves past. And it'll create a weird little effect. And I made this myself. I'm very proud of it. If you're up close, you might see this effect. And if you're far away, you might just see a little bit more yellow and then a little bit less yellow. And that's kind of how our telescopes see it. This is a more accurate view of microlensing as one star passes behind another star. And that star's gravity will bend more light into the viewer's eyes. But usually our telescopes can't really see this effect of it going around the bottom and making a little Einstein ring. So we just see a point, or we just see a curve like this where it goes up and then down. And this is a very good example of a single point source, single lens light curve where it's very symmetrical. It just goes up and down. There's not really any variation in it. But we can read this curve and then read different curves that have a little bit more variation to figure out what's behind them and see what's actually going on. And we can actually use that to find exoplanets, which 700 have been found so far with microlensing, because it'll cause like a little bump in there. What's really important about microlensing also is that it's entirely random and indiscriminate, meaning that if we figure out how to read these curves, it's an entirely new way of looking at the universe that's not just staring at it with telescopes. And it can zoom in completely on star systems and all the intricacies of them that we can't see with our current telescope capabilities. But I'm concerned with binary source microlensing in specific, of which there's not really a lot of it in the data. We can see this one from Jung et al. 2018, which is two sources passing behind one lens. And they're not even rotating around each other. They're just passing by. So of binary systems, this is a very simple one. And it just causes a little extra bump in the light curve there. So even though binaries make up about 30% of all star systems, why don't we see them? Are we not looking for them? Are people who do surveys of them just throwing them out because they don't look like good microlensing curves? Do they not show up in the data for some reason? Are there other outside biases? We really haven't studied this enough to know. So, dude, where are my binaries? I'm trying to find them. And how can we figure out how many binaries we should be seeing? If we can model a wide range of binary source systems, we can figure out how many different light curves influenced by a binary source can look. We can find out how many different light curves influenced by a binary source can look and how different they can appear to the naked eye and also to a computer. On the right here, I've modeled 9 binary sources with going down, there's a smaller radius, and going to the left, there's a smaller period. And with these, it can show an example of a binary curve. And this is also the simplest case where there's one dark star and one bright star, which happens when there's a white dwarf orbiting a larger star. So we can take many of these and compare them to a single light source, single lens curve to quantify the difference and tell how many of these we should be seeing. In this case, we've chosen Chebyshev polynomials, which are really useful for modeling light curves because they start and end at the same point. And these are a set of orthogonal polynomials that can be expanded to any function, similar to Fourier series or Legendre polynomials. And to quantify these differences between light curves, we can take all of the coefficients of all of the polynomials from one light curve and from another light curve, and then find the differences between them and square them so they're all positive and such. And also make sure they're normalized so that if you have a bigger light curve than another one, but they look the same, you don't get a big difference. And this way, we can really quantify those differences and really tell if we should be observing them or not. So here's the same example used before, but I've calculated the differences between a single lens, single source curve, which you can see this one looks very similar to a single lens, single source curve, and it has quite a small d squared. And then over here, there's the differences between each other so that we can tell when they're very close, they should have similar parameters or similar looking light curves. And this is still considering the simplest case and the same figure. So this is a more complicated example where I've taken into account, instead of just period and radius and one star, I've taken 2 stars and have a mass ratio between the 2 stars, the total mass of the system, and a separation between both the binary stars. And I've taken them and made light curves out of them, and then calculated their Chebyshev fits, plotted the Chebyshev fit also in green, and then taken the difference between them. And you can see this one looks very, very different from a point source, and it has quite a large d squared. And this one looks very, very similar, would be basically indistinguishable from a single single lens, single source curve, especially with the error that a telescope adds. And it, of course, has a very small d squared. And so this is when you vary a lot of total masses and separation of the binaries and take it at different mass ratios. So for a mass ratio of 1, which means that both the binaries are the same, or both the stars in the binary are the same size, you get this very optimistic view of the d squareds, meaning that at about 10 to the negative 0.1, we should be able to see them basically all of them. So that means that a good area between above 1.0 separation, we can see basically all of these binaries, or we should be able to. Of course, for a smaller mass ratio, there's a lot less to be seen and a lot less optimistic, but that's to be expected because the system would have less variation. And looking ahead, there's of course a lot more that can be done in here because I've taken a very simple case where we've only considered binaries that are facing on. We can still consider binaries that are inclined in relation to us, binaries where, or systems where there are stars in the view of the pixel that we're looking at. So there's like extra light infiltrating our curve. Triple body systems, higher order systems, and binary lens, binary source systems, which should also take up a small amount of the curves that we're looking at. Future telescopes are also going to greatly expand the amount of microlensing events that we can see. We have the Rubin Observatory and the Roman Observatory, which I didn't mean to. The Rubin and Roman observatories, which Rubin will be looking and taking big videos of the sky every couple of days, and the Roman Observatory should be looking at the sky every 15 minutes or so. So they're going to greatly increase the amount of microlensing events that we can look at and that we can sample from to really know if our rate matches up with our expected, or with our observation. And then this will be me after lunch of Roman and Rubin. I found my binaries, or maybe not. Who knows? It's a very exciting time to be studying microlensing because of this, and I'm very excited to see how it will change and evolve. And so acknowledgements. I want to acknowledge Rosanne DiStefano for being my mentor and the Roman Rubin microlensing group, Jonathan and Matt Ashby and everybody running the REU program, my mom for being my first astronomy teacher, all of the AstroREU interns and CEERS interns, my friends at home, and my partner who's in the audience. And there's bibliography. And this is all the microlensing events recorded by Gaia from 2014 to 2018. And that's it.
Thank you, Carmen. Questions? Zach?
Yes. Is there any advantage to taking the differences of the coefficients of the Chebyshev polynomials as opposed to separating it into points and then taking like chi-square difference?
The way that we've done this is just because taking the chi-square difference would be definitely difficult if it was like a bigger curve that was magnified by some number. So like if you have a point source polar lens that's small versus a big one, they have different closest approach to their lens. Then one will obviously have a much larger separation from the other one, but they will be essentially the same curve. You know, so taking the coefficients instead and normalizing them is a much better way to look at it.
I was wondering, great talk, when you were calculating your d squared, you mentioned that you were normalizing, so I was wondering if there's any advantage to, and then you later mentioned like cutoffs or binning, so if this data is all normalized, are there any trends that you see in higher or lower intensities that might be useful to consider, or is it all kind of similar?
We normalize it as in all of them start with 1, so like we've divided the entire coefficient space by the first coefficient. I don't know what you mean by binning or like different energies because we're all looking in like optical basically. But yeah, normalizing just means like if you have a big old curve, it's going to have the same kind of shape of the Chebyshev. So we want to normalize that so that they look the same.
Okay, yeah, thank you.
Any more? Yes.
I'll ask in the interim. So You were talking about how the d squared needed to be, I believe, higher or lower than a certain value for a strong detection, but you've normalized everything. So how do you take into account that the amplitudes should be different, and that might influence your ability to detect with a telescope?
Well, the normalizing takes into account that the amplitudes are different, meaning
Right.
that if you have a bigger curve with and it still looks like a point source point lens, it should have the same Chebyshev expansion as one that is smaller and is still a point source point lens. And wait, what was the beginning of your question?
You had a plot that was showing the d squared versus separation distance, and that you said that we should be able to detect sources with a a lower d squared than a certain value.
And we don't know that value yet. That needs more.
Right.
That needs more.
And I think maybe what's going on here is, I mean, what you're really asking, right, is if I had infinitely good observations, would I be able to tell the difference between a binary and a single source?
Oh, okay.
Right? And whether you can detect the thing at all and get good signal to noise is a different question from, even if I had perfect data, right, I still can't tell whether it's a binary or not because the two things are too close together, right? I think that's what's, if I interpret the question and the answer.
Yeah, that was a good answer. Thank you.
If there are no more questions, I will declare my final 32nd year of the REU program done. I want to say how incredibly proud I am of the students this year. You've worked so hard. You've done fantastically. And you've been a pleasure to hang out with. So thank you again. Thank you everyone for coming.
Let's all thank Jonathan.
I just want to acknowledge Margaret hiding in the back there, who's an alum of the program from what year, Margaret?
1999.
1999, and still here at the CFA. We haven't scared her away yet. So thanks everyone. We are going to take a break and then come back for the CREATE team. And then ASTRO students, let's strategize about dinner.
Yeah.
This year's CREATE symposium, where we're going to have all of the CREATE interns give a 15 minutes plus 5 to questions presentation. They've already rehearsed their presentations at least twice. Some people have given an extra presentation on top of that. So they should be pretty good on the timing, and they should be pretty great. Let me tell you a little bit about the CREATE program if you don't know about it. CREATE is an acronym. It's not as difficult as the other acronyms like mayonnaise, which we'll hear about later. It is an easy acronym. It stands for the CFA, so it's got an acronym in the acronym. That happens sometimes. CFA research experiences in astronomy, technology, and engineering. So we have the AstroREU that we heard earlier today. We have the Solar REU that we heard yesterday, and the Boy program that we heard yesterday as well. And then we also had the Astro AI and Earth AI interns, and we had the Black Hole Explorers, and so many groups, so many acronyms. This group is really intended to bring together the different aspects of science and engineering that we do here, and technology that we do here at the CFA, that doesn't have a dedicated program for a very specific task. So we have Astro. Some of our students are mechanical engineers, some of them are computer scientists. We don't recruit just astronomy majors because we need people that are not just astronomy majors. So it's one of the reasons why the CREATE program is called CREATE, and also the objective of that program is to bring in more of the talent that we need to get experience here at the center so that they could potentially maybe contribute to future projects in the future with their respective backgrounds. The CREATE program is run by myself and a whole bunch of people who help out behind the scenes, who often don't get enough credit. People like Catherine Murphy, people like Tina, I'm going to butcher her last name, in the director's office, so I just won't say it, who really help out with all of the logistical planning for all the students to bring them here and to set up their stipends and do everything, stuff that is way beyond my pay grade, even though I'm a scientist here, but we couldn't do without the support of the administrative staff. We also couldn't do without the support of the National Museum of the American Latino, who funds the program in its entirety, with some support from our partner organizations and from the director's office as well. The way the program works is that we partner with institutions across the United States. Typically, it was usually just in Massachusetts, but now that we have dormitory housing, we've brought in that pool. We included a lot of schools in San Antonio, and we also have, so we have 2 partners in San Antonio College, University of Texas in San Antonio, and we also have a partner in Worcester, Massachusetts, Worcester State University. So we recruit exclusively from those programs because they have the students that we want, who are the students studying these different majors that you'll hear from. So I have 1 minute left to just say that this crop of students has been really great to get to know and really great to see grow in the program. And I'm really excited for you all to be able to listen to them today, give their presentations on their various topics. So thank you again for joining us, and we're going to start with Jessica.
What's up?
All right, hello, my name is Jessica Joyner. I am a CREATE intern, just as Rudy introduced. I am a student at San Antonio College. However, this fall I will be transferring to the University of Texas at San Antonio. I'm majoring in mechanical engineering. And this summer I have been right across the street at the receiver lab for the SMA. And I'm gonna tell you about how we make motors go and stop. So today I'll be talking about the precision control system for calibration and polarization of the submillimeter array. So the first question we have to ask is, what even is the submillimeter array? Well, it's actually a series of 8 radio telescopes that work together as an interferometer, which basically means it combines all the signals together from all the telescopes to produce a really sharp and high resolution image. It's located near the summit of Mauna Kea. That's because the higher you go, the less moisture you get in the atmosphere. Moisture can scatter your radio waves and make weaker signals. So farther you get from moisture, the better your results end up being. It makes observations on the submillimeter wavelengths. This means that the wavelengths are short enough to be able to penetrate through dust and gas clouds. So usually a lot of this stuff would get blocked. Visible light would get blocked through these things, but since they're so short, they could penetrate.
And it can reveal hidden cosmic structures, just meaning we can observe protoplanetary disk, star formation, galaxies, and black holes, supermassive black holes. So the SMA was a key component of the Event Horizon Telescope. It was one of many telescopes around the world that was able to get a photo of, as we see, Sagittarius A and M87. Right around there, you see those wispy lines around. That is actually the magnetic field. Since the SMA and all these other telescopes can polarize, that means we can reveal magnetic fields. That basically reveals the other half of the picture you're looking for. So it creates depth for the image and shows how everything interacts with each other. So I'm in charge of one instrument that is in charge of two separate controls. It is calibration and polarization. Now, calibrating, this is something we have to do with every instrument. One way you can do it with a thermometer is using the ice point method. What you'll do is create a very specific condition called ice point, where you put a bunch of ice and then some water, put more ice, and you get it to the point where the ice is at, where the environment is at equilibrium, meaning that the ice is melting at an equal rate as the water is freezing. This means that the temperature that should be read back to you is 32 degrees Fahrenheit or 0 degrees Celsius. Now, if you dip your thermometer in there and it reads something else other than 32 degrees, then that's how you know your thermometer is off. So next time you go into a room to make a measurement of the temperature, you know to add or subtract from the measurement that you got from your calibration. Now, how does this connect to the ambient load assembly? Well, here, this is one instrument used on the ambient load assembly. It's called the ambient load. This is just for polarization. It sets the correct gain and temperature scale for the telescope. It is at a constant room temperature, so 300 Kelvin. So the ambient load is a perfect absorber. It is made of EcoZorb, which is a multi-layer absorber. And since it is a perfect absorber, it can also emit perfectly as well. And it is in charge of, calibrating the brightness of the objects that you're looking at. In radio astronomy, temperature is related to how much microwave radiation is being emitted from objects. So whenever you point up at a certain level in the sky and you are getting 60 degrees Kelvin, you don't actually know if it's actually 60 degrees. So you make the receiver read the ambient load, and then it'll tell you how far off it is from 300 Kelvin, and you know to compare it to the source you're looking at in the sky and to add it and subtract it from there. So another thing that my instrument does is polarization. We have polarization in something really cool with 3D glasses. So in older model 3D glasses, what would happen is that the projector would project two images at the same time, which is why whenever you're watching a 3D movie, if you take off the glasses, it looks really blurry and weird. It's because it's presenting two separate images at a shift. So one is presenting linear polarized light, and the other one is presenting horizontally polarized light, or vertically and horizontal. And each lens corresponds with the image that's being projected. So your brain will receive these images at the same time, and then you'll get a 3D image you'll perceive a 3D image. However, with linear polarizers, they can only work if you are sitting completely upright or completely horizontal. So another way we also do it now with more modern 3D glasses is with circular polarization. You have one screen that's polarized counterclockwise, and then one screen that's polarized clockwise, and then you have your corresponding lenses, and now the user can perceive a 3D image at any angle that they want. So we use polarization with these polarized quarter wave plates. We have two of them. Each of them each wave plate corresponds to a certain frequency of the beam that you're trying to receive, so you just use one at a time. The SMA receives circularly polarized light. This is great because circularly polarized light, it could tell you the handedness of your electric field that you're receiving. However, the receiver on the SMA only allows linearly polarized light to come in. So how do we make this transition? Well, we use the wave plates. It will be tilted at a 45-degree angle. What this will do is add a phase shift to your circularly polarized light and shift it and turn it into linearly polarized light so that so that the receiver can fully receive it now. These wave plates are very important because it does expose the magnetic fields of the structures that you are looking at. Now, let me see. So altogether, this is what the instrument looks like. I would say it's about toaster size, maybe. So you have your 2 quarter wave plates right there, and as you can see right here, so they're all placed upon 3 different tracks. So they have 3 translational motors, 1 motor for each instrument, and then you have 2 translational motors right here for your wave plates, since the wave plates do rotate at a certain angle. And right over here, we have the Arduino, which is the brain of the entire system. It tells the motors how to operate and the speed and the velocity at which they should move forward. So now we have all the components there. Now how do we actually communicate them with the Arduino? Well, we have our motor controls. There are a bunch of different parts of motor controls. So the motors that are used on the load assembly, we use DC motors. That stands for the direct current motor. A lot of motors in your instrumentation use stepper motors. However, this one relies completely on the current that in order to tell it to stop or to go. Stepper motors don't act the same way. This one is fully reliant on the current. Again, you have your Arduino right here that communicates with all these components. And then you have something called a PWM pin. This is called pulse width modulation. It acts like a trap door in a sense. So with these DC motors and this Arduino, what we do is we don't change the voltage to speed it up and slow it down. We keep a consistent voltage the entire time. Now, if we want to speed it up and slow it down, we have to trick the Arduino a bit. So if we want the motor to speed up, then the trapdoor will open and it'll allow the voltage to pass through for longer periods of time. And if we want the motor to slow down, then we'll close the trapdoor more often, not allowing the voltage to go through as much. And the Arduino will think that we're giving it a lower voltage, when in reality, that's not what's actually happening. But it will still result in the motor speeding up and slowing down. Right here, we also have the encoder pins. This provides feedback on the position and the direction for precision control. This basically tells us our position, and with that, we can figure out if it's actually landing in the correct spot or not, or if it's overshooting. Not indicated here on this motor is flags and limit switches. So when we had created this whole system earlier in the summer, we didn't really need a flag switch since it was just a motor that just went round and round and round. However, when you were working with the load assembly, you saw that there were tracks. It had a start point and an end point. Whenever you're working with these motors, you don't want them to push past those limits and keep going. That can just overall damage your entire system, or it could just burn out your motor. So you have your flags and limits to tell it when to stop, and it's a hard stop that it has to listen to. So now just imagine something real quick. You are in Japan right now, and you are on a bullet train going 200 miles an hour, and you see your stop coming up. It's approaching pretty quickly. Now, would you rather it go from 200 miles an hour to an instantaneous 0, or would you like to slow down and gradually meet your stop? Trick question, actually, it can't go instantaneously 200 to 0 unless you hit a wall or something. But in real life, motors don't respond immediately to what you say. So if I tell a motor to stop in a simulation, it will stop just fine. However, in real life, if I tell a motor to stop, it has to take time to actually slow down and reach its endpoint. Now, it's good and bad. It's good if you're on a bullet train and you want it to gradually slow down. It's bad if you want it to get somewhere quickly and get really precise results and you want it to stop immediately. That is something we deal with our load assembly, and we have 2 ways of fixing this. We have something starting off with PID controls. P, I, and D each stand for a different phase of our loop that we calibrate our motor through. So the P stands for proportional. What this does is that it receives the error in your position. So say you are at position 0 and you want to get to 1,000. Well, your error is at 1,000 right now. So it gets the error. The integral section adds up your error over time, And the D section, the derivative, it calculates the slope of your error. So how quickly and how slowly you are gathering these errors. Now, if we look right here, so right now we have our set point. PID controls can be used for thermometers, for your cruise control in your car. But right now we're using it for a thermometer. So the set point was right here. And when you add your P section first, so proportional, you will get your error and multiply it by a constant, and it'll look something like this. And right now we have something here called a steady state error, which means it is reaching a certain point, but it has this gap here and it can't quite reach this upper limit right here. So then it'll implement the integral section. So then it'll do proportional and integral, it'll do both parts. This time, it does end up landing at your target. However, before here, we have all these oscillations. This isn't really healthy for your motor, and also it wastes a lot of time. So then, once you add your proportional, integral, and derivatives to it, you slow down your oscillations, and you don't overshoot as much. And as you notice here, you reach your desired position even sooner compared to beforehand. So this isn't just the only solution that you need. You also need your, oh, sorry, one sec. Okay, so here is the PID working in real time. So here we have this, oh, sorry, one sec. So here we have it set up, and this is position time graph, and we have it in this weird sort of exponential almost curve. But we don't want that. Whenever you're working with motors, you want a nice S curve, something that looks more like this. However, you could see that it is reaching its targets way too soon, and it's still overshooting by a huge margin. So with adjusting the PID values at the top, you will soon reach your margin a lot sooner and a lot more cleanly. However, right here you see it still didn't quite reach its mark, which is why we do our next section, which is our trapezoidal velocity profile. So whenever you put in an input, it will run through this profile and run 3 separate equations. You put in your input, and it says, okay, it takes this amount of time to complete this transition. Now, if it takes a longer amount of time, it will have a phase dedicated just to acceleration, a phase dedicated just to cruise, and one just for deceleration. If you are just going from position 0 to 50, which is very small for the motors that we're working with, then it'll decide whether or not it even needs a cruise control section, and it can completely condense this and turn it into a triangle. That's not a good or a bad thing. It is perfectly fine if it turns into a triangle. It just means it was a really short distance. Now, both of the PID and the velocity profile work hand in hand with each other. So here, this is combining both of them together. Now here we have a motor that we worked with in the lab, and we can see right here that that was the target, and it completely overshot by like 3,000 points. So that's definitely not good, and it kept going until we had to physically tell the motor to stop going. So whenever we implement both of the PID variables and the velocity profile, you'll see a nice graph that looks like this. Your velocity profile only runs one time per iteration. So it'll choose a time to accelerate, cruise, and decelerate for your entire movement. Now here, you're gonna see a bunch of little bumps right here, and you can see them right here too. This isn't a bad thing. This is showing you that your PID loop is working. So the PID throughout this entire iteration is being called every 10 milliseconds. So you can think about it like a cat trying to chase a laser pointer. The trapezoidal velocity profile is going to be the laser pointer in this situation, and it is going to create that path that you want the cat to follow. Now, the cat isn't perfect. It's a bit jittery. It's a bit jumpy. But what it's going to do is that at every 10 milliseconds, it's going to make sure that it stays on that line. And it's going to try to stay as close to that line as possible. Now, reflections in future work. What went really well was applying all the code across different motors. Now, I personally don't really like coding, but I've learned to somewhat love it, I guess, maybe. But thankfully, the code that I needed for the translational motors, all that code worked across all of them. All I needed to do was adjust the PID variables and the acceleration and velocity for all of them, because each motor is unique. And then what was kind of hard was the logic for all the code working. Sometimes if you input 0 into an equation, it outputs undefined. So the motor reads that and it just doesn't move. With this, you just have to change the logic of the code so that it does work for every variable. And for future improvements, right now the SMA is planning on doing more solar observations. So if there were to be a solar filter to be placed into the instrument, it would be placed in the ambient load assembly, so we could take out a wave plate, replace it with the solar filter. And I'll say, thank you very much. That's the end of it.
Great, thank you, and thank you for a great talk. With those on the live chat, on the YouTube stream, if you want to ask a question, just put it in the live chat. If it shows up in time, we'll try to read it out. For those in the audience, if you have a question, just raise your hand.
Jessica, that was a fantastic talk. So can you go back to the plot where you had the PID implementing the trapezoid shape? Yes. So is it what I just said, like the PID is trying to get a trapezoid shape like in the velocity profile, or is it like you have parameterized the trapezoid and that's trying, like there are separate parameters for the PID and the trapezoid, I guess?
So they're two separate things that work hand in hand. So I would say the PID is more small term, like more smaller picture, while the trapezoidal is more big picture. So the trapezoidal will reveal the grand scheme of where it needs to go and how it needs to move. But the PID, it's going to see snapshots of every single second and adjust per snapshot. So it can be in the middle of the acceleration, the cruise, or the deceleration. It'll only see every 10 milliseconds, it'll run through, see its position, and decide how it should act from there.
Thank you very much.
Hi, Jessica. This was an amazing talk, and on this graph, I was just wondering about the position plots. What's the difference between the red and blue line?
Oh yeah, sure. So the blue line up here, that is the target right here. So up here, the target was around 500. This was for a way early iteration with a very simple motor. And then here, the target was 15,000 encoder steps. So the position here is just it achieving its S-curve, very slight, but you could see it. This just means it was working really fast, and that's the goal we're going for.
On the left, that's the previous iteration.
Yeah.
The overshot its target.
A whole by like 3,000 counts, yeah.
Did it actually go back after?
So it did go back. It required us telling it to stop and then like return back to where it was going. So whenever we're doing these, we just want the user to put in a single input and then not have to do anything else. So, yeah.
Thank you.
No problem.
We have time for one more question. If not, let's thank Jessica again. We'll do the transition to the next speaker.
I forgot to start the timer.
Test. Is that loud enough or no?
Yeah, that's good. That's good.
Oh, I can't hear myself. Do I begin? Oh, okay. Good afternoon, everybody. My name is Manuel. I am a CREATE intern visiting from the University of Texas at San Antonio. I'm a rising senior studying physics with a minor in mathematics, and over the summer I had the amazing opportunity of working with Dr. John Zuhone in a project that we were titling Spinning Hot Gas and Massive Cluster of Galaxies. And so I first want to introduce the topic by briefly summarizing what galaxy clusters are. These are one of the largest gravitationally bounded structures in the universe, anywhere contained between 100 to 1,000 galaxies. And in between these galaxies, there resides a very hot and highly diffuse gas that we refer to as the intracluster medium, or ICM for short. They are also very weakly magnetized, and they emit X-rays. And so on the right here, we have an example of a galaxy cluster, a Bell 370. And when we look into the composition of these galaxy clusters, we see that 3% of it are made up of stars from all the galaxies, and 12% of it is coming from the ICM.
And so a majority of it is coming from the dark matter that we can't see or observe. And so the only thing we can really observe here is the ICM. And so when we go into trying how to observe these massive structures, when we had the Hubble Space Telescope, this is all we could see of the optical waveband, a lot of beautiful stars, a lot of beautiful galaxies. But what we didn't know is that there was structures hidden behind them. And so when Chandra took the same picture of the night sky, we then got revealed certain structures. And so what I have here displayed is the bullet cluster, and we were able to see this in the X-rays. And so when we combine techniques such as these in observations and make a composite image and use gravitational lensing, we can start probing questions into the things that we can't observe, such as dark matter, which is what we believe is the evidence for dark matter in the blue. And so the reason why I chose this specific image is because the next slide is going to talk about galaxy cluster mergers. And so the bullet cluster is a perfect example of that, because galaxy cluster mergers are when we have two massive structures collide with one another. And these are one of the most energetic events in the universe, producing up to 10 to the 65 ergs or 10 to the 58 joules. The bullet cluster was coined the bullet cluster because we can see here, oh, I forgot I have a laser pointer. We can see here this bullet-shaped cold front and this shock front right here. These are all types of observables that we can see in the ICM. And so these are just one of the two that we can see. The other remaining one is stripped gas tails. But a certain feature that I want to specifically look at are cold fronts. And so let's first discuss what are cold fronts. And so cold fronts are formed from the bulk motions of these mergers. So you have gas of different densities and temperatures interacting with one another. And from there, they create these sharp discontinuities in their density and temperature in the hot plasma that resides in these galaxy clusters. And so when we look at this plot, the right side of these figures, this is the work of Markovich and Viklinin. We can see here a Bell 2142 shot in X-rays. They decided to take radial sections of the north portion and the south portion here. And we can see when they map the surface brightness as a function of radius in the bottom two plots here. This is the south section, this is the north section. We see that as we get closer to the dashed line here, we have this immediate drop off in the surface brightness, and then it continues on. The same is said here in the northern portion of this plot right here, and it drops off right by that dashed line. And so we can characterize these cold fronts by their surface brightness edge that separates the two regions of different densities and temperatures. And so we are able to observe cold fronts, but how do they get made? What motions or bulk motions create these types of observables that we are able to observe in these X-ray signatures? And so a way to do that is by making first an idealized simulation where we can try and make a simplified case where we can have two bodies of a lot of mass interact with one another and see what proceeds in their dynamics. And so what I have here is first the dark matter density. It's a nice little movie. And we're going to see that from on the right-hand side, they're just gravitationally interacting with each other. And this is what I want to point out, stuff that we can't see. We just know that these two objects interact with each other gravitationally. Well, what happens if we want to look into the observables, such as density, temperature, and magnetic field strength? Well, they have a lot more chaotic behaviors that we can start witnessing. And so we're seeing this in the ICM, all these three observables. And we're seeing how these structures are becoming to evolve over time. And what I want to point out is this behavior right here, this spiraling behavior. That's what we consider as sloshing, or the spinning of this hot gas. It's where we have this smaller gas core interacting with the more massive one. And so it's accelerating the gas in the main cluster core, creating these spiraling features here. And so we want to figure out, okay, well, does sloshing or the rotation of this gas affect its overall angular momentum? And if so, how else can we measure it or figure out if it is changing the entire system? And so another thing I want to add is that this is a very controlled experiment. We can control the parameters, and this is a way for us to simplify the problem that we're looking at. But what if we want to look at it at a much more cosmological scale? What if we want to make a movie that can kind of display the complexities that create these massive large-scale structures? And so here I have a movie playing from the Illustris TNG team. This is showing how the formation of these galaxy clusters are being made, and they are showing about 300 of the halos that I'm going to be working with. I only work with a sub data set of them, only about 10 of them. And they're showing from 500 million years after the Big Bang, and they're progressively going towards present time. And so I want everyone just to get lost, and I want to hear oohs and ahs for this movie, okay? Because the first time I've seen this, I didn't even know we could make this type of thing. Thank you. You still got 5 seconds. I need to hear more oohs and ahs, okay? And so, one I want to point out, you can start seeing these massive structures beginning to form. Those are the galaxy clusters that we want to look into. And so the most massive one is this one right here. That's Halo 0. So we have about 300 of these. And so they go from 0 to 300, each going with a smaller mass. And so 0 being the largest. And so I first wanted to say, well, why do we care about these large-scale structures? Well, we want to first figure out if there's any evidence for non-thermal pressure support. What prevents these huge structures from collapsing into one another? Right now, we believe that they're all thermal pressure supported, but what about the rotation and the acceleration of these gases? Do they help prevent it from also gravitationally collapsing? We also want to see how these galaxy mergers became. See if we can trace back to the steps and figure out if the angular momentum of these gas structures can then reflect their merger history of the cluster. And then later on, hopefully, oh, sorry, that was a spoiler. Later on, figure out maybe we can detect gas-galaxy misalignment that could help further probe into the question of identifying dark matter, or at least finding other pieces of evidence for dark matter. And so, how do we try measuring the spinning hot gas? And so we have this amazing way to analyze and visualize volumetric data. It's provided by YT. This helps us take our cosmological simulations and create plots of these, gather information from these simulations, such as density, temperature, and magnetic field strength. And earlier, when I showed you the idealized simulations, they're a lot more simplified. We were very easily able to see the spiraling structures that were creating these discontinuities between the density and temperature profiles, but here there's a lot more stuff going on. Now there's AGN feedback, there's maybe multiple clusters interacting with each other, there's things falling in, falling out, so they're a lot harder to analyze since we're taking this at a cosmological level now. And so what we can try doing, luckily with YT, is we can take our simulated data and we can actually gather the angular momentums from them and see how they change over time. And so on the plot on the left here, I'm showing how the angular momentum vector is changing in direction relative to the first initial measurement. And so we're just seeing how this angular momentum vector is changing over across multiple radii. And we can see that there's a couple of differences between each halo. Halo 0 is the very first one. We can see it has very minor changes in its angular momentum. But if we take something like Halo 2 in the green, we can see it jumping almost very rigidly. I'm hoping that's a word. And it's showing a lot of different behaviors that isn't as smooth as the biggest one in our system. And so when we look at it in the angular momentum versus radius plot on the right-hand side here, we're just adding up all the angular momentum, just seeing how it's, I guess in other words, spinning. As we get into larger radii from the cluster core, we're seeing that we have a very smooth increase in angular momentum. And with the Halo 2 that we saw, Halo 2 that we saw here, it also produces the same types of chaotic behavior. And so what can we assume from these two plots? We can then say that large deviations suggest a chaotic merger history, while smaller deviations imply a more coherent and relaxed structure. And so this is kind of like a cheat code because we're able to gather the angular momentums from our simulations. But when we take actual observations, we're not able to do that. The only thing we can really do is go off by the Doppler shifts and within emission lines that are being produced by the hot gas. And so what we try doing here is trying to mimic the same thing, where we take the Doppler shift effect of the emission lines on the hot gas and try and project a velocity profile that's along the line of sight. And so we can try and see maybe the rotations that are going on in these systems. And so what I have here is I chose Halo 0 as our first one to look at and Halo 2 to compare it with. And so we can see here that the red is the gas moving away from the observer, and the blue is the gas moving towards the observer. So we're kind of seeing this rotation around its rotational plane. And we can see that as we go from the center and we start going radially outward, we're seeing that there's almost no change at all across the entire system. It's pretty coherent, it's pretty relaxed, and so that can tell us that the stable angular momentum vector is having a much more relaxed merger history. And so this is just saying that it's following its flow. Nothing's disturbing this system. It's much more just these two things are merging, and they're having this coherent flow of gas. While we compare it to Halo 2, there's a lot more things going on, and as we keep going further out from the cluster core, now we enter into different things that are going on. The angular momentum vector is changing very rapidly in each one, and we're seeing different behaviors and different turbulent flow as we go out. And so we can then imply that, well, the changing angular momentum vector is deviating a lot. We can then imply that it's a very chaotic merger history. And so what we can then do is that we can then try and compare this to actual observations that are going to be taken by CRISM or other space telescopes that are able to measure these radial velocities and see if we can maybe help in terms of comparing how our simulations compare to actual observations. And so in conclusion, I just want to say that by analyzing simulations, we can gain insight into the merger histories of galaxy clusters. I generated 10 halos, and they all contain the same velocity profiles along with their volumetric data sets. We want to increase this to the 300 that were actually contained in the simulation, create a much more statistical, I guess, model that can tell us how these galaxy structures are, or these large-scale structures are performing or developing over time. We then want to hopefully gain a better understanding of why these structures are changing the way they are dynamically. And that is about all I have. And so I just want to say thank you again to my mentor, Dr. John Zujon, Dr. Rodolfo Montes, and CREATE program for bringing me out here, Center for Astrophysics, and the coffee machine in the lobby. Thank you so much.
Thank you, man. Do we have any questions in the audience?
No questions.
We got a couple of shout outs in the live chat. One for you,
Oh.
one for you, Jess. From Alfonso and from Lizette.
No.
Hi, amazing talk, and I just had a quick question.
Yeah.
A halo is just a galaxy, right?
No, that's the cluster core. So we just say dark matter halo because that's the whole entire system. And then within that halo, we see the galaxy cluster with all its mass and stuff. We just know that the halo, the dark matter has most of the mass in it. And so everything else is very small to us. And so it rotates around its halo, or within its halo.
Galaxy cluster that includes dark matter.
Yes.
Thank you so much. Oh no.
You can repeat the question and so we have it on record.
Wait, so I repeat the question?
Yeah.
What was the question?
Oh, so yeah, the question was, what is a halo? Yeah, the halo is, well, Manny told me the halo is like basically a galaxy cluster that has dark matter in it. That's all I know.
Thank you. Sorry about that. Any additional questions from the audience? I have one for you.
Okay.
What was the most difficult part of your research this summer?
Most difficult part will probably be the learning curve of learning how to apply different, I guess, packages in Python, such as YT. My mentor was a big contributor to this program, so it helped that knowing that if I had a question, he could answer it. But it also was like, so I just come for you the documentation, and like, if I ever had an issue, he would kind of like really easily, oh, this is how you do it. And so I like that aspect, but also I am also one that wants to like also learn how to do it. And so I'll kind of like not ask him sometimes, because I wanted to learn through experience how to create these plots and create these maps that we see now. And so probably just the learning curve of those packages.
Is YT on GitHub?
On GitHub. It is a website. Like it's.
Like, could you contribute to the comments, to the documentation? The things that you were asking, were they things that needed to be documented?
No, they already were. It was more of him to like kind of just, this is how we go through this first step. This is kind of like a practice exercise to get more well-rounded with YT. And he really had most of the solutions. It just became like, how do we use these solutions to help us go towards the progression of this project?
Cool.
Mm-hmm.
So yeah, in this plot, you have like a changing angular momentum vector, and that kind of correlates to the merger being more chaotic. Is there any factors that comes to play that affects the angular momentum and makes it changing? And also for like the halo 0 case, there's a stable angular momentum vector. Is this just like in the simulations you're changing like the angular momentum and seeing what happens, or is there a factor that causes the change of angular momentum?
That's a great question. So Halo 0 was like, we would consider the biggest disappointment in our data set because it's the most massive one. And so we were hoping to see a lot more changes within its angular momentum vector. But in terms of the simulation, at least the way it was explained to me is that the parameters are set and we let the simulation play. It's whatever happens after that, we then can have timestamps to then say, hey, by the way, at this giga year, this is when the mergers were happening. And from there, we can take volumetric data sets from that time period. Sorry, what was the other part of the question? It was.
Oh, that's basically the whole question.
Oh, I'm sorry.
That explains it well. Thank you so much.
Good. We have time for one more question.
Oh my God.
You have a dying question about galaxy clusters. Now is the time to ask somebody who's been studying them all summer. Go ahead.
So I guess I remember in my undergraduate studies, there's like a scenario where you have two galaxies that's close by, and before they even start to merge, they have some kind of effects on each other. Do you see any of that in like the simulations before they start to merge? Like, is it like any, I don't know, just general like effects or like any kind of interesting things that happens before they merge?
So you have amazing questions. By the way, D-Rod. So I didn't specifically look at the galaxies or the stars, but one thing that we are talking about in terms of our future work is that we're trying to think, I said it earlier in our Why Do We Care part, this detect gas and galaxy misalignment. And so we can actually map the stars and galaxies in our simulations, and from there see that when these mergers interact with each other, the scales are so large that the galaxies actually don't collide with one another. And so they pass by each other. But the thing is that the gas actually collides with one another. And so we have this misalignment between the two structures. And so later on, we do plan on creating misalignment maps to show how the gas and galaxy are both interacting differently and better display this misalignment.
Thank you.
Very cool. Let's thank Manny again. We have one more speaker for the first session, and then we'll have a refreshments break at 3:20. And then we will continue with the rest of the program after that.
There. Then you can adjust it the way you want it to.
So, don't forget to take it off.
Let me clip this one.
Testing, testing. Is that good?
That's good. That's good.
Okay, perfect. Okay. Hello, everyone. My name is Petrac Meli. I am a rising senior at Worcester State University studying computer science. And this summer, I've had the pleasure of working with Dr. Adam Foster and Dr. Priyanka Chakraborty on optimizing the AtomDB charge exchange model. So what is charge exchange? Well, charge exchange is when you have a donor atom, typically neutral hydrogen or helium, because those are the most abundant elements in the universe. And then you have an ionized atom, and for our cases, up until iron. And they collide at some velocity. And so when they collide, the electron from our donor atom gets sent to the ionized atom in some state. And then as this electron cascades down to the lowest available state, it'll release a photon or multiple photons at some energy. Excuse me. So where it gets caught in what state is decided via its cross-section. So the cross-section is the probability that the electron will get caught in that state. And so let's assume that our electron gets caught at this state right here. This state can cascade down all the way to ground via this path and release an electron at some energy. But now let's assume it gets caught over here. Well, now it has to go through multiple states, and through each state, it releases its own individual photon at some energy. And so you'll end up getting different lines depending on what state it gets captured in. But why do we care about charge exchange? Well, this phenomenon happens where there is cold gas and hot ions interacting. So a big example is the solar wind around the Earth's atmosphere. Another example would be solar wind going towards Jupiter, and its magnetosphere captures those charges, sends it to its poles, and in the X-ray we are able to observe an aurora. And we're also able to observe it in supernovae explosions, where the hot ions from the explosion interact with the cold interstellar medium. But what is the history of this ACX2 model? Well, it started off with ACX1. This one helped solve the mystery of the diffuse soft X-ray background. And so a paper in 2014 titled Resolving the Origin of the Diffuse Soft X-ray Background. We can see here in this graph, which is the surface brightness as a function of wavelength. We have our data right here from the DXS spectral data, and you'll see this red fit right there. Now, prior to the charge exchange model, we were unable to account for this data. They were only using thermal modeling, and that's what this blue line is, the hot gas in our cavity. But now we have these purple and green lines, and these are two components of the solar wind caused by charge exchange. And when you add these all up, including the thermal model, you'll notice that it lines up quite well with the data. And so after this, we have our ACX2 model. And this one is able to use real data from the Chronos database that contains our sigma data, or our cross-sectional data. And it also uses AtomDB data for our line emissivities, that being the line and continuum data. But any ions that aren't in this database will end up falling back to that ACX1 behavior. And so an example of this one being used was in a paper in 2020 titled Spectral Modeling of Charge Exchange in the Central Region of M51. I want you to notice this spectrum right here with the flux as a function of wavelength. And at the 22 angstrom range right here, you'll see our blue line, which is our data, and our red line, which is our M-dole, or what I assume to be model. And it fails to account, our model fails to account for these lines in the oxygen 7 range, as well as some of the lines at the 12 to 16 angstrom range. And in this paper, they were able to discover that hot ions from the AGN jet interacting with the cold interstellar medium accounts for some of these oxygen 7 lines. And so the pink dotted line right here is our charge exchange. And if you're looking at the 22 angstrom range, you see now that our model is able to fit that really well. Before I get into what I've done in the main project, I want to talk about the issues and solutions with this model. Well, what was the main issue for it? So when fitting a spectrum of any source, the ACX2 model was taking up a considerably greater amount of time compared to our other models in the fit. And so the goal is to greatly improve that model runtime. I want to talk about how the model works first before I'm able to get into how we figured out what we could do to it. So take a look at this onion-looking graph. You'll see we have 3 classes titled ACX model, donor model, and CX ion spectrum, and then 3 subclasses in that CX ion spectrum class. Well, each of these classes are essentially wrappers for the one below it. So let's start off in the middle. Our CX ion spectrum class is what decides, based on the cross-sectional data we have, to use ACX1, NLS, or N to create our ion spectrum. And then this gets summed up into our donor model class. Now, depending on how many donors that you've input to the program, so helium or hydrogen, it'll run through multiple ion spectrum runs.
And once you've done that, the donor model class feeds that spectrum and sums it up into our total ACX model, thus giving us the finished spectrum. So what are some of the tools we use to find these issues? Well, we looked at something called cProfile, which is a profiler that you input a function into, and what it does is it records the CPU time and the number of calls it makes for each function underneath that one. And if you look at this one, which is, it's a little confusing, but let me explain how it works. You have each of these layers right here, and each of these layers add up to the one above it. The individual cells themselves is actually giving you the time that that function ran in the entire program. So let's take a look at our main calc spectrum function. That took 7.87 seconds. Looking at what that one used, you see we have our initialization of this ion spectrum. And then to the left, we have this calc spectrum function. And if you correspond it to the line, that's for our NLS ion spectrum class. And that took 4.17 seconds. And so that was one of the first things that we looked at, is that why is this one taking up a majority of the time in our program? And so looking underneath that one, you notice that it's spending most of that time doing something called calc cross-section. And so why is calc cross-section taking so long? Well, it's spending most of its time running a function called getItem. So it's taking a while to get this data and calculate the cross-section. But this really shouldn't be happening because it gets stored into our memory. So what were some of the solutions that we went through finding? Well, as I said, calculating the cross-section was taking too long, and this was due to inefficient indexing in our cross-sectional data. And so we ended up figuring out that getting this data, we were using a nested for loop, but it's a lot easier to just use Boolean indexing to say which cross-sectional data corresponds to this, and then it gets that, and it's a lot more efficient. Next thing, we have data type conversion. So in order to get the fits data into our program, we use an AstroPy HDU list, and this is just mildly inefficient compared to other data types, for example, NumPy ND arrays. Because NumPy itself, the core structure of it is written in C, and C is just a naturally faster language compared to Python. And then some other thing that we decided to put in is utilize our data initialization. So the data was getting initialized within each of our functions. And so when you would call a function multiple times, it would always reinitialize that data. And that was inefficient, so we decided to just take the data, initialize it in the main class's initialization function. And that allows you to use it for these functions without having to reinitialize. So after we've done all that, we have this. And immediately you'll notice that the ion spectrum class is taking up the bulk amount of that time. Well, we don't really care about that because you're only going to initialize the ion spectrum once when you run this model in a fit. So you can ignore 3 seconds, pretty much, from the whole program when you're running fits. So before, it took 7.87 seconds, right? And now, it's taking 3.26 seconds to calculate that spectrum. That is about half the time. So that's pretty good. Looking further down, if you remember, we had our calc spectrum function, which took 4.17 seconds. And now, where's it gone? Well, it's in that little box right there. So you can see it's already taking much less time to do that function. Going even further down, that calc spectrum function took 3.87 seconds to calculate our cross-section. And now, the new calc cross-section is only taking 0.0187 seconds. That's roughly 200 times faster. And it was definitely the main reason this program was running so slowly. So what's our final results? Well, we have our model runs on the x-axis, looping through it 100 times. And then you have how long it took in seconds. The blue line, you'll see, is our original file. And the red line is the final file that we ended up finishing. The blue line has a much steeper slope. It is roughly 10 times faster now. And initialization, on average, might be a little longer,
but again, it doesn't really matter in the grand scheme of things. And so in order to actually take this and say, okay, can we use it on a real source, we have supernova remnant N132D, which with the release of the CRISM telescope, we were able to get much better resolved data. So I want you to take a look at this graph right here. This is from a paper released very recently titled Evidence for Charge Exchange Emission in Supernova Remnant N132D from CRISM. And you'll see we have the data and we have our model. And after running, in this paper, after they were running a fit, they noticed that while very faint, it did have charge exchange instances. And that's the main thing we were looking at when creating the model now. And so the one on our left, it's not as good as the one on the right, just because we didn't have enough time. But you can definitely see that red line is the fit. And then these dotted lines are the charge exchange. And they do correspond, while maybe lightly, but they do show up. And so running through our old file and our new file through 6 iterations, how long did each one take? Well, in the original file, you can already tell it took roughly 220 seconds, let's say. And for the new one, it took only 55. So that's a roughly 4 times speed increase as opposed to before that. And this is taking into account that within each iteration of a fit, you're calculating a spectrum many times within it. So what questions have we concluded? Well, were we able to speed up our model? Yes. Were we able to speed up the fitting time in a real example? Yes. Is the model runtime comparable to our other models? Yeah. With only a thermal model, it runs in roughly 0.7 seconds. And now with the ACX2 model included, it takes 1.6. So it's pretty comparable there. So what are some future considerations for this project? Well, in the near future, supposedly, we're set to receive a newer data set with more cross-sectional data corresponding to our ion and our donor. And because we have more of this data, it'll just take naturally longer. So you'll have a larger runtime to go through this data. And so for the future, some other things that we might be able to do is changing the structure of some of the Python program. That was outside the scope at this point. But for example, we have a function called expand egrid, which does our continuum calculations. And that one is just taking maybe a bit more time now. Or it's taking a majority of our time in the program. And converting it from Python to C++ would also be greatly beneficial. That was what we originally planned to do, but life doesn't work out how you want it. And I've never coded in Python or C++ before, so it's a little hard to learn at this point. And that's pretty much it. I want to thank Dr. Adam Foster, Priyanka, Rudy, my fellow CREATE members, and Nick, my professors at Worcester State, and my family.
I want to thank you for bringing life to the live chat during your presentation. It was going off. And I think we're going to adopt this one and call you Petrash the optimization legend.
So that's my friends.
If you're online and you want to leave a question, feel free to ask a question in the live chat and we'll ask it. For those people here in the room, do you have any questions?
Hello, great job on your presentation. I had a question about maybe in the future, if you have thought or if you think could be implemented like parallelization in the program. Like, do you think there's a way that you could do parallelization on the program, or what steps would be needed if you wanted to parallelize some functions, if possible?
I'm sure that's definitely possible. I'm not sure exactly how I would do that, but looking into that would definitely be a good idea.
Okay, one more question on the chat. Did you pull any all-nighters? How many? From Jennifer.
I actually did not pull any all-nighters because I value my sleep. Even when I say I do,
I usually end up falling asleep at the table.
Work-life balance. Can you go back to the slide with the results from the 2025 paper in the Japanese journal? Yeah. So this might be I'm not an astronomer, so this might be a very easy question to answer, but why are the dotted lines, they seem to correspond to the ups and downs of the thick line at the top, except for in the middle with those two oscillations upwards? Why do the dotted lines not also follow that?
You mean here?
Yeah.
It might have something to do with it's just not finding charge exchange happening within that region. Again, they are very faint in this source, so if you take a look over here, there is some smaller lines, but when we took the fit, we didn't have much time to do a really good one, so that could probably be it.
Also, we're going to miss you at CFA football. Sorry to interrupt.
That's essentially, right? There's no charge exchange there, but there's something else there.
So yeah, just to answer that one, slightly unfair question for Raj because I didn't actually talk to him about this, so that's not his fault. The reason is because those are silicon charge exchange lines, and those strong features are from sulfur. So there just isn't sulfur in that particular spectrum in charge exchange.
So this might be a question for you then. What is charge exchange? Or Petraj can...
Whoa.
Oh, okay.
What is charge exchange?
Yeah, what is... So, yeah, that's something, like a term that's been thrown around here. Is that the same as, like, charge splitting when, like, you know, a single photon hits multiple pixels and the charge kind of splits among the pixels, or is it a different phenomenon?
Is that an instrumentation?
Yeah, so that might be an instrumentation thing. Like,
charge exchange is... Charge exchange is when you have your donor atom and your ionized atom, and they collide, and the electron gets exchanged into your ionized atom, and then it cascades. In space. Yes.
Not on the detector.
No. As far as I'm aware, I don't know.
Hi, amazing talk. And yeah, I was really interested about how you sped up a software to, and then the fitting to be like basically very fast. It was like 3 seconds and then went to like 0.3 from what I saw. So I was wondering what kind of hardware do you use to run these? And with like the higher amount of like data being used, would you be able to run this like on a computer, or it's like a personal computer, or do you need like a cluster for that?
Yeah, I mean, most of these, hold on. Like these ones over here, these ones just the times I ran this function on my MacBook. And so I have one of the newer MacBooks, I have the M4 Pro chip, or yeah, something like that. So it is one of the better chips, but it shouldn't be too much different for any other system.
Oh, okay. Thank you so much. Yeah, and I think like also I agree with you where like parallelization might definitely come in handy, especially with the Pro chip that has a lot of cores. So like being able to utilize that with the incoming data sets would be good. And there's like a package called Ray on Python that you can use to parallelize the code. And there's probably like a lot of different other ways too. But yeah, thank you so much.
Yep.
Any additional questions? Even if you don't afraid to ask a question, I can. No questions? No questions? Okay, great. Let's give him another round of applause. All right, now we have a 20-minute break. Refreshments, bio break, whatever you wish. There's sandwiches back there still. There's might be some cold coffee. We might be getting a refresh in a little bit. And we'll start again at 3:40. Thank you, everybody.
I'm sure that works. Thank you.
I had a quick question.
test. Yeah. Okay, good. We're on the time. All right, everybody. Thank you again for sticking around, and thank you for coming to the first half session. We're now going to kick off the second half session of the CREATE interns presentations. Reminder to people who are on the live stream YouTube, if you have a question for a speaker, please put it into the live chat, and I will address it as soon as I see it. We are on a little bit of a lag with that live stream, so just bear with us if we are behind. Okay, great. Our next speaker for this half is Adam. Take it away. Is the green light glowing? And then move it maybe a little bit more central. Central and lower. Try.
Hello?
Central, lower, lower. On the sweater maybe.
Hello? Okay,
yeah.
Good? Cool. Okay, hello everybody. My name is Adam Yahid, and I am an undergraduate at Worcester State University studying computer science. I'm here with the CREATE program, and I'm going to be talking about disambiguating software mentions using machine learning models. This is Zippy. He's going to be joining us along the presentation. Okay, so first we have an issue, right? That's with software attributions. Citations in general are important, but usually software mentions are often overlooked. This is a big problem in general with papers, scientific papers, and that's for a few reasons. First, obviously, it's good to give credit where credit's due. Two, it's good for adopters, whoever wants to use software mentioned in papers, it's good to cite it for them. And three, it's good for statistics on what software is being used, how often, things like that. Okay, so you might be asking the question of why not just find the term and cite it? Why not just Control F? And the big issue with that is ambiguity. A lot of software terms are not as simple as finding a term and then citing it because it could be very ambiguous. For example, I have two sentences here. There is a software called mayonnaise. Believe it or not, there are a few software terms that are foods. This is one example. As you can see in the first sentence, it talks about mayonnaise as we all know it, the condiment. And then the second one, it talks about mayonnaise in the software term. So how can we differentiate the two and cite the correct one? So we have a process, and the first thing we do is we actually do find the term. Then we take a chunk of text around the term. We chose to take 100 words before and after the term where we found it. And then we use an NER machine learning model to determine the context and determine if it's actually a software or not. So you might be asking, what is NER? That stands for Named Entity Recognition. And it basically takes a sentence, for example. Here we have Zippy used Python to study astronomy at the Center for Astrophysics. What NER does is it takes a sentence and it picks out entities where it sees it. So for example, Zippy, it'll pick that out and it'll determine that it's a name. It'll take astronomy, determine that that's a field of study, and the Center for Astrophysics is a location. And then what we want is something where it would take out Python and say that it's a software entity, and then this would be the link to that software entity. And it can also have different variations, but depending on the context, it should link to the same thing. So a bit of background info, bibcodes and ADS. ADS, I'm sure most of you are aware, it's a digital library containing scientific papers in the astronomical field. And bibcodes are just unique identifiers for each paper. This is a couple of examples. The way that the IDs work is the first part is the year, then the journal, the volume,
the page it's on, and then lastly, this last letter is the initial of the author. So we need data and inputs to use the machine learning models. So what we have are a list of software names taken from the astrophysics source code library and corresponding metadata, as you can see on the side here. We have the title, which is the name of the software, and other metadata. What we also want is these positive bib codes down here, and I'll talk about that in a bit. And we use this with our corpus, which is SciEx articles spanning from 1940 to 2025. This includes bib codes, titles, abstract, and full text. Okay, so I mentioned positive bib codes. What is a positive bib code? Basically, it's a bib code where the software term was found in the correct context. It was curated, and we know that it is software. Uncurated is basically everything else. It used to be negative, but that's not quite correct because negative would imply that it's in the incorrect context, but we just don't know if it is or not yet. So it's just uncurated. So what we have to do is look through these terms, look through the papers, finding all 3,000 software terms from the ASCL library, and then taking the context around each of those. And using a script was extremely inefficient when I made it. But luckily, my advisor came to the rescue, and she optimized it. I had calculated that mine would have taken a year to run, which not good. Hers ran in a matter of hours. So it was great, and it gave us all the context we needed to actually feed it into the models to verify what we wanted to. Okay, so what are we actually doing? How are we verifying? We have these lists of positive bib codes, everything that we know that the software is cited in the correct context. And then we match that against these contexts that we are given. The models have tokenizers. And this might be a little different than what you're used to. With AI and machine learning, you might think of something like ChatGPT that is generative and has reasoning. That is where you input it, and then it spits out an answer, and it creates another string of text. This is a bit different. You input it, and it does what it's trained to do, and it outputs something. It has a specific narrow task. This is an example of how tokenization works. You feed it the sample text here. It tokenizes it, and these are called tokens. Basically, it's how the models work with text. Some tokenize it in words, some into characters. Each model is different. These are the two language models that we decided to use. The first one on the left is the Indus NER model. This one was trained on NASA's Science Mission Directorate articles, and it's well trained in the correct domain of astronomy and astrophysics, but it's not as well trained on software mentions. And then the one on the right, the OEG model, was kind of the opposite. It is well trained on software mentions, but in a different domain, the bio and economics multi-domain. So one of these two we figured would be better for us, and that's what we aim to see. So these are the results that we found. This is after taking the context for only the positive bib codes, and then putting them each through both models, and then condensing it so that each bib code has a unique number. So, for example, there were 1,700 lines that were found. So 1,700 different contexts that the software were found in. But that included bib codes that were duplicated. So this is condensing each one down to a single bib code and then seeing if they were found in that bib code. As you can see, the OEG model got 100% correct, and the INDIS model got mostly correct, but it got around 5 incorrect. This is just to show what the INDIS saw as correct and incorrect. It correctly picked out this software name in this sentence, and in this one, it incorrectly said that this was a note, even though it is a software mention. It's in a URL for a software. There were a few challenges. First one is the OEG model had a tokenization error, which I'll show on the next slide, and also software domain disambiguation, which I'll talk about in a couple slides as well. So the tokenization issue with OEG was basically this. So there was a software called Zeus, and when we put it through the OEG model, we saw that it tokenized it like this. It split Zeus into ZE and hashtag US. This is obviously incorrect. It should be one mention. But we worked around that by just dividing by 2, because for each mention, it just divided in half. And then there's a second layer of disambiguation. So I was looking through the data, and I looked at sushi. And I noticed that the top sushi is what we want to see in the astronomy field. But I noticed that the other 2 sushis were also found as software, but they aren't the correct ones. So this brought up the issue of, okay, we found that it's a software, but how do we know that it's the correct software? So if the model found that these are softwares, linking to this one would be incorrect. So that's an issue as well. A potential solution to this is create embeddings based on common surrounding words. If, for example, the top sushi had words that are more common to that software, as opposed to the other 2, it would be, the model would see that and then create an embedding where it would rank it kind of like here. And it would say that it's closer to one model, to one of those softwares compared to one of the other ones. The problem with this is something like sushi doesn't have that much context to give, so there's limited training data. With these machine learning models, they become more confident the more training you give it, and with sushi, I don't think there's enough data to actually feed it to give it a good enough confidence level. A few future directions for this project is analyzing edge cases and outliers. As I mentioned with sushi, that was just me looking through the data and finding that there was that issue. Looking further into the data, something that can't be seen as a whole would be useful. Then curate a negative bib code subset and analyze that. As I said before, we have positive and uncurated bib codes, but we don't have any negative, explicit bib codes that we know aren't in the correct context. So that would be worthwhile to analyze. And then lastly is increase the effectiveness of what I did with the models by basically doing what I said in the previous slide with the embeddings and finding context similarities between similar softwares. And then this chart at the bottom is pretty much a future idealized version of a pipeline that would be implemented into ADS or SciX that basically does all of this from start to finish, from inputting the corpus and then outputting the citations in the correct way. So that's it. I just want to give some acknowledgments to my mentors and to my fellow CASPER interns who were great supporters and friends this summer. And that's it. Thank you.
I didn't even have to stand up. It was right on time. Any questions from the audience? We got a little peek behind the scenes of what happens when you search ADS.
Hi Adam, amazing talk. And I had a question about just particularly like how the software packages used in these papers. Do they usually have their own citations like with bibcode, or is it like the software that's sometimes used? Is it like not is it like not published? Like, for example, there's like a journal called the Open Source Journal of Software, or something like that, and they have like the software it's in there. It has to like it's published and it has its own like bibcode and stuff like that, and then from what I can tell, there might be. Is there like some software that you found in these articles that didn't have like that their own bibcode, or does it like they all have their own bibcode and you're just using this machine learning technique to try to find and associate it with just try to find the actual the software origin, because like you just have like an acronym.
Yeah. So in this slide, as you can see on the right, we took all the software names from the ASCL library, like I said, and this actually has, as you can see, a preferred citation and where it should be linked to. So this is where we got all our terms from. So if they have a preferred citation or a link, this is where you would find it. And if they don't, then it would just be an empty field. I don't know if that answers your question.
Yeah, that was a really good question, actually. So let me add to that. All of the software that's currently in ASCL, which is pretty much most astronomical software, they all get indexed by ADS and they get assigned bibcodes. That's not true in all scientific fields. And it's also not true for very new software or sometimes for very old software. That just isn't an ASCL. And if it's formally cited, we are trying to index everything in the ADS and assign bibcodes. But if it's not formally cited, like in the examples here, that's exactly where we need NER and trying to find how the software was used and whether it was used with other methods. Thank you.
Hey, Adam, nice talk. Can't believe you fit it all into like 14 minutes. I was wondering, when you were doing your research on this, are there places where you can find best practices for naming software so that this disambiguation is easier? Or just curious.
I mean, I think that's the whole point of this, right? Is like that you, I guess, can name it that, and then this will disambiguate it. But I think just in general, just like if you just think if it's in another context could be used, then it probably is ambiguous.
Can you show us the mayonnaise again?
Yeah.
And just to let everyone look at that for a second, where the letters are coming from.
Yeah, so mayonnaise, they chose out morphological analysis yielding separated objects in near infrared using source estimation. And they chose to name it mayonnaise. So obviously that's ambiguous. Just don't name it mayonnaise.
They are. They are. This is, I think Fabio Zero. No, Fabio Zero is doing the sushi. So I don't know who this team is actually. Oh, time for one more question.
So I guess this works sort of similarly to the probabilistic LLMs, but without the generative part. I'm curious about when you talked about disambiguating if two software packages were named the same thing. I guess a naive way of doing it would be like comparing the vectors of the sort of words, but could you talk a little bit more about the embedding approach that you mentioned?
Yeah, so embeddings is just like, again, if you feed it enough data, it'll see that it's closely aligned to one versus the other. The thing is there rarely is enough data with software packages that aren't as commonly used like this. But this is outside of like the scope. That's why it's a future improvement. I'm not too sure. This is just the one suggestion that we were thinking about doing.
Let's thank Adam again and go on to our next speaker. Great job. take it away.
So my name is Smriti Shashidhar, and I was an intern with the CREATE program this summer. And this will be my project talking about the subreflector control for the submillimeter array. So what is the submillimeter array? So some of you that were here earlier might have already seen this mentioned, but just as a recap, it is a configuration of 8 radio antennas that collectively act as an interferometer. And the reason that we're even able to see in the submillimeter wavelength is because of the location, where this is at the summit of Mauna Kea in Hawaii. And because usually at ground level, submillimeter wavelengths are not able to permeate all the way through the atmosphere due to water content. But because of this location, it's relatively dry and very high up, so we are able to observe the submillimeter wavelengths. But what is the reason for going through all of this work to look in this wavelength? The thing is, when we look in longer radio wavelengths, we're not really able to see specifically for molecule emissions for star formation regions, and that's something that the submillimeter wavelength is very good at doing. So if we look at this picture down over here, right here, we can see that this is a picture that Hubble took in the optical of M51. Very pretty picture, but it does not give a lot of insight into the star formation regions, whereas when we look at the picture that the SMA took in the submillimeter wavelength, we can see it very clearly points out where those star formation regions are. And similarly, if we look over here at a picture that Spitzer took in the infrared, again, very pretty picture, but we can't really see what exactly is happening in the middle. But when we zoom in, which the SMA did, looking in submillimeter wavelengths, we can see this very massive protostar and these molecular outflow regions that it has over here. So it gives us all of this really important information, but how exactly does it do that? Well, a little intro to radio interferometry. So the way that this works is that these 8 antennas are in a movable configuration. So they can be moved from place to place, which affects the baseline, which is the distance between them. The reason this is important is because that distance between these antennas affects how they receive the signal from the radio source. Because they are separated, the signal that they receive from the radio source has a different delay as it hits each antenna, and that delay creates an interference pattern that, when combined, creates our interferometer response that you can see in this corner. So what is this actually showing us? This is showing us the interferometer response coming from the radio source. And an easy way to think about it is it's kind of like a reverse double slit experiment. So the double slit experiment is basically having one coherent light source going through double slits, and then you would see an interference pattern up here. This is kind of the opposite, where we're seeing this interference pattern coming from a radio source, making it go through 2 slits inside the antennas, and then it's combining and forming a response, hitting the detector as a coherent source. So now to move on to the mechanism that I was specifically working with, which is the subreflector controller. So if we take a look at this radio dish right here, we can see that when there's incoming radio waves, they bounce off of the dish, hit the subreflector, which is right here, and then go into the feed horn to be detected internally. So the subreflector is a very important component of these radio antennas due to the fact that it is what allows these radio waves to be focused, to actually be detected. If they're not able to focus, they cannot be detected properly. So because it's such an important part of actually detecting this data, it requires a lot of mobility. Hence why there are 4 different axes of motion, which can be seen right here. We have our x-axis, which moves it from left to right, our y-axis, which moves it up and down, our z-axis, which moves it in and out, and this tilting axis that we have here. And these are limit switches. These are there on every single axis to make sure that the motor doesn't outstay its boundary and it stays within those boundaries that is set for it. So I mentioned this tilting axis here. All 4 of these axes are used to move it to focus the signal, but the tilting axis also has a different thing it can do, which is called a chopping motion. What that is when the radio antenna is pointed at a specific radio source in the sky, and then the tilting axis is used to tilt it just a little bit away so that it is now pointing at a section of the sky that doesn't have a radio source. What it then does is it chops very quickly between those 2 portions of the sky, one with the radio source and one without, and it creates two different images, which when subtracted can provide a resolved image of the radio source. This is currently not used for any scientific observations as of yet, but what this is doing is it allows us to make sure that the antenna is capable of detecting accurately before we move it to actually look at scientific observations that are a lot more important. So how do these motors within the controller actually work? These are incredibly important because this is what allows that subreflector to have that mobility. And the way this is accomplished is through stepper motors. A stepper motor is basically a motor that only moves with discrete steps. This is really important because this allows that precision and accuracy to happen, as opposed to using something like a DC motor, which is only dependent on voltage, and that just allows it to move continuously, and you don't really get the same precision with that. The way that this motor can get to discrete steps is through these components that we can see right here. So we have our stator, which is the outer circle region here, which is stationary and doesn't move. And on the stator, you'll see that there are those coils. Those coils, when a current runs through them, become magnetized and generate a magnetic field. What happens then is that the rotor, which is this internal mechanism here, and the part that actually moves, then moves to rotate to align with the magnetic field, which we can see right here. So now that the motor can move to these discrete steps, how do we know what position is actually being read? So the way that this is done is with the quadrature encoder. So this works by having a light inside the motor where it shines through this grating here, and this grating moves as the stepper motor is moving. And so since the grating is moving, the amount of light that is hitting this photodetector chip keeps going in and out. So it gets read as a pulse every single time that the stepper motor moves, which is how we're able to correlate the mechanical motion of the motor to an electrical impulse that we can see in our data and actually read back the position. So another important thing to note is not only the position of the motor, but also what direction it's moving in. So next to this photodetector chip, we also have these two output channels, A and B, and they're slightly out of phase, which allows us to know which direction the motor is moving in. So if we look at this diagram here, we can see if the pulse hits the channel A first and then channel B, we know that it is turning clockwise, and if it goes the other way, it hits B first, then we know that it's going counterclockwise. So we can see how all of these mechanisms are internally being controlled by the subreflector controller and allow it to go to these positions, but how do we make sure it's actually being accurate? That is where PID comes into play. So this is a way to ensure the accuracy of our motor position. Like I mentioned, it is really important for this to be very precise, which is why we want to implement something like this. PID basically allows for our motor to follow a set path, a set trajectory, if you will, and that allows the motor to know where exactly it's supposed to be at every time step to ensure accuracy and precision. Because if the code just tells your motor, I want to go from position A to position B and then stop, that's easy for code to do, but when you tell a motor to do that, a motor can't move instantaneously. It has to first start from a 0 position, speed up, know when to cruise, know when to slow down, and fully come to a stop, which is not very inherent in the code itself. Which is why we need to implement things like this. So the way this works is we set a trajectory in the code. The code will tell it, okay, if you have this much distance, we need you to speed up for a certain time, cruise for a certain time, and slow down for a certain time. And this motion is set with kinematic equations. This is obviously an idealistic view, but that doesn't actually work with the motor. A motor is not perfect. So we can see we also need something to make sure that the motor is constantly checking if it's following that path or not. And that is where PID comes into play. So we can see here that there are 3 different components to PID, 3 constants, Kp, Ki, and Kd. So what it's doing is there is the calculated position that the motor is supposed to be at, and there's the actual position the motor is at. What it does is the code keeps looping and it checks, is the position where it's supposed to be? If not, what's that error? It looks at that error and it combines it with these 3 constants to keep trying to match it to the correct position that it's supposed to be at. So here in this example, this is a plot that is looking at a DC motor and the speed of it. So here we set PID constants for this motor, and we're trying to get it to move from position A to position B. And you can see here, these are the 3 contributions from KP, Ki, and Kd. And these summate to create the total speed that the motor is supposed to be set at. This speed, you can see that it speeds up and then it slows down. And this is why we want to make sure it is actually being accurate. So what we can see, this is a kind of perfect looking curve, and this is not so perfect. This is the speed that the motor is actually going at. You can see it's a lot more bumpy, but the overall picture of the curve looks very similar to the speed, and that's how we know that it is actually reaching its position. So this was implemented using a DC motor, but the same premise is used when we look at the stepper motor. So what I actually did was create a Python script that is talking to the software that controls these motors. The Python script basically just asks for a user input, and that's all they have to do. The code takes care of the rest. It sends commands to the software, and the software then tells the motor what motions to go through. The reason the script was created is because before this, all you could do was sending commands for every single motion. There are multiple commands you have to send in, and you have to check if it hits that limit. Will it know that it has to stop rotating? Because sometimes if it hits the limit and it keeps rotating, now the position you're reading isn't actually accurate. So all of those checks are being done by the code instead of you having to be there in real time to check it, which makes it a lot more efficient and accessible. And this also means it can run autonomously. After you initially input it, you can take your hands away and it'll do what it's supposed to do. So to test this script, we tested it using the x-axis of motion on the subreflector controller. So here we are checking for the error in stepper counts and encoder counts. Just to mention again, the stepper those are the counts that the motor itself actually uses to find its position, and the encoder counts are the position values that we are reading back because of the voltage differential it's measuring. So here we can see that when it's traveling at specific distances, the error in the stepper counts was around 10 to 13 counts, which falls within our 10 micron range, which is good. And for the encoder counts, you can see they fall within 1 to 3 encoder counts being off, which is okay. That also falls within our 10 micron range. So this met our specs, and if we were to in the future work on trying to reduce this error, this could be reduced by adjusting the PID constants that I mentioned earlier, and we could better account for the hysteresis of the system. What that basically means is, like I mentioned before, code is almost instantaneous. Motors can't do that. And hysteresis is basically just that delay that physical motors have that code doesn't, and you have to account for that. So sometimes maybe you think that the motor came to a stop and you're reading back the position, but maybe that's not its actual final position because it wasn't actually done moving. So stuff like that can affect our error, and that can be something that, if we better account for it, could help reduce our error as well. So how does this help us? What is this actually doing? So in the short term, this script is made generalized, so it can be applied to the y and the z axis already. It just remains, the only thing left is to be tested in that. And it could also be applied to the tilting axis as well. And like I mentioned, we could better improve the position accuracy of these motors. But how does this help in the long term? What this will hopefully eventually let us do is to sync the translational and oscillatory motion across all the antennas of the submillimeter array. Basically right now, the submillimeter array can get all the antennas to move to look at a specific point in the sky, but the antennas move independent of each other. They eventually get to the same position, but along the way they're not moving in sync. The reason we want them to move in sync is because if they are able to move in sync, we might be able to allow for a simultaneous low and high resolution data capture. This would mean they would have to move in sync together and also be able to do that chopping motion I mentioned earlier together. And that would all require a high degree of precision, which is why we want to make sure we're accounting for any errors in our system. And low and high resolution data capture is really important because there is a lot of valuable data to be got in low resolution and in high resolution. And right now the interferometer can only look at high resolution data. So if we look at this image here, this is an ultraviolet observation of the Andromeda Galaxy. And you can see in the ultraviolet, all of these very bright sources are what the radio telescope currently, the SMA, is very good at looking at in high detail. But you can see all of these sources exist in this context of this larger Andromeda Galaxy that the SMA currently does not look at. It's looking at these very specific sources, but not the whole thing. So if we were able to do low and high resolution data captures at the same time, we would be able to see not only the very specific point sources, but also the larger context of the galaxy or whatever stellar structure that they are part of. And yeah, thank you. I'd like to thank my mentors at the SMA, Dr. Ram Rao and Dr. Garrett Keating, and also Dr. Rodolfo Montes for being our CREATE program advisor. And yeah, thank you for all the interns.
Awesome, thank you. You got a shout out from Lizette on the live stream. Again, if you're on the live stream and you have a question, put it in the live chat and we'll read it in the room. If you have a question in here, raise your hand. I'm happy to bring the mic to you. I have a question. You first.
Thank you. That was an excellent talk. And yeah, I had a question about the errors on the that slide there. So you said that the errors are below like 10 microns, which is really good. I was wondering, like, how does this system for the SMA kind of takes the errors into account? Is this like whenever you move the telescope, it's like an error where like, does it like point at the exact position, or is it like within this like margin of error? And if that's so, if during like each run, does that error kind of accumulate, and do you need to like recalibrate the telescope to then like make sure that the errors don't accumulate, if it does? Because I'm kind of new to this.
No, yeah. So basically, these errors are usually whenever you're working with any type of like physical motor in general, you can't say it's actually ending up at a very, very specific position. There is going to be a little bit of a range that you know it's going to end up within. And we try to minimize that range as much as possible, but you can't fully eliminate it right now. So whenever the SMA does move, it does have that kind of range in mind. You know you're moving to something within a resolution of maybe plus or minus 10 microns. I cannot say how that error might accumulate because there are like ways in place to recalibrate your position. So I would say if anything like that does happen, it is possible to recalibrate just to make sure you're accounting for any type of error that might be building up, like you're saying.
Awesome. Thank you so much.
Mm-hmm.
That was also my question about those errors.
Hi, so I remember you talking about a user being able to put in one input and then it being able to just do the rest of the job from there. Does that imply that if a user puts in one input, it'll move all the axes at the same exact time?
So actually in the code, you can specify that. So you can say, I want to move to 10,000 counts in axis A, I want to move to 5,000 counts in axis B, something in axis C. You can input all of that in one line of code, and the motor will do all of that on its own. So it will, you don't have to like say that you can only do one position and it has to be for all the axes. The code can take that into account if you want to go to different positions in different axes.
And will they move at the same exact time, like simultaneously with each other, or one axis at a time?
I think the way that I have it currently, it would go one axis at a time, but that is something that in order to make it more efficient, there might be some parallel computing that might be able to be done later so that they could all move at the same time. But for what I have currently, it would have to go one by one.
We have a question from Lizette. What was the hardest part about this project? She said cool project first.
The hardest part, honestly, using terminal. Okay, because terminal is just like every single keyboard shortcut I have spent the entirety of my life ever learning and memorizing cannot be used because terminal loves to have its own little shortcuts that don't even make sense half the time. Because why do I have to press Y to copy things? I don't like that. So yeah, terminal.
Terminal, okay. Add it to the, we'll add it to the intro session, session on terminal. Any extra questions?
Hi again. I had a question on. I had a question on the the serial commands. So like, in an Arduino, there's like the interface, and you can be able to like see what serial commands or like what's USB like inputs, like ports are available on the Arduino or whatever, right? And then like for Python, what kind of is there like a software package that allows you to read these commands from the motors? Because like there's like a little, like on the motor itself, like it reads it based on like these lines. So what kind of interface is it between that and Python?
So I actually did not have to do that on my end because the software that I was communicating with using Python was doing that for me. So if I wanted to read back what position I'm at, I would, in the Python script, type in a command that would command the software, tell me what position I'm at. Because the software is already getting the position inputs from the encoder, and it's reading where the stepper position is, like where you're telling the stepper position to be. So I didn't have to do that separately in the Python script. I could get that directly from the software.
Oh, so it was like a Python script that already had it, like all the commands from the serial, or like, I guess I'm trying to say, like, is there like a name for the package, or like, is it just a script that's in Python?
It's just a script, yeah. Oh, it's not like in Arduino where there's like a specific library I would need to read that encoder, because there probably is a library to read that encoder, but it's not in my Python script, it's in the software I'm communicating with.
Awesome.
So I don't have to do that part, because it's already in the software.
Awesome, thank you so much for that.
Okay, let's transition to our next speaker. Give another round of applause to this speaker. I totally lost track of time, sorry.
Where's that microphone?
Is that good? Can you hear me?
Speak a little more.
Can you hear me?
Yes.
Okay, excellent. Okay. So, hey y'all, my name is Lisa Tesco. I'm a student at San Antonio College at Texas. My major is physics, and I'm gonna have a minor in astronomy/astrophysics. This summer, I had the privilege of working with Dr. Jason Eastman on characterizing exoplanets and their host stars in binary systems. So why are we doing this? We are doing this because we have 221 exoplanet candidates in binary systems, of which we have the AO, adaptive optics by photometry. So we have data about the second star, the companion star. Of these 221, we expect 50% to be real. The other 50% are other things, including only visual binaries, which means these stars are not actually bound. And we want to understand the properties of the real ones. And we found something interesting about some of these candidates. They're hot Jupiters. Hot Jupiters being Jupiter-sized planets very close to their host star, therefore very hot. Hence the name, hot Jupiters. We've known about hot Jupiters since around 1995, and since then we've been wondering, how'd they get there? How'd they form? We know there's not enough material in the area that they are to form something as large as Jupiter-sized planet, so they must have migrated. So how'd they get there? One potential method we know is the Kozai cycle with tidal forces. This is a process that requires three bodies, a host star, an exoplanet, and a second star, which is a binary system with an exoplanet, exactly what I'm modeling. So the planet, because of the Kozai cycle and tidal forces with having the second star, the planet oscillates between eccentric and then circular orbits over millions and millions of years, and the tidal forces dissipate its orbital energy, tidally circulating its orbit. So these are some graphs about the Kozai cycle and tidal forces. The graph on the left here shows the eccentricity, and this shows the inclination. They are opposite proportionally. When the eccentricity is low, inclination is high, and vice versa. You see they go up and down until they eventually level off. And this is a little illustration of the process, but I think I like mine a little bit better. So I'm going to show you. This shows the three bodies, the host star, the planet, and the second star, the binary system. And it goes in between eccentric orbit, eccentric, circular, before it lands at circular. To understand these hot Jupiters, though, we have to understand the bodies inside of it, which brings me to the tools that I use to model these systems. TESS, the Transiting Exoplanet Survey Satellite. The way that TESS works is it spends 27 days looking at one sector of the sky, spending 1 year looking at one hemisphere before it flips over and spends the next year looking at the second hemisphere. And it has been doing so since 2018, continues to do so, so all these stars have been observed multiple times. The tool that I use to actually model it is ExoFast. It's a program written by Dr. Eastman that allows us to model the best fits for a star's brightness and age and its exoplanet's period and transits. Shout out to Dr. Eastman because this program is insane and I don't know how he did that. We have some trouble modeling the binary systems though. So what some people have done is sometimes they just straight up didn't know there was a second star. Other times they're like, yeah, we're just gonna ignore that. It's irrelevant, you know? Or they would make assumptions. For example, if star 2, it makes up 3% of star 1's light, then they would adjust the transit by 1%. However, the depth of the transit is RP over the radius of the planet over the radius of the star squared. So any false assumptions you have about star 1 result in biased results for everything else you have. So enter ExoFast V2, in which we are able to model both stars in a binary system at the same time, leading to more accurate stellar results and therefore more accurate planetary results. The process of doing this is we collect telescope data and prior stellar and planetary data, which we get from TESS, and then we set the number of stars and planets in the system, and then I push a little button that says click to continue, and it goes. And it produces 3 types of files. The first being a spectral energy distribution, an SED model. So what we have here is this black line that's really close to the red line is the total light emitted from star A and B. The red line is star A, green line is star B. Oh no, sorry. Okay, so what we have, these are blue. These blue dots along the red line are the data we have from TESS, and these dots along the green line, these are from Gaia, another space mission. It gives us adaptive optics, AO photometry for the second star, which means that we are able to place some restraints on the brightness of these stars. And we learn a couple things from this graph. We learn that the peak shows us a temperature and color, and the x-axis is its wavelength and things like that. The second model is a mist model. So what we have here is the black line is our theoretical idea of the evolution of the star. And ExoFast produces these 2 black dots. Those are its predicted ages of the star, and the red asterisks are the actual data that we have from the star. And we want the model to ideally match reality, you know? So they should be as close as possible, which in this case they are, so yay. The third model we have is a transit model. The animation to the right shows a transit in which the planet is going in front of the star, and when it goes in front of the star, you can see in this little light curve that the brightness dips as the star goes in front and then goes back up as the planet goes behind the star. Over here we have the actual transit model we got from ExoFast. The red line here shows the ExoFast's best fit, and the black dots here are the data we have from TESS. They should match up because we want our model to match reality. And now going on to a system I modeled, TOI 123, which is Test Object of Interest 123. So here, again, this is before we ran it through ExoFast. This is just straight from TESS. We noticed that the blue dots are on the black line when we want them to be on the red line, and they do not match up with these red error bars, which is a problem. And you'll also notice that there is no data along the green line, star B. So when we ran it through ExoFast, we did add that AO photometry to star B, which allows us to give restraints on the brightnesses of the stars. And we get the MIST models. This is the MIST model from star A. Before, pretty acceptable. After, pretty better. From this, we can tell that star A is an evolved giant star. And this is star B. The start started pretty good, ended better though, so yeah. And from those, we can learn about the stellar parameters of TOI 123. Something we'll notice here, which is a little odd, is that star A is cooler than star B, which is a little odd. We're not sure why, because usually star A is hotter than star B. And the third file that it produces is the transit. Here we can see that before we ran it through ExoFast, the period was a little too long, and it didn't match up over here. When we ran it through ExoFast, we added a third sector of data to make it a little more accurate. And from this, we get our planetary parameters. We'll notice here that the semi-major axis, in terms of stellar radii, is about 4. So it is 4 stellar radii away from its star. To put that into context, the Earth is 218 solar radii away from the sun. So this is like insanely close. So between that, it's short period, and it's double the size of Jupiter and very hot, we can be like, that's a hot Jupiter. So what can we do with this? There are endless possibilities, a lot of things we can do. A lot of it can be focused on hot Jupiters, though. We can learn how does a stellar companion affect the orbit of an exoplanet. And since these hot Jupiters that we have observed have a third body in the system, do all hot Jupiters have a third body in their system? And we can understand that through the Kozai and tidal forces, which we learned about before. Yeah. Okay, so what we did in conclusion was we modeled binary star systems with an exoplanet to get stellar and planetary parameters. We got results that can help us answer questions about hot Jupiter migration and plenty of other things. Thank you to Dr. Rudy Montes, Dr. Jason Eastman. I want to thank you so much. Your passion and your patience really helped me learn a lot, and it was truly a privilege working with you. Thank you to my CREATE interns and various other besties that I made here. Thank you.
Great, thank you. Do we have questions from the audience? You got a shout out from Cameron on the live chat.
Hi, Lisa. Wonderful presentation. I was just wondering if you could scroll back to your MIST files, or just the most recent one. Yeah. So why is the line shaped like that?
Well, that's our predicted star's evolution. I don't know why it's shaped exactly like that. Could be an error, could be, maybe that's actually what it is. You never know. There are things about astronomy that we just don't know, so it could be anything.
So it must be a different mass model then.
Yeah.
You know
Sure.
what the mass was in before?
No, I do not.
Yeah, the mass changed from it. So that's showing how the star evolves over time. So as a star burns its hydrogen and helium, it actually changes its temperature and changes its surface gravity and radius. So that's just how we computed how a star evolves over time.
Thank you. Other questions?
So people have asked what the hardest part of working on their projects is. What was the funnest part of working on your project?
Ooh, I think the funnest part was also the hardest part. Yeah, no, so I knew nothing about computers actually, and learning about like a terminal and a PowerShell and like how to do all these weird things. Dr. Eastman like really helped me out with that. I know a lot of things now about my computer that I didn't know before. For example, I found out that my computer has a USB-C port that I didn't know it had. Yeah. It was fun learning that. Yeah.
Remind us, what kind of operating system are you using?
Ooh, Windows.
Windows.
Yeah.
Hi, Lisa.
Hi.
Amazing talk. And yeah, I have a question about this plot again,
Mm-hmm.
but not about the curve, but like about the black dot. So is that the, so this is for, I guess, a property of this specific star, which is TOI 123?
Yeah,
And
that's the system. Yeah.
And that's the actual, is that the model prediction, or is the red the actual?
The black dot is the model prediction. The red dot is where it actually is.
Okay.
Pretty sure.
So then but then the black line is also the model,
Yes.
and then the black dot is the model.
Yes.
So why is it that like the red star is like on the model for both of the before and after? I was just like kind of.
Could be that I got it wrong, and it's actually opposite, or could be that astronomy is just weird, man.
That's pretty fair. So thank you so much.
Are there other models? I mean, is it ambiguous to some extent, or are there other fits that would work? Or
There are some, and this is something another student did a project on, about the periods, various periods of the planet. We can just keep this running. We ran this a lot of times because it took a lot of time on my computer, because apparently my computer is slow. It took like several days to do like 300 steps. It was pretty slow. And we can keep running that as many times, and the longer we run it, the better model we're gonna get. This one is not up to publication quality. We'll probably run it like longer, but yeah.
All right. Last question, if it's fast or short. If not, let's thank the speaker again. While we're transitioning, I don't think our driver is up there, but I just want to give a shout out to ITS for supporting all the student presentations this week. Yeah. That's a lot more effort than they're probably used to. I mean, we used to have like a seminar a day, sometimes 2 or 3 a day, and that slowed down. But this week probably gave them a little taste of why we stopped that. But they all have been great presentations. All the programs have had wonderful students this summer. The last speaker of today is a special student, because the part of the CREATE program, one of the things we do is we actually do a what's called the peer mentor. This is a student who was in the program last year, and they are invited back to come back, and they serve in this peer mentor role, which is kind of like the person who's there to help organize social activities, keep the social juices flowing amongst the group, and also to, field those really quick questions like, I don't know, how do I print something? Even though I don't think we ever figured that out, did we?
We figured out you do need an SI account to print something. Oh, can you hear me? Yes. Okay.
And then, so this is Sophia, and she's our peer mentor, and she's going to close us up.
Yay. Thank you guys for sticking it out to the last presentation. My name is Sophia Garcia. I go to the University of Texas at Austin, which was not mentioned by Rudy in the introduction, but everybody else's college was, even though he is an alumni of the university. I worked with Dr. Herschel Gupta and Dr. Michael McCarthy's lab on the rotational spectrum of protonated benzonitrile. So that's what I'm here to talk to you guys about today. So our celestial topic here is these huge molecular clouds. So they're gassy, dusty clouds in interstellar space. And they're the birthplace of stars and thus eventually planet formation. So we can learn a lot if we know their composition and we know their dynamics. So that's the goal in finding these out. The thing is, these are really weird because they're in such an odd environment. They have super slow collision rates. So in this room right now, we might expect a collision between air particles maybe like once every nanosecond. And a similar collision in these molecular clouds might take like 2 weeks. It could be like one collision every 2 weeks. So super slow chemistry happening here, and that means super weird chemistry happening here. So there's two processes that can kind of speed up this slow chemical reaction process. There's bottom-up formation, which you take smaller constituents and build them up into bigger molecules. And then there's top-down formation, where you take bigger molecules and you rip them apart into smaller molecules. So this is really helpful in our goal in identifying a molecule, identifying its successor, and then trying to figure out where to go from there. So trying to find all of the molecular processes happening in these clouds by filling them in one by one, all of these molecules that may not exist on Earth, and a lot of them don't exist on Earth. So these processes tell us where to look next. And to identify these molecules in space, we can take their rotational spectrum as recorded in the lab and compare them to astronomical data recorded by radio telescopes to find their specific molecular signals in their spectra from the radio data. So early on, the molecular findings were similar to these top ones. So they were carbon chains. These are carbons in the middle, nitrogens at the end, hydrogens on the other side. And then they got just suspiciously long. They never get that long on Earth. They would just react away here. So this is like our first instance of seeing alien type of molecular formation in these clouds. And with better detectors and more like deeper integrations on radio spectrometry, we found benzonitrile. This was a recent find, and it's the first aromatic ring molecule ever found in space. And fast forward, these huge monster-looking ring molecules have also been found. And we don't really know the processes happening in between them, whether top-down or bottom-up formation processes dominate, and what's happening when. And we can use rotational spectroscopy to figure that out. So rotational spectroscopy measures the transitions between quantized rotational energy levels. So whenever a molecule is rotating, its dipole orientation is changing in space, and that will either emit or absorb radiation, which we can then detect. So that's how rotational spectroscopy works. And because it works off of this dipole moment, we can't really see nonpolar molecules. So nonpolar molecules don't have a dipole moment to interact with that radiation, so they're essentially invisible or microwave inactive to the detector. However, these ring molecules are very, very abundant on Earth, so we're looking for them in space and in these molecular clouds. But we can't see these ring molecules, right? So benzonitrile was the first ring molecule to be found thanks to this little CN dipole that you see on the right here. And that has a dipole moment, and we can detect it with rotational spectroscopy. So from there, we can kind of predict that this molecule may be protonated. And this is because we know cosmic rays to be present in the interstellar medium. So we can guess that they're hitting these clouds. And there's an abundance of H2. So when the cosmic rays hit that H2, it'll ionize it to H2+. That H2+ will really, really want another proton. It'll become H3+. And if that H3+ reacts with the known present benzonitrile molecule, it'll turn into protonated benzonitrile. Okay, and that's the star of the show today. There's also these destruction paths. Because this is so unstudied, these are probably not the only destruction paths. There's not very many recorded. We don't know much about them, but these are probably the most likely and trivial ones that are recorded online as of now. So To record this in the lab, we have to use Fourier transform microwave spectroscopy. That works in 4 main stages. So you have production, expansion, excitation, and then relaxation or detection. So for production, we take this, we have a sample tank, and we fill it with hydrogen, or H2, and benzonitrile. And we pump it through this discharge nozzle. And that's where we can apply a DC discharge voltage through it and ionize the plasma inside the nozzle before it gets expanded into the cavity, which is at vacuum. And the tank is at a higher pressure. So this pressure difference is what creates this expansion in a supersonic molecular beamform, which is crazy fast, going like Mach 2. And what that does is it rotationally cools the molecules down. So all of their rotational energy turns into translational energy, and now you're simulating an environment that's similar to the molecular cloud in the sense of temperature. So the molecular clouds are around 2 Kelvin, and we're simulating the same environment just with this pressure difference without cryogenics at all. So pretty impressive, if you ask me. And from there, we can send a microwave pulse through the spectrometer. That'll excite the molecule to its next rotational state. Once it falls back down, that's what we're recording, the de-excitation of the molecule, or its signature little wobble as it comes back down to its ground state. We detect that as a free induction decay, which is what you see here in the red. And then that's fed into our software. A Fourier transform is applied to it, and then we get the rotational spectrum of protonated benzonitrile. So before we can actually do all of this, we have to set the conditions for it. So we use another protonated molecule to set the conditions for another protonated molecule, our protonated benzonitrile in this case. And we chose, this is protonated carbonyl sulfide. We chose this because it's a readily available molecule, and it's similar to benzonitrile in the sense where you can buy it in a bottle and then make your protonated molecule along with it. So conditions like nozzle tension or microwave pulse width or DC discharge voltage can be determined and will be very similar for other protonated molecules, which is why we use this molecule to set the spectrometer's conditions so that we can then study benzonitrile and protonate that. So after that, we use the rotational constants of benzonitrile, which are inversely related to the moment of inertia of different axes of the molecule. You can plug those into a spectral simulation software, which will tell you the predicted frequencies that you can expect these rotational transition lines to appear at. And from there, we can do a deep survey, so a broad search of the rotational transitions in the cavity. And eventually, with a lot of optimization, we found these benzonitrile lines, the middle ones, are protonated benzonitrile for the first time in an overnight survey. And once we identified these, tweaked everything to be even more precise than it already was, which was honestly crazy precise, we could take deeper integrations and we could get this pretty rotational spectrum that we're looking for and get all the information that we really can get out of rotational spectroscopy with this. So now that we found it, we have to make everyone else believe that we found it. So we need to identify or confirm its identity. So there's a few things that you can do here. You can take away the DC discharge in the nozzle, so you're not creating the ion in that plasma anymore before it's expanded into the cavity. All of the ions lines disappear, and you're only seeing just the benzonitrile signature. That worked, great. Next, we applied a comically large magnet to the side of the spectrometer, and what that does is deflects any ions in it, so our protonated benzonitrile, away from the detection field, kind of like centered in it. So the signal of the protonated benzonitrile ion gets weaker. And then the last thing that we did was in our tank, we replaced the hydrogen with deuterium, which is a heavier version of hydrogen. And that can shift the spectra, that's what you're seeing here, very predictably. So because it's a bit heavier, it's going to bring its velocity down, it's moving a bit slower, and it has less kinetic energy to be able to spread these lines apart, which, as you can see in the deuterated version on top, is a bit closer than the regular protonated benzonitrile on the bottom. So these all confirm the lines of protonated benzonitrile. And the last thing that we did, you know, you're never really done. So you could always get a better signal. And what we did was we heated up our tank of hydrogen and poison, and it was very safe. And we're big on lab safety, and nobody has to worry about that. And we recorded some temperature and intensity data points. So as the temperature increased, we recorded different intensities that we were detecting in the spectrometer. Then we wrote a code using the Anton equation, the ideal gas law for benzonitrile and hydrogen, respectively, to find the partial pressures. Wrote another code to find the tank concentration and plot that against the benzonitrile intensity. So the results that you see here, the optimal concentration for the best signal that you can get is around 0.02 to 0.03%, which is a bit higher than our initial concentration, so this did help us get a better signal. Right now we're working on a paper. Hopefully that will be out soon, and more work can come from that, including the concentration optimization that can be used for other molecules to be found in the future, and other molecules can also be found once this presence is identified in space. We can use that to try and fill in more steps in the reaction networks of interstellar space. So that's pretty cool. So that's my presentation. I'd like to thank my advisors, Dr. Herschel Gupta, Dr. Michael McCarthy, and Dr. Rudy Montez. I'd also like to thank Dr. Jonathan McDowell, love him, and my peers and these beautiful internships this summer. Thank you so much. CREATE, you did amazing. I love you guys.
The University of Texas.
The University of Texas at Austin. Yes. We have another alumni in the room.
Yes.
Yeah. Hook 'em. Yes. Okay.
I apologize for not mentioning it in the intro. But yes, it is my alma mater as well. All the schools except for Worcester State I have not had the benefit of having a degree from or going to take classes from. But the other ones, yes. Do we have any questions from the audience? We have a shout out for you from Rose Garden.
Hi, Sophia. That was a great talk. I really liked it. And I'm really happy about just the fact that you can just have a molecule in a lab and I don't know, it's just really fascinating to see the actual spectrum from the molecule and then try to see it in the radio data. So I have a question about the radio data. So I'm not sure if I completely understand, but so yeah, it says deep survey. So did you find this particular molecule that you worked on in the lab in this deep survey?
Yes. The middle line right here is the first signature found of protonated benzonitrile, and the rest I want to say is a benzonitrile signature.
I think that's very amazing. And also, just another quick question: what radio telescope this survey?
It hasn't been identified in space yet, but I would be guessing it would be through Green Bank Telescope.
Okay. Awesome. Thank you so much.
Good. More questions?
All right. So I had a question about the lab setup. Do you think you could switch back to that slide real quick? All right. So that. Oh, did I turn it off? Oh, my. Okay. So the red little squiggles there. I guess one, am I correct in seeing that as just the right half of an interferogram? And if so, where's that interference coming from?
I guess in a way, it's like I was explaining before, whenever the molecule is de-exciting, it's relaxing back to its ground state, it'll because of its dipole moment, it'll interact with the radiation already in the cavity, and that absorption or emission is what we're detecting. And it's called a free induction decay, and that's what we're detecting, is this little decay. So it's a similar little, it's wobbling back down to base.
Okay, thank you.
So one thing is that you're turning off the microwave pulse. First you're exciting, right? And molecules are being polarized, and then you're turning off the lamp. And what you're seeing is this emission, which appears like that.
Yes, that's where this quick pulse, yeah.
Hi, great talk. So I was wondering, what would the implications be, if we can think of any at this point, if we were to find this protonated benzonitrile in space? What implications would that have for space chemistry, maybe the formation of stars, maybe the formation of planets?
That's a great question. Harsha, do you have an answer for that? Because I would love to know.
You can work the answer out. So if you go I want her to answer it. Okay. So go back to your reaction network that you showed formation, destruction slide.
Oh.
Yeah. So you have, this is just a set of reactions here, right? So if you form something, Sophia, by protonation, what's happening in the last step? You're making other molecules, right?
Right.
So those molecules are, protonated benzonitrile doesn't exist by itself. It is being formed from something else and is being made into something else by these processes. So that's what you want to.
So this is reacting back into benzonitrile and then HCN. So what does this mean for star formation?
Well, eventually it will mean, but we're figuring out how molecules grow in complexity and what pathways they follow. And so this is a central intermediate in the chemistry of these aromatic rings, and nothing much is known about the production or destruction of these species. So what she showed, the bottom up versus top down, go back one slide. There's a lot of different molecules that are found between benzonitrile and that huge molecule that was detected by a postdoc in our lab. And we want to understand how things grow. And protonation does two things. One is it allows this molecule to react fast now with electrons and other species. And by learning how this is formed or destroyed, we can now plug in those abundances. We can detect this ion and plug in those abundances in chemical models, which can tell us, okay, how does this affect the chemistry downstream? And does it explain all the abundances we see? Because this is not in isolation. This is part of a network.
Yeah, so at the end of the day, we don't know. I think
But we would know. We will know if we do the observation.
Right. So this would be a key chemical intermediate, and like Crystal said, it's very reactive. So it would definitely insinuate a further step down the line in these huge networks.
Great. Time for one more question.
I hope it's an easier one, at least. What are the biggest sources of error or uncertainty in your setups with these measurements? What's causing you the most issue in finding your lines correctly or background noise?
Like in the recorded spectrum? There's an error in the instrument itself. I want to say it's 5 kilohertz.
Yeah,
is that right?
Measurement uncertainty. You can measure things very precisely. So
Yeah, it is very precisely measured.
But what's the actual uncertainty there?
Is it 5 kilohertz? Is it 10 kilohertz?
So it depends on how broad your lines are, but the intrinsic, the resolution that we can get is up to 1 kilohertz, and we can measure lines to about that, maybe even better. These lines are broader, so they're not as precisely measured, but they're still like 5 kilohertz, 5 to 7 kilohertz full width and a half max. Actually greater, but the precision is that much. For comparison, lines in space are very, very sharp too. So we're approaching the Doppler width of the line that you can observe in a dark cloud. Ideally, we want to do better, but there are a few things that affect these particular measurements, which she didn't talk about here. So, ballpark number, 1 part in how many? Can we measure to precisely 2?
1 part in how many what? Hertz?
What fractional accuracy
Oh,
for measurement?
0.018? Was that the right number?
So 1 part in, we could measure things to 1 part in 10 to the 6 or better frequency.
That's crazy. Yes, very precise, very precise.
Thank you, everybody. And thank you for staying for the complete session. And let's thank all of the great interns again. Thank you, Sean.